Hello everyone, welcome to this fantastic machine learning beginner to advanced full course by Simplilearn. But before we begin, if you enjoy watching these videos and find them interesting, subscribe to our channel as we bring you the best videos daily. Also, hit the bell icon to never miss any updates from Simplilearn. So let's get started. We will brief you with machine learning introduction. After that, we will see the types of machine learning. Going forward, we will cover machine learning roadmap, skills required for machine learning engineers, and the top applications and projects for machine learning. We will walk you through some fantastic concepts like AI versus ML versus DL. By proceeding with the course, we will teach you different machine learning algorithms like linear regression, logistic regression, and many more with hands-on demo explanations in Python. We will walk you through unique projects like fake news detection, object detection, and many more. These projects will serve you as the finest portfolios for your future interviews. Speaking of interviews, we have covered you long with most frequently asked machine learning interview questions to help you crack the most challenging interviews. But before we begin to understand what machine learning is,
here we have our, it looks a little bit like Frankenstein, our Frankenstein-looking robot. Today, let me tell you what is machine learning. Machine learning works on the development of computer programs that can access data and use it to automatically learn and improve from experience. Watch a robot builder construct a house in 2 days. This was back in July 29th, 2016, so that's pretty impressive. This amount of time to continue to grow in its development. And it's smart enough to leave spaces in the brickwork for wiring and plumbing and can even cut and shape bricks to size. Amazon Echo relies on machine learning, and with more data it becomes more accurate. Play your favorite music, order pizza from Domino's, voice control your home, request rides from Uber. Have you ever wondered the difference between AI, machine learning, and deep learning? Artificial intelligence, a technique which enables machines to mimic human behavior. This is really important because this is how we are able to gauge how well our computations or what we're working on works, is the fact that we're mimicking human behavior. We're using this to replace human work and make it more efficient and make it more streamlined and more accurate. And so the center of artificial intelligence is the big picture of all of this put together. IBM Deep Blue Chess, electronic game characters. Those are just a couple examples of artificial intelligence. Machine learning, a technique which uses statistical methods, enabling machines to learn from their past data. So this means if you have your input from last time and you have your answer, you use that to help prove the next guess it makes for the correct answer. IBM Watson, Google search algorithm, email spam filters, these are all part of machine learning. And then deep learning, which is a subset of machine learning, composing algorithms that allow a model to train itself and perform tasks. AlphaGo, natural speech recognition. These are a couple examples. Deep learning is associated with tools like neural networks where it's kind of a black box. As it learns, it changes all these things that are, as a human, we would have a very hard time tracking. And it's able to come up with an answer from that. Now let's see how machine learning works. First, we start with training the data. Once we've trained the data, we go into the machine learning algorithm, which then puts the data into a processing, which then goes down to another machine learning algorithm. And then we take new data, because you have to test whatever you did and make sure it works correctly, and we put that into the same algorithm. Once we do that, we check our prediction, we check our results, and from the prediction, if we've set aside some training data and we find out it didn't do a good job predicting it, and it gets a thumbs down as you see, then we go back to the beginning and we retrain the algorithm. And a lot of times it's not just about getting the wrong answer, it's about continually trying to get a better answer. So you'll see the first time you might be like, oh, this is not the answer I want, depending on what domain you're working in, whether it's medical, economical, business, stocks, whatever. You try out your model, and if it's not giving you a good answer, you retrain it. If you think you can get a better answer, you retrain it, and you keep doing that until you get the best answer you can.
Now let's look into the types of machine learning. Machine learning is primarily of 3 types. First one is supervised machine learning. As the name suggests, you have to supervise your machine learning while you train it to work on its own. It requires labeled training data. Next up is unsupervised learning, wherein there will be training data but it won't be labeled. Finally, there is reinforcement learning, wherein the system learns on its own. Let's talk about all these types in detail. Let's try to understand how supervised learning works. Look at the pictures very carefully. The monitor depicts the model or the system that we are going to train. This is how the training is done. We provide a dataset that contains pictures of a kind of a fruit, say an apple. Then, we provide another dataset which lets the model know that these pictures were that of a fruit called apple. This ends the training phase. Now, what we will do is we provide a new set of data which only contains pictures of apple. Now here comes the fun part. The system can actually tell you what fruit it is. And it will remember this and apply this knowledge in future as well. That's how supervised learning works. You are training the model to do a certain kind of an operation on its own. This kind of a model is generally used into filtering spam mails from your email accounts as well. Yes, surprised, aren't you? So let's move on to unsupervised learning now. Let's say we have a dataset which is cluttered. In this case, we have a collection of pictures of different fruits. We feed this data to the model and the model analyzes the data to figure out patterns in it. In the end, it categorizes the photos into 3 types as you can see in the image based on their similarities. So, you provide the data to the system and let the system do the rest of the work. Simple, isn't it? This kind of a model is used by Flipkart to figure out the products that are well suited for you. Honestly speaking, this is my favorite type of machine learning out of all the 3. And this type has been widely shown in most of the sci-fi movies lately. Let's find out how it works. Imagine a newborn baby. You put a burning candle in front of the baby. The baby does not know that if it touches the flame, its fingers might get burned. So it does that anyway and gets hurt. The next time you put that candle in front of the baby, it will remember what happened the last time and would not repeat what it did. That's exactly how reinforcement learning works. We provide the machine with a dataset wherein we ask it to identify a particular kind of a fruit, in this case an apple. So what it does as a response, it tells us that it's a mango. But as we all know, it's a completely wrong answer. So as a feedback, we tell the system that it's wrong, it's not a mango, it's an apple. What it does, it learns from the feedback and keeps that in mind. When the next time, when we ask a same question, it gives us the right answer. It is able to tell us that it's actually an apple. That is a reinforced response. So that's how reinforcement learning works. It learns from its mistakes and experiences. This model is used in games like Prince of Persia or Assassin's Creed or FIFA, wherein the level of difficulty increases as you get better with the games. Just to make it more clear for you, let's look at a comparison between supervised and unsupervised learning. Firstly, the data involved in case of supervised learning is labeled. As we mentioned in the examples previously, we provide the system with a photo of an apple and let the system know that this is actually an apple. That is called label data. So the system learns from the label data and makes future predictions. Now, unsupervised learning does not require any kind of label data because its work is to look for patterns in the input data and organize it. The next point is that you get a feedback in case of supervised learning. That is, once you get the output, the system tends to remember that and uses it for the next operation. That does not happen for unsupervised learning. And the last point is that supervised learning is mostly used to predict data, whereas unsupervised learning is used to find out hidden patterns or structures in data. I think this would have made a lot of things clear for you regarding supervised and unsupervised learning.
In recent years, artificial intelligence and machine learning have permeated every aspect of our lives. If you are a programmer, chances are you have begun utilizing GitHub's Copilot, an AI tool that transforms natural language prompts into coding suggestions, streamlining the programming process. As a writer, you may have encountered OpenAI's GPT-3 or similar autoregressive language models that leverage deep learning to generate text resembling human language. Many of us dedicated a few hours to experimenting with DALL-E 2, the AI/ML powered text to image generator capable of producing intricate visuals based on the most unusual request. Not only is DALL-E 2 exponentially more powerful, but it also has the potential to revolutionize the field of digital art. Consider its impact on a digital artist, illustrator, or graphic designer career. Imagine creating a highly realistic image within seconds using an app. These technologies have significant real-world applications with far-reaching implications. Let me tell you some fascinating facts about machine learning. According to recent studies, machine learning related job postings have increased by a staggering 344% in the past 5 years. Companies across the globe are actively seeking professionals who can harness the power of data and build intelligent systems. The average salary is $190,000 in US and 26 lakhs per annum in India. Accelerate your career in AI and ML with our comprehensive postgraduate program in AI and machine learning. Gain expertise in machine learning, deep learning, NLP, computer vision, and reinforcement learning. You will receive a prestigious certificate, exclusive alumni membership, and hackathons and Ask Me Anything sessions by IBM. With 3 capstone and 25 plus industry projects using real data sets from Twitter, Uber, and more, you will gain practical experience. Master classes by Purdue faculty and IBM experts ensure top-notch education. Simplilearn's Job Assist helps you get noticed by leading companies. Live sessions on AI trends like ChatGPT, generative AI, and explainable AI. This program covers statistics, Python, supervised and unsupervised learning, NLP, neural networks, computer vision, GANs, Keras, TensorFlow, and many more skills. Enroll now and unlock exciting AI and ML opportunities. The link is mentioned in the description box below. With that having said, now here is a comprehensive step-by-step guide to learning machine learning. Number 1 is skills required. Number 2, job roles in ML. Number 3, companies hiring ML engineers. And the number 4 is future scope of ML. Now starting with the number 1, that is fundamentals of machine learning. Familiarize yourself with the fundamentals of machine learning. In the initial stages of learning to drive, we are familiarized with the different elements, varieties, and regulations pertaining to operating a car. It is essential to delve into the fundamentals of machine learning to understand what lies ahead and the required knowledge. Now moving to number 2, that is acquiring proficiency in Python or R programming language. To excel in the field of artificial intelligence and machine learning, it is crucial to develop a strong command of Python or R programming language. Both Python and R are widely used in the data science community due to their versatility and extensive libraries for scientific computing. So now moving on to the third step, that is gain knowledge of essential Python libraries for machine learning. Once you have acquired proficiency in Python as part of our machine learning journey, the subsequent step involves familiarizing yourself with essential Python libraries crucial for working with data and implementing machine learning solutions. The key Python libraries that you should learn for machine learning are NumPy, Pandas, Matplotlib, and scikit-learn. Now moving to step 4, that is learn and implement various machine learning algorithms. After gaining proficiency in Python as part of our machine learning journey, the subsequent milestone involves learning various machine learning algorithms and their implementation using Python. Listed below are some of the key machine learning algorithms that are essential to learning. Number 1, linear regression. Number 2, logistic regression. Number 3, passive regression. Number 4, naive Bayes. Number 5, support vector machines. Now moving to step 5, master the concepts and implementation of neural networks. Once you have acquired knowledge of Python and machine learning algorithms, the next significant step in the machine learning roadmap is to learn neural network architecture and their implementations using Python. Outlined below are several crucial neural network architectures that are essential to learning. Number 1, artificial neural networks. Number 2, CNN. Number 3, RNN. Number 4, long short term memory. Now moving to step 6, that is engage hands-on projects to apply your knowledge and reinforce your understanding. After acquiring knowledge of Python, machine learning algorithms, and neural network architectures, the next crucial step is the machine learning roadmap and is to gain practical experience by working on projects that allow you to apply what you have learned. The first project is iris flower classification. Number 2, California house price prediction. Number 3, stock price prediction. Number 4, customer segmentation. Now we'll move to job roles in machine learning. Machine learning, as highlighted earlier, has gained immense popularity for its ability to elevate human efforts and enhance machine performance through autonomous learning. This popularity has resulted in lucrative and sought after career options within the field, including roles like machine learning engineer. So the duty of a machine learning engineer encompasses the creation, construction, and deployment of machine learning models. Collaborating closely with data scientists and software engineers, they participate in the development and execution of machine learning systems. According to Glassdoor, ML engineers can earn up to $150,000 in US and 11 lakhs per annum in India. Now moving to data scientist. The role of a data scientist involves gathering, scrutinizing, and interpreting extensive datasets. Leveraging machine learning algorithms, they uncover patterns and glean insights from the data, utilizing this knowledge to inform decisions and address challenges. According to Glassdoor, data scientists earn $145,000 in US and 13 lakhs per annum in India. Now moving to NLP engineers. The specific duties may vary based on the role and sector, but as outlined by Freelancer Map, an NLP engineer typically engage in tasks such as designing natural language processing systems and addressing speech patterns and AI speech recognition. According to Glassdoor, an NLP engineer can earn $120,000 in US and 10 lakhs per annum in India. Now moving to computer vision engineer. Engineers specializing in computer vision operate within the realm of computer vision, employing machine learning to empower computers to comprehend and interpret visual data from their surroundings. Their responsibilities include tasks such as image and video analysis and object detection. According to Glassdoor, CV engineers earn $156,000 in US and 8 lakhs per annum in India. Now moving to business intelligence developer. The main role of a BI developer is to develop, deploy, and maintain BI tools and interfaces. They are also responsible for simplifying highly technical language and complex information into layman's terms for everyone else in the company to understand. According to Glassdoor, business intelligence developers earn $105,000 in US and 7 lakhs per annum in India. Now we'll see the top companies hiring for machine learning engineer. Number 1 is Amazon. Then we have Accenture, Google, Apple, Intel. So these are the top hiring companies that hire machine learning engineers. Now we'll talk about future of machine learning. Machine learning has a bright future but faces several difficulties. ML is predicted to grow increasingly pervasive as technology develops, revolutionizing sectors including healthcare, banking, and transportation. The work market will change due to AI-driven automation, necessitating new position and skills. And with this, we have come to the end of this video. I hope you found this video informative and interesting.
Hello everyone and welcome to our video on skills required for an ML engineer. Machine learning has been the talk of the town lately. Every organization has realized the potential of machine learning in improving their business objectives and attaining their enterprise goals. This expanding demand has led to a lot of people applying for machine learning jobs and upskilling themselves in the field of machine learning. You can take up this growing opportunity in the field of machine learning and utilize it to land yourself a very challenging, fulfilling and high-paying job. In this video, we will be breaking down in complete detail each and every skill that you would need in order to crack the machine learning engineer job interview. Well, ML is not just a passing trend. It's a seismic shift that is reshaping our world and creating new avenues for innovation and discovery. So by embracing a career in ML, you become part of a dynamic field that thrives on solving complex problems, pushing boundaries, and making a profound impact on society. So the demand for ML professionals is skyrocketing across industries, from healthcare and finance to entertainment and transportation. Organizations are actively seeking talented individuals who can harness the power of AI to drive their business forward. But what skill does it take to become an ML engineer? How can you embark on this thrilling journey? We have the answers to all your questions. Also, accelerate your career in AI and ML with our comprehensive postgraduate program in AI and machine learning. Gain expertise in machine learning, deep learning, NLP, computer vision, and reinforcement learning. You will receive a prestigious certificate, exclusive alumni membership, and Ask Me Anything sessions by IBM. With 3 capstone projects and 25 plus industry projects using real datasets from Twitter, Uber, and more, you will gain practical experience. Masterclasses by Caltech faculty and IBM experts ensure top-notch education. Simplilearn's Job Assist help you get noticed by leading companies. This program covers Python, supervised and unsupervised learning, NLP, neural networks, computer vision, GANs, Keras, TensorFlow, and many more other skills. So enroll now and unlock exciting AI and ML opportunities. The link is in the description box below. So without any further delay, let's get started.
To become a machine learning engineer, you need a combination of technical skills, non-technical skills, and some bonus skills. So here are some essential skills required to pursue a career as an ML engineer. So first we will talk about some technical skills to become a ML engineer. So first one in the list is programming languages. Strong programming skills are essential. You should be proficient in at least one programming language such as Python or R. Python is widely used in the ML community due to its rich libraries, that is NumPy, Pandas, TensorFlow, and PyTorch that supports ML tasks. And the second on the list is machine learning algorithms and techniques. You should have a solid understanding of various ML algorithms such as linear regression, logistic regression, decision trees, random forest, neural network, and deep learning. Familiarize yourself with the principles behind these algorithms, their pros and cons, and when to use them. So third one on the list is data preprocessing. ML models require clean and well prepared data. You should know how to handle missing data, deal with normalized and standardized data, and the final is perform feature engineering. Understanding data preprocessing technique is crucial for effective ML model training. And the fourth one is data manipulation and analysis. Data is the foundation of ML model. You should be skilled in the data manipulation and analysis using libraries like NumPy and Pandas. This includes cleaning and transforming data, exploratory data analysis, which is EDA, and understanding the statistical properties of the data. And the fifth one is machine learning libraries and frameworks. Familiarity with popular ML libraries and frameworks is essential. Some commonly used one include NumPy, Pandas, TensorFlow, and PyTorch. These libraries provide pre-implemented ML algorithms, neural network architectures, and tools for model training and evaluation. Now that we have seen the technical machine learning engineering skills, let us have a look at the non-technical machine learning skills. So the first one is industry knowledge. Machine learning projects that effectively tackle genuine challenges are likely to achieve great success, regardless of the industry you are involved in. It is crucial to have a comprehensive understanding of its operation and identify ways to optimize business outcomes. And the second one on the list is effective communication. Effective communication plays a crucial role in facilitating these interactions. Companies seeking skilled ML engineer value candidates who can effectively convey technical discoveries to non-technical terms like marketing or sales, demonstrating clarity and fluency in their explanation. Moving forward, let's see some bonus skills to become a ML engineer. The first one on the list is reinforcement learning. In 2023, reinforcement learning emerged as a catalyst for numerous captivating advancements in deep learning and artificial intelligence. To pursue a career in robotics, self-driving cars, or any other AI-related field, it is crucial to comprehend this concept. And the second on the list is computer vision. Computer vision and machine learning are fundamental branches of computer science that can independently fuel highly advanced systems relying on CV and ML algorithm. However, their combination has a potential to unlock greater even possibilities and achievements. So remember that the field of ML is constantly evolving, so continuous learning and staying updated with the latest development and the research papers are essential to be the practical.
Machine learning has improved our lives in a number of wonderful ways. Today, let's talk about some of these. I'm Rahul from Simplilearn, and these are the top 10 applications of machine learning. First, let's talk about virtual personal assistants. Google Assistant, Alexa, Cortana, and Siri. Now, we've all used one of these at least at some point in our lives. Now, these help improve our lives in a great number of ways. For example, you could tell them to call someone. You could tell them to play some music. You could tell them to even schedule an appointment. So how do these things actually work? First, they record whatever you're saying, send it over to a server, which is usually in a cloud, decode it with the help of machine learning and neural networks, and then provide you with an output. So if you've ever noticed that these systems don't work very well without the internet, that's because the server couldn't be contacted. Next, let's talk about traffic predictions. Now say I wanted to travel from Buckingham Palace to Lord's Cricket Ground. The first thing I would probably do is to get on Google Maps. So search it. And let's put it here. So here we have the path you should take to get to Lord's Cricket Ground. Now here the map is a combination of red, yellow and blue. Now the blue regions signify a clear road, that is, you won't encounter traffic there. The yellow indicate that they are slightly congested and red means they're heavily congested. So let's look at the map, a different version of the same map. And here, as I told you before, red means heavily congested, yellow means slow moving and blue means clear. So how exactly is Google able to tell you that the traffic is clear, slow moving or heavily congested? So this is with the help of machine learning and with the help of two important measures. First is the average time that's taken on specific days at specific times on that route. The second one is the real-time location data of vehicles from Google Maps and with the help of sensors. Some of the other popular map services are Bing Maps, Maps.me, and here we go. Next up, we have social media personalization. So say I want to buy a drone and I'm on Amazon and I want to buy a DJI Mavic Pro. The thing is, it's close to 1 lakh, so I don't want to buy it right now. But the next time I'm on Facebook, I'll see an advertisement for the product. Next time I'm on YouTube, I'll see an advertisement. Even on Instagram, I'll see an advertisement. So here, with the help of machine learning, Google has understood that I'm interested in this particular product. Hence, it's targeting me with these advertisements. This is also with the help of machine learning. Let's talk about email spam filtering. Now, this is the spam that's in my inbox. Now, how does Gmail know what's spam and what's not spam? So Gmail has an entire collection of emails which have already been labeled as spam or not spam. So after analyzing this data, Gmail is able to find some characteristics like the word lottery or winner. From then on, any new email that comes to your inbox goes through a few spam filters to decide whether it's spam or not. Now, some of the popular spam filters that Gmail uses is content filters, header filters, general blacklist filters, and so on. Next, we have online fraud detection. Now, there are several ways that online fraud can take place. For example, there's identity theft, where they steal your identity, fake accounts, where these accounts only last for how long the transaction takes place and stop existing after that, and man-in-the-middle attacks, where they steal your money while the transaction is taking place. The feed-forward neural network helps determine whether a transaction is genuine or fraudulent. So what happens with feed-forward neural networks are that the outputs are converted into hash values, and these values become the inputs for the next round. So for every real transaction that takes place, there's a specific pattern. A fraudulent transaction would stand out because of the significant changes that it would cause with the hash values. Stock market trading. Machine learning is used extensively when it comes to stock market trading. Now you have stock market indices like Nikkei. They use long short-term memory neural networks. Now these are used to classify, process and predict data when there are time lags of unknown size and duration. Now this is used to predict stock market trends. Assistive medical technology. Now, medical technology has been innovated. With the help of machine learning, diagnosing diseases has been easier, from which we can create 3D models that can predict where exactly there are lesions in the brain. It works just as well for brain tumors and ischemic stroke lesions. They can also be used in fetal imaging and cardiac analysis. Now, some of the medical fields that machine learning will help assist in is disease identification, personalized treatment, drug discovery, clinical research, and radiology. And finally, we have automatic translation. Now, say you're in a foreign country and you see billboards and signs that you don't understand. That's where automatic translation comes of help. Now, how does automatic translation actually work? The technology behind it is the same as the sequence-to-sequence learning, which is the same thing that's used with chatbots. Here, the image recognition happens using convolutional neural networks, and the text is identified using optical character recognition. Furthermore, the sequence-to-sequence algorithm is also used to translate the text from one language to the other.
Finding a suitable job in the field of machine learning is becoming increasingly difficult. The ideal way to display your machine learning skill is in the form of portfolio of data science and machine learning projects. A solid portfolio of projects will illustrate that you can utilize those machine learning skills in your profile as well. Projects like movie recommendation system, fake news detection, and many more are the best way to improve your early programming skills. You may have the knowledge, but putting it to the use what is keep you competitive. Here are 10 machine learning projects that can increase your portfolio and enable you to acquire a job as a machine learning engineer. At number 10, we have loan approval prediction system. In this machine learning project, we will analyze and make prediction about the loan approval process of any person. This is a classification problem in which we must determine whether or not the loan will be approved. A classification problem is a predictive modeling problem that predicts a class label for a given example of input data. Some classification problems include spam email, cancer detection, sentiment analysis, and many more. You can check the project link from the description box below to understand classification problem and how to build a loan prediction system. At number 9, we have fake news detection system. Do you believe in everything you read in social media? Isn't it true that not all news is true? But how will you recognize fake news? ML is the answer. You will be able to tell the difference between real and fake news by practicing this project of detecting fake news. This ML project for detecting fake news is concerned with the fake news and the true news. On our dataset, we create a TFID vectorizer with sklearn. The model is then fitted using a passive-aggressive classifier that has been initialized. Finally, the accuracy score and the confusion matrix indicate how well our model performs. The link for the project is in the description box below. At number 8, we have personality prediction system. The idea is based on determining an individual personality using machine learning techniques. A person's personality influences both his personal and professional life. Nowadays, many companies are shortlisting applicants based on their personality, which increases job efficiency because the person is working on what he is good at rather than what he is compelled to do. In our study, we attempted to combine personality prediction system using machine learning techniques such as SVD, naive-bayes, and logistic regression to predict a person's personality and talent prediction using phrase frequency method. This model or method allows users to recognize their personality and technical abilities easily. To learn about more this project, check the link in the description box below. At number 7, we have Parkinson disease system. Parkinson disease is a progressive central nervous system element that affects movement and causes tremors and stiffness. It comprises 5 stages and affects more than 1 million worldwide each other. In this machine learning project, we will develop an SVM model using Python modules, scikit-learn, NumPy, and pandas. An SVM, we will import the data, extract the features and label and scale the features, split the dataset, design an SVM model, and calculate the model accuracy. And at the end, we will check the Parkinson disease for the individual. To learn about more this project, check the link in the description box below. At number 6, we have text-to-speech converter application. The machine learning domain of audio is undoubtedly cutting edge right now. The majority of the applications available today are the commercial. The community is building several audio-specific open source framework and algorithm. Other text-to-speech APIs are available for this project. We will utilize pyttsx3. pyttsx3 is a Python text-to-speech conversion library. It operates offline unlike other libraries and is compatible with Python 2 and Python 3. Before API, various pre-trained models were accessible in Python, but changing the voice or volume was often difficult. It also needed additional computational power. To learn more about this project, check the link in the description box below. At number 5, we have speech recognition system. Speech recognition, often known as speech to text, is the capacity of a machine or program to recognize and transfer words spoken aloud into readable text. ML speech recognition uses algorithms that model speech in terms of both language and sound to extract the more important parts of the speech, such as words, sentences, and acoustic modeling is used to identify the phonemes and the phonetics on the speech. For this project, we will utilize pyttsx3. pyttsx3 is a Python text-to-speech conversion library. It operates offline unlike other libraries and is compatible with Python 2 and Python 3. To learn more about this project, check the link in the description box below. At number 4, we have sentiment analysis. Sentiment analysis, also known as opinion mining, is a straightforward process of determining the author's feeling about a text. What was the user intention when he or she wrote something? To determine what could be personal information, we employ a variety of natural language processing and text analysis technology. We must detect, extract, and quantify such information from the text to enable classification and data manipulation. In this project, we will use the Amazon customer review dataset for the sentiment analysis. Check the link in the description box below. At number 3, we have image classification using KNN. Deep learning is a booming field currently. Most projects and problem statements use deep learning is and any sort of work. Many of you, like myself, would choose a conventional neural network as a deep learning technique for answering any computer vision problem statement. In this project, we will use CNN to develop an image processing project and learn about its capabilities and why it has become so popular. We will go over each stage of creating our CNN model and our first spectacular project. We will use the CFR10 dataset for image classification in this project. To learn more about this project, check the link in the description box below. At number 2, we have face recognition system. Currently, technology absolutely amazes people with incredible invention that makes life easier and more comfortable. Face recognition has shown to be the least intrusive and fastest form of the biometric verification over time. This project will use OpenCV and face recognition libraries to create a face detection system. OpenCV provides a real-time computer vision tool, library, and hardware. We can create amazing real-time projects using OpenCV. To learn how to create face recognition system for you, check the link in the description box below. And last but not the least, we have movie recommendation system. Almost everyone today uses technology to stream movies and television shows. While figuring out what to stream next can be disheartening. Recommendations are often made based on a viewer history and preferences. This is done through a machine learning and can be a fun and the easy project for the beginners. New programmers can practice by coding in either Python or R, and with the data from the movie lens dataset generated by the more than 6,000 users. To learn how to create movie recommendation system for yourself or for your loved ones, check the project in the description box below.
Human versus artificial intelligence. Humans are amazing. Let's just face it. We're amazing creatures. We're all over the planet. We're exploring every niche and nook. We've gone to the moon. We've gone into outer space. We're just amazing creatures. We're able to use the available information to make decisions, to communicate with other people, identify patterns in data, remember what people have said, adapt to new situations. So let's take a look at this. So you can get a picture. You're a human being, so you know what it's like to be human. Let's take a look at artificial intelligence versus the human. Artificial intelligence develops computer systems that can accomplish tasks that require human intelligence. So when we're looking at this, one of the things that computers can do is they can provide more accurate results. This is very important. Recently I did a project on cancer where I was identifying markers. And as a human being, you look at that and you might be looking at all the different images and the data that comes off of them and say, I like this person, so I want to give them a very good outlook. And the next person you might not like, so you want to give them a bad outlook. Well, with artificial intelligence, you're going to get a consistent prediction of what's going to come out. Interacts with humans using their natural language. We've seen that as probably the biggest development feature right now that's in the commercial market that everybody gets to use, as we saw with the example of Alexa. They learn from their mistakes and adapt to new environments. So we see this slowly coming in more and more. And they learn from the data and automate repetitive learning. Repetitive learning has a lot to do with the neural networks. You have to program thousands upon thousands of pictures in there, and it's all automated. So as today's computers evolve, it's very quick and easy and affordable to do this. What is machine learning and deep learning all about? Imagine this. Say you had some time to waste. Not that any of us really have a lot of time anymore to just waste in today's world. And you're sitting by the road, and you have a whole lot of time passes by. There's a few hours, and suddenly you wonder how many cars, buses, trucks, and so on passed by in the 6 hours. Now, chances are you're not going to sit by the road for 6 hours and count buses, cars, and trucks, unless you're working for the city and you're trying to do city planning, and you want to know, hey, do we need to add a new truck route? Maybe we need a bicycle lane because we have a lot of bicyclists here, that kind of thing. So maybe city planning would be great for this. Machine learning. Well, the way machine learning works is we have labeled data with features. Okay, so you have a truck or a car, a motorcycle, a bus, or a bicycle, and each one of those are labeled. It comes in, and based on those labels and comparing those features, it gives you an answer. It's a bicycle, it's a truck, it's a motorcycle. Let's look a little bit more in depth on this. In the model here, the features we're looking at would be like the tires. Someone sits there and figures out what a tire looks like. It takes a lot of work. If you try to figure the difference between a car tire, a bicycle tire, a motorcycle tire, so in the machine learning field, this could take a long time if you're going to do each individual aspect of a car and try to get a result on there. And that's what they did do. That was this is still used on smaller amounts of data where you figure out what those features are and then you label them. Deep learning. So with deep learning, one of our solutions is to take a very large unlabeled data set and we put that into a training model using artificial neural networks. And then that goes into the neural network itself when we create a neural network. And you'll see the arrows are actually kind of backward, but which actually is a nice point because when we train the neural network, we put the bicycle in and then it comes back and says, if it said truck, it comes back and says, well, you need to change that to bicycle. And then it changes all those weights going backward, they call it back propagation, and let it know it's a bicycle, and that's how it learns. Once you've trained the neural network, you then put the new data in, and they call this testing the model, so you need to have some data you've kept off to the side where you know the answer to. And you take that and you provide the required output, and you say, okay, is this neural network working correctly? Did it identify a bike as a bike, a truck as a truck, a motorcycle as a motorcycle? Let's just take a little closer look at that. Determining what objects are present in the data. So how does deep learning do this? And here we have the image of the bike, It's 28 by 28 pixels. That's a lot of information there. Could you imagine trying to guess that this is a bicycle image by looking at each one of those pixels and trying to figure out what's around it? And we actually do that as human beings. It's pretty amazing. We know what a bicycle is, and even though it comes in as all this information. And what this looks like is the image comes in, it converts it into a bunch of different nodes. In this case, there's a lot more than what they show here. And it goes through these different layers and out comes and says, okay, this is a bicycle. A lot of times they call this the magic black box. Why? Because as we watch it go across here, all these weights and all the math behind this, and it's a little complicated on the math side. You really don't need to know that when you're programming or working with the deep learning. But it's like magic. You don't know, you really can't figure out what's going to come out by looking what's in each one of those dots and each one of those lines are firing and what's going in between them. So we like to call it the magic box. So that's where deep learning comes in. And in the end, it comes up and you have this whole neural network. It comes up and it says, okay, we fire all these different pixels and we connects all these different dots and gives them different weights, and it says, okay, this is a bicycle. And that's how we determine what the object is present in the data with deep learning. Machine learning. We're going to take a step into machine learning here, and you'll see how these fit together in a minute. The system is able to make predictions or take decisions based on past data. That's very important for machine learning, is that we're looking at stuff, and based on what's been there before, we're creating a decision on there. We're creating something out of there. We're coloring a beach ball. We're telling you what the weather is in Chicago. What's nice about machine learning is a very powerful processing capability. It's quick and accurate outcomes, so you get results right away. Once you program the system, the results are very fast. And the decisions and predictions are better. They're more accurate. They're consistent. You can analyze very large amounts of data. Some of these data things that they're analyzing now are petabytes and terabytes of data. It would take hundreds of people hundreds of years to go through some of this data and do the same thing that the machine learning can do in a very short period of time. And it's inexpensive compared to hiring hundreds of people. So it becomes a very affordable way to move into the future, is to apply the machine learning to whatever businesses you're working on. And deep learning. Systems think and learn like humans using artificial neural networks. Again, it's like a magic box. Performance improves with more data. So the more data the deep learning gets, the more it gives you better results. It's scalability. So you can scale it up, you can scale it down, you can increase what you're looking at. Currently, we're limited by the amount of computer processing power as to how big that can get, but that envelope continually gets pushed every day on what it can do. Problem solved in an end-to-end method. So instead of having to break it apart, and you have the first piece coming in and you identify tires, and the second piece is identifying labeling handlebars, and then you bring that together, that if it has handlebars and tires, it's a bicycle, and if it has something that looks like a large square, it's probably a truck. The neural networks does this all in one network. You don't really know what's going on in all those weights and all those little bubbles, but it does it pretty much in one package. That's why the neural network systems are so big nowadays and coming into their own. Best features are selected by the system. And this is important. They kind of put it's on a bullet on the side here. It's a subset of machine learning. This is important. When we talk about deep learning, it is a form of machine learning. There's lots of other forms of machine learning, data analysis, but this is the newest and biggest thing that they apply to a lot of different packages, and they use all the other machine learning tools available to work with it. And it's very fast to test. You put in your information, you then have your group of tests, and then you held some aside, you see how does it do. It's very quick to test it and see what's going on with your deep learning and your neural network. Are they really all that different? AI versus machine learning versus deep learning. Concepts of AI. So we have concepts of AI. You'll see natural language processing, machine learning, an approach to create artificial intelligence. So it's one of the subsets of artificial intelligence. Knowledge representation, automated reasoning, computer vision, robotics, machine learning versus AI versus deep learning, or AI and machine learning and deep learning. So when we look at this, we have AI with machine learning and deep learning. And so we're going to put them all together. We find out that AI is the big picture. We have a collection of books. It goes through some deep learning. The digital data is analyzed. Text mining comes through. The particular book you're looking for, maybe it's a genre of books, is identified. And in this case, we have a robot that goes and gives a book to the patron. I have yet to be at a library that has a robot bring me a book, but that will be cool when it happens. So we'll look at some of the pieces here. This information goes into, as far as this example, the translation of the handwritten printed data to digital form. That's pretty hard to do. That's pretty hard to go in there and translate hundreds and hundreds of books and understand what they're trying to say if you've never read them. So in this case, we used a deep learning because you can already use examples where they've already classified a lot of books, and then they can compare those texts and say, oh, okay, this is a book on automotive repair. This is a book on robotic building. The digital data is then analyzed. Then we have more text mining using machine learning. So maybe we'd use a different program to do a basic classify what you're looking for and say, oh, you're looking for auto repair and computers. So you're looking for automated cars. Once it's identified, then of course it brings you the book. So here's a nice summation of what we were just talking about. AI with machine learning and deep learning. Deep learning is a subset of machine learning, which is a subset of artificial intelligence. So you can look at artificial intelligence as the big picture. How does this compare to the human experience in either doing the same thing as a human we do, or it does it better than us? And machine learning, which has a lot of tools, is something that learns from data, past experiences. It's programmed. It comes in there and it says, hey, we already had these 5 things happen. The 6th one should be about the same. And then there's a lot of tools in machine learning, but deep learning then is a very specific tool in machine learning. It's the artificial neural network, which handles large amounts of data and is able to take huge pools of experiences, pictures, and ideas and bring them together. Real life examples. Artificial intelligence, news generation, very common nowadays as it goes through there and finds the news articles or generates the news based upon the news feeds or the backend coming in and says, okay, let's give you the actual news based on this. There's all the different things, Amazon Echo, they have a number of different Prime Music on there. Of course, there's also the Google Command, and there's also Cortana. There's tons of smart home devices now where we can ask it to turn the TV on or play music for us. That's all artificial intelligence. From front to back, you're having a human experience with these computers and these objects that are connected to the processing. Machine learning, spam detection, very common. Machine learning doesn't really have the human interaction part. So this is the part where it goes and says, okay, that's a spam, that's not a spam, and it puts it in your spam folder. Search engine result refining, another example of machine learning, whereas it looks at your different results and it is able to categorize them as far as this had the most hits, this is the least viewed, this has 5 stars, however they want to weight it. All good examples of machine learning. And then the deep learning. Deep learning, another example is as you have like a exit sign, in this case is translating it into French, sortie. I hope I said that right. The neural network has been programmed with all these different words and images, and so it's able to look at the exit in the middle, and it goes, okay, we want to know what that is in French, and it's able to push that out in French, and learn how to do that. And then we have chatbots. I remember when Microsoft first had their little paperclip. Boy, that was like a long time ago. They came up and you would type in there and chat with it. These are growing. It's nice to just be able to ask a question and it comes up and gives you the answer. And instead of it being where you're just doing a search on certain words, it's now able to start linking those words together and form a sentence in that chat box. Types of AI and machine learning. Types of artificial intelligence. This and the next few slides are really important. So one of the types of artificial intelligence is reactive machines. Systems that only react. They don't form memories, they don't have past experiences, they have something that happens to them and they react to it. My washing machine is one of those. If I put a ton of clothes in it and they had all clumped on one side, it automatically adds a weight to recenter it. So that my washing machine is actually a reactive machine working with whatever the load is and keeps it nice, and so when it spins it doesn't go thumping against the side. Limited memory. Another form of artificial intelligence. Systems look into the past. Information is added over a period of time, and information is short-lived. When we're talking about this, and you look at like a neural network that's been programmed to identify cars, it doesn't remember all those pictures. It has no memory as far as the hundreds of pictures you process through it. All it has is, this is the pattern I use to identify cars as the final output for that neural network we looked at. So when they talk about limited memory, this is what they're talking about. They're talking about, I've created this based on all these things, but I'm not going to remember any one specifically. Theory of mind. Systems being able to understand human emotions and how they affect decision making to adjust their behaviors according to their human understanding. This is important because this is our page mark. This is how we know whether it is an artificial intelligence or not. Is it interacting with humans in a way that we can understand? Without that interaction, is just an object. So when we talk about theory of mind, we really understand how it interfaces. That whole, if you're in web development, user experience would be the term I would put in there. So theory of mind would be user experience. How is the whole UI connected together? And one of the final things is, as we get into artificial intelligence, is systems being aware of themselves, understanding their internal states, and predicting other people's feelings and act appropriately. So as artificial intelligence continues to progress, we see ones that are trying to understand, well, what makes people happy? How would they increase our happiness? How would they keep themselves from breaking down if something's broken inside? They have that self-awareness to be able to fix it. And just based on all that information, predicting which action would work the best, what would help people. If I know that you're having a cup of coffee first thing in the morning is what makes you happy, as a robot, I might make you a cup of coffee every morning at the same time to help your life and help you grow. That'd be the self-awareness, is being able to know all those different things. Types of machine learning, and like I said on the last slide, this is very important. This is very important. If you decide to go in and get certified in machine learning or know more about it, these are the three primary types of machine learning. The first one is supervised learning. Systems are able to predict future outcome based on past data. Requires both an input and an output to be given to the model for it to be trained. So in this case, we're looking at anything where you have 100 images of a bicycle, and those 100 images are bicycle. So they're preset. Someone already looked at all 100 images and said, these are pictures of bicycles. And so the computer learns from those, and then it's given another picture, and maybe the next picture is a bicycle, and it says, oh, that resembles all these other bicycles, so it's a bicycle. And the next one's a car, and it says, it's not a bicycle. That would be supervised learning, because we had to train it. We had to supervise it. Unsupervised learning. Systems are able to identify hidden patterns from the input data provided by making the data more readable and organized. The patterns, similarities, or anomalies become more evident. You'll heard the term cluster. How do you cluster things together? Some of these things go together, some of these don't. This is unsupervised, where it can look at an image and start pulling the different pieces of the image out because they aren't the same. All the parts of the human are not the same as a fuzzy tree behind them because it's slightly out of focus, which is not the same as the beach ball. It's unsupervised because we never told it what a beach ball was, we never told it what the human was, and we never told it that those were trees. All we told it was, hey, separate this picture by things that don't match and things that do match and come together. And finally, there's reinforcement learning. Systems are given no training. It learns on the basis of the reward punishment it received for performing its last action. It helps increase the efficiency of a tool function or a program. Reinforced learning, or reinforcement learning, is kind of, you give it a yes or no. Yes, you gave me the right response. No, you didn't. And then it looks at that and says, oh, okay, so based on this data coming in, what I gave you was a wrong response, so next time I'll give you a different one. Comparing machine learning and deep learning. So remember that deep learning is a subcategory of machine learning. So it's one of the many tools. And so we're grouping a ton of machine learning tools all together. Linear regression, k-means clustering. There's all kinds of cool tools out there you can use in machine learning. Enables machines to make decisions on their own based on past data. Enables machines to make decisions with the help of artificial neural networks. So it's doing the same thing, but we're using an artificial neural network as opposed to one of the more traditional machine learning tools. Needs only a small amount of training data. This is very important. When you're talking about machine learning, they're usually not talking about huge amounts of data. We're talking about maybe your spreadsheet from your business and your totals for the end of the year. When you're talking about neural networks, you usually need a large amount of data to train the data. So there's a lot of training involved. If you have under 500 points of data, that's probably not going to go into machine learning. Or maybe you have, like the case of one of the things, 500 points of data and 30 different fields. It starts getting really confusing there in artificial intelligence or machine learning, and the deep learning aspect really shines when you get to that larger data that's really complex. Works well on a low-end systems. So a lot of the machine learning tools out there you can run on your laptop with no problem and do the calculations there. Where with the machine learning, you usually needs a higher end system to work. It takes a lot more processing power to build those neural networks and to train them. It goes through a lot of data. When we're talking about the general machine learning tools, most features need to be identified in advance and manually coded. So there's a lot of human work on here. The machine learns the features from the data it is provided. So again, it's like a magic box. You don't have to know what a tire is. It figures it out for you. The problem is divided into parts and solved individually and then combined. So in machine learning, you usually have all these different tools and use different tools for different parts. And the problem is solved in an end-to-end manner. So you only have one neural network or two neural networks that is bringing the data in and putting it out. It's not going through a lot of different processes to get there. And remember, you can put machine learning and deep learning together. So you don't always have just the deep learning solving the problem. You might have it solving one piece of the puzzle. With regular machine learning and most machine learning tools out there, they take longer to test and understand how they work. And with the deep learning, it's pretty quick. Once you build that neural network, you test it and you know. So we're dealing with very crisp rules, limited resources. You have to really explain how the decision was made when you use most machine learning tools. But when you use the deep learning tool inside the machine learning tools, the system takes care of it based on its own logic and reasoning. And again, it's like a magic black box. You really don't know how it came up with the answer. You just know it came up with the right answer. A glimpse into the future. So a quick glimpse into the future, artificial intelligence, be using it to detecting crimes before they happen, humanoid AI helpers, which we already have a lot of. There'll be more and more. Maybe it'll actually be androids. That'd be cool to have an android that comes and gets stuff out of my fridge for me. Machine learning, increasing efficiency in healthcare. That's really big in all the forms of machine learning. Better marketing techniques. Any of these things, if we get into the sciences, it's just off the scale. Machine learning and artificial intelligence go everywhere. And then the subcategory deep learning, increased personalization. So what's really nice about the deep learning is it's going to start now catering to you. That'll be one of the things we see more and more of. And we'll have more of a hyper-intelligent personal assistant. I'm excited about that.
What are the different types of machine learning algorithms? Machine learning algorithms are broadly classified into three types: the supervised learning, the unsupervised learning, and reinforcement learning. Supervised learning in turn consists of techniques like regression and classification, and unsupervised learning we use techniques like association and clustering. And reinforcement learning is a recently developed technique, and it is very popular in gaming. Some of you must have heard about AlphaGo. So this was developed using reinforcement learning. Primary difference between supervised learning and unsupervised learning. Supervised learning is used when we have historical data and we have labeled data, which means that we know how the data is classified. So we know the classes if we are doing classification, or we know the values when we are doing regression. So if we have historical data with these values, which are known as labels, then we use supervised learning. In case of unsupervised learning, we do not have past labeled data, historical labeled data. So we use techniques like association and clustering to maybe form clusters or new classes maybe, and then we move from there. In case of reinforcement learning, the system learns pretty much from scratch. There is an agent and there is an environment. The agent is given a certain target and it is rewarded when it is moving towards that target, and it is penalized if it is moving in a direction which is not achieving that target. So it's more like a carrot and stick model. So what is the difference between these three types of algorithms? Supervised algorithms or supervised learning algorithms are used when you have a specific target value that you would like to predict. The target could be categorical, having two or more possible outcomes or classes, if you will. That is what is classification. Or the target could be a value which can be measured. And that's where we use regression. Like for example, weather forecasting, you want to find the temperature. Whereas in classification, you want to find out whether this is a fraud or not a fraud. Or if it is email spam, whether it is spam or not spam. So that is a classification example. So if you know, or this is known as labeled information, if you have the labeled information, then you use supervised learning. In case of unsupervised learning, we have input data, but we don't have the labels or what the output is supposed to be. So that is when we use unsupervised learning techniques like clustering and association, and we try to analyze the data. In case of reinforcement learning, it allows the agent to automatically determine the ideal behavior within a specific context. And it has to do this to maximize the performance. Like for example, playing a game. So the agent is told that you need to score the maximum score possible without losing lives. So that is a target that is given to the agent. And it is allowed to learn from scratch, play the game itself multiple times, and slowly it will learn the behavior which will increase the score and keep the lives to the maximum.
If you want to become an AI expert and gain handsome salary packages, look at the wide range of AI ML courses by Simplilearn in collaboration with top universities across the globe. By enrolling in any of these certification programs, you will gain expertise in skills like generative AI, prompt engineering, ChatGPT, explainable AI, machine learning algorithms, supervised and unsupervised learning, model training, and optimization, and there's much more on the list. With hands-on experience in the tools like ChatGPT, DALL-E, Python, OpenCV, and TensorFlow, you will catch the eyes of top recruiters. So what are you waiting for? Hurry up and enroll now. An year of experience is preferred to enroll in these courses. Find the course link in the description box.
When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model. And that's why it'd be multiple linear regression. And finally we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is a statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that, we put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle, a good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from is called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your C coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1, plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values, based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the matplot library. So you have to always import matplot library and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplot library inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000 companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simplilearn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/Simplilearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a :-1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row, that shows that this is the highest corresponding data. That's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter notebook. And what we're bringing in is we're going to bring in the sklearn preprocessing, where we're going to import the label encoder and the one hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there, we're going to take the label coder, and we're going to fit and transform the X, also the third row. So we're going to take that third row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally, we need to do a one hot encoder, which equals one hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have x equals x colon comma 1 colon. All this is doing is removing that one extra column we put in there when we did our one hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit, because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn .linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom when we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's the linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do x train and y train because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, It gives an output, linear regression. It says copy x equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a y_predict variable, and we're going to put in the x_test. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have y_predict equals regressor.predict x_test going in, and this gives us y_predict. Now because I'm in Jupyter inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print y_predict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print y_predict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the r² value, that's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the r² value. And we're looking at the error. So, in the R2 score, we take our y_test versus our y_predict. Y_test is the actual values we're testing. That was the one that was given to us so we know are true. The y_predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if r² value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression. So now that we have a successful linear regression model,
Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis, x is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well. As the number of years are on the lower side, maybe 1 year, 2 years, or 3 years till after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set, saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them, so it can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this where you're trying to find continuous values is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion and this is the ratings for which people did not get promotion, that is a no, and this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not, yes, no, right? So there is nothing in between, and what is the employee's rating, okay? And ratings can be continuous, that is not an issue, but the output is discrete in this case, whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right because it looks like there will be a lot of errors. The root mean square error, if you remember for linear regression, would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to be rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonal should have the maximum numbers. and the others other than diagonals, the cells other than the diagonals should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0 and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are 2 misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and one has been predicted as number 8 and another one has been predicted as number 9. So these are 2 misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, alright, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and
each pixel, whether it is activated or not activated. That is the information available for each pixel. Now, based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall, each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. Right? So whenever we perform any training, we split the data into training and test, so that the training data set is used to train the system. So we pass this probably multiple times and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. Seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes 2 parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the
confusion matrix. Let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images.
There's all kinds of regression models that come out of this. So when we put them side to side, we have our linear regression, which is a predictive number used to predict a dependent output variable based on independent input variable. Accuracy is measured using least squares estimation. So that's where you take, you could also use absolute value. The least squares is more popular. There's reasons for that mathematically and also for computer runtime. But it does give you an accuracy based on the least square estimation. The best fit line is a straight line, and clearly that's not always used in all the regression models. There's a lot of variations on that. The output is a predicted integer value. Again, this is what we're talking about when we talk about linear regression. And we're talking about regression, it means the numbers coming out. Linear usually means we're looking for that line versus a different model. And it's used in business domain, forecasting stocks. It's used as a basis of most predictions with numbers. So if you're looking at a lot of numbers, you're probably looking at a linear regression model. For instance, if you do just the high lows of the stock exchange, and you're going to take a lot more of that if you want to make money off the stock, you'll find that the linear regression model fits probably better than almost any of the other models, even high-end neural networks and all these other different machine learning and AI models, because they're numbers. They're just a straight set of numbers. You have a high value, a low value, volume, that kind of thing. So when you're looking at something that's straight numbers, and are connected in that way, usually you're talking about a linear regression model, and that's where you want to start. A logistic regression model used to classify dependent output variable based on independent input variable. So just like the linear regression model and like all of our machine learning tools, you have your features coming in. And so in this case you might have label, an image or something like that is probably the very popular thing right now, labeling broccoli and vegetables or whatever. Accuracy is measured using maximum likelihood estimation. The best fit is given by a curve, and we saw that when we're talking about linear regression, you definitely are talking about a straight line, although there is other regression models that don't use straight lines. And usually when you're looking at a logistic regression, the math, as you saw, was still kind of a Euclidean line, but it's now got that sigmoid activation, which turns it into a heavily weighted curve. And the output is a binary value between 0 and 1. And it's used for classification. Image processing, as I mentioned, is what people usually think of, although they use it for classification of like a window of things. So you could take a window of stock history and you could generate classifications based on that and separate the data that way. If it's going to be that this particular pattern occurs, it's going to be upward trending or downward trending. In fact, a number of stock traders use that not to tell them how much to bid or what to bid, but they use it as to whether it's worth looking at the stock or not, whether the stock's going to go down or go up. And it's just a 0 or 1. Do I care? Do I even want to look at it? So let's do a demo so you can get a picture of what this looks like in Python code. Let's predict the price at which insurance should be sold to a particular customer based on their medical history. We will also classify on a mushroom dataset to find the poisonous and non-poisonous mushrooms. And when you look at these two data, the first one, we're looking at the price. So the price is a number. So let's predict the price which the insurance should be sold to. And the second one is we're looking at either it's poisonous or it's not poisonous. So first off, before we begin the demo, I'm in the Anaconda Navigator In this one, I've loaded the Python 3.6 and using the Jupyter Notebook. And you can use Jupyter Notebook by itself. You can use the Jupyter Lab, which allows multiple tabs. It's basically the notebook with tabs on it. But the Jupyter Notebook is just fine, and it'll go into Google Chrome, which is what I'm using for my Internet Explorer. And from here we open up new, and you'll see Python 3, and again this is loaded with Python 3.6. And we're doing the linear versus logic regression, or logit. You'll see Logit is one of the names that kind of pops up when you do a search on here. But it is a logic. We're looking at the logistic regression models. And we'll start with the linear regression because it's easy to understand. You draw a line through stuff. And so in programming, we got a lot of stuff to unfold here in our startup as we preload all of our different parts. And let's go ahead and break this up. We have at the beginning import pandas. So this is our data frame. It's just a way of storing the data. Think of when you talk about a data frame, think of a spreadsheet. You have rows and columns. It's a nice way of viewing the data. And then we have, we're going to be bringing in our preprocessing label encoder. I'll show you what that is. When we get down to it, it's easier to see in the data, but there's some data in here like sex. It's male or female, so it's not like an actual number. It's either you're one or the other. That kind of stuff ends up being encoded. That's what this label encoder is right here. We have our test split model. If you're going to build a model, you do not want to use all of the data. You want to use some of the data and then test it to see how good it is. And if it can't have seen the data you're testing on until you're ready to test it on there and see how good it is. And then we have our logistic regression model, our categorical one, and then we have our linear regression model. These are the two, these right here. Let me just clear all that. There we go. These two right here are what this is all about. Logistic versus linear. Is it categorical? Are we looking for a true false, or are we looking for a specific number? And then finally, usually at the very end, we have to take and just ask how accurate is our model. Did it work? If you're trying to predict something, in this case we're going to be doing insurance costs. How close to the insurance cost does it measure that we expect it to be? You know, if you're an insurance company, you don't want to promise to pay everybody's medical bill and not be able to. And in the case of the mushrooms, you probably want to know just how much at risk you are for following this model as far as whether you're going to eat a poisonous mushroom and die or not. So we'll look at both of those, and we'll talk a little bit more about the shortcomings and the value of these different processes. So let's go ahead and run this. This is loaded the data set on here, and then because we're in Jupyter Notebook, I don't have to put the print on there. We just do data set, and it prints out all the different data on here, and you can see here for our insurance, because that's what we're starting with, we're loading that with our pandas, and it prints it in a nice format where you can see the age, sex, body mass index, number of children, smoker. So this might be something that the insurance company gets from the doctor. It says, hey, this is what we need to know to give you a quote for what we're going to charge you for your insurance. And you can see that it has 1,338 rows and 7 columns. You can count the columns, 1, 2, 3, 4, 5, 6, 7. So there's 7 columns on here. And the column we're really interested in is charges. I want to know what the charges are going to be. What can I expect? Not a very good arrow drawn. What to expect them to charge on there. So is this going to be, is this person going to cost me $16,884, or is this person only going to cost me $3,866? How do we guess that so that we can guess what the minimal charge is for their insurance? And then there's one other thing you really need to notice on this data. And I mentioned it before, but I'm going to mention it again because pre-processing data is so much of the work in data science. sex. Well, how do you deal with female versus male? Are you a smoker? Yes or no? What does that mean? Region. How do you look at region? It's not a number. How do you draw a line between southwest and northwest? You know, they're objects. It's either your southwest or your northwest. It's not like I'm southwest. I guess you could do longitude and latitude, but the data doesn't come in like that. It comes in as true, false, or whatever. You know, it's either your southwest or your northwest. So we need to do a little bit of pre-processing of the data on here to make this work. Oops, there we go. Okay, so let's take a look and see what we're doing with pre-processing. And again, this is really where you spend a lot of time with data science, is trying to understand how and why you need to do that. And so we're going to do, you'll see right up here, label. And then we're going to do a label encoder, one of the modules we brought in. So this is sklearn's label encoder. I like the fact that it's all pretty much automated, but if you're doing a lot of work with the label encoder, you should start to understand how that fits. And then we have label.fit right here, where we're going to go ahead and do the dataset .sex.drop duplicates. And then for dataset sex, we're going to do the label transform the dataset sex. And so we're looking right here at male or female. And so it usually just converts it to a 0 or 1 because there's only 2 choices on here. Same thing with the smoker. It's 0 or 1, so we're going to transfer the change the smoker 0 or 1 on this. And then finally we did region down here. Region does it a little bit different. We'll take a look at that. And I think in this case it's probably going to do it because we did it on this label transform. With this particular setup, it gives each region a number, like 0, 1, 2, 3. So let's go ahead and take a look and see what that looks like. Go and run this. And you can see that our new data set has age, that's still a number. Sex is 0 or 1. So 0 is female, 1 is male. Number of children, we left that alone. Smoker, 1 or 0. It says no or yes on there. We actually just do 1 for no, 0 or no. Yeah, 1 for no. I'm not sure how it organized them, but it turns the smoker into 0 or 1, yes or no. And then region, it did this as 0, 1, 2, 3. So it's 3 regions. Now, a lot of times when you're working with data science and you're dealing with regions or even word analysis, instead of doing one column and labeling it 0, 1, 2, 3, a lot of times you increase your features. And so you would have region northwest would be 1 column, yes or no. Region southwest would be 1 column, yes or no. True, 0, 1. But for this particular setup, this will work just fine on here. Now that we spent all that time getting it set up, here's the fun part. Here's the part where we're actually using our setup on this, and you'll see right here we have our Y linear regression dataset drop the charges, because that's what we want to predict. And so our X linear data set drop the charges, because that's what we're going to predict. We're predicting charges right here. So we don't want that as our input for our features. And our Y output is charges. That's what we want to guess. We want to guess what the charges are. And then what we talked about earlier is we don't want to do all the data at once. So we're going to take 0.3, means 30%. We're going to take 30% of our data, and it's going to be as the testing site. So here's our Y test and our X test down there. And so that part, our model will never see it until we're ready to test to see how good it is. And then of course right here you'll see our training set, and this is what we're going to train it. We're going to train it on 70% of the data. And then finally the big ones, this is where all the magic happens. This is where we're going to create our magic setup, and that is right here. Our linear model, we're going to set it equal to the linear regression model, and then we're going to fit the data on here. And then at this point, I always like to pull up, if you're working with a new model, it's good to see where it comes from. And this comes from the scikit-learn, and this is the sklearn linear model, linear regression that we imported earlier. And you can see they have different parameters. the basic parameter works great if you're dealing with just numbers. I mentioned that earlier with stock, high-lows. This model will do as good as any other model out there if you're doing just the very basic high-lows and looking for a linear fit, a regression model fit. And one of the things when I'm looking at this is I look for methods. And you'll see here's our fit that we're using right now, and here's our predict. And we'll actually do a little bit in the middle here as far as looking at some of the parameters hidden behind it, the math that we talked about earlier. And so when we go in this, we go ahead and run this, you'll see it loads the linear regression model and just has a nice output that says, hey, I loaded the linear regression model. And then the second part is we did the fit. And so this model is now trained. Our linear model is now trained on the training data. And so one of the things we can look at is the for IDX and column name and enumerate X linear trained columns. Kind of an interesting thing. This prints out the coefficients. So when you're looking at the back end of the data, you remember we had that formula, bxx1 plus bxx2 plus the intercept, and so forth. These are the actual coefficients that are in here. This is what it's actually multiplying these numbers by. And you can see like region gets a minus value, so when it adds it up, I guess region. You can read a lot into these numbers. It gets very complicated. There's ways to mess with them. If you're doing a basic linear regression model, you usually don't look at them too closely. But you might start looking in these and saying, hey, you know what, smoker, look how smoker impacts the cost. It's just massive. So this is a flag that, hey, the value of the smoker really affects this model. And then you can see here where the body mass index, so somebody who is overweight is probably less healthy and more likely to have cost money. And then, of course, age is a factor. And then you can see down here we have sex is then a factor also. And it changes as you go in there. Negative number, it probably has its own meaning on there. Again, it gets really complicated when you dig into the workings and how the linear model works on that. And so we can also look at the intercept. This is just kind of fun. So it starts at this negative number and then adds all these numbers to it. That's all that means. That's our intercept on there. And that fits the data we have on that. And so you can see right here, we can go back and, oops, give me just a second. There we go. We can go ahead and predict the unknown data and we can print that out. And if you're going to create a model to predict something, we'll go ahead and predict it. Here's our Y prediction value, linear model predict. And then we'll go ahead and create a new data frame. In this case from our X linear test group. We'll go ahead and put the cost back into this data frame. And then the predicted cost, we're going to make that equal to our Y prediction. And so when we pull this up, you can see here that we have the actual cost and what we predicted the cost is going to be. There's a lot of ways to measure the accuracy on there, but we're going to go ahead and jump into our mushroom data. And so in this, you can see here we've run our basic model. We've built our coefficients. You can see the intercept, the back end. You can see how we're generating a number here. Now with mushrooms, we want a yes or no. We want to know whether we can eat them or not. And so here's our mushroom file. We're going to go ahead and run this and take a look at the data. And again, you can ask for a copy of this file. Send a note over to simplilearn.com. And you can see here that we have a class, the cap shape, cap surface, and so forth. So there's a lot of feature. In fact, there's 23 different columns in here going across. And when you look at this, I'm not even sure what these particular, like PEE, PE, I don't even know what the class is on this. I'm going to guess by the notes that the class is poisonous or edible. So if you remember before, we had to do a little pre-coding on our data. Same thing with here. We have our cap shape, which is B or X or K. We have cap color. These really aren't numbers, so it's really hard to do anything with just a single number. So we need to go ahead and turn those into a label encoder, which again, there's a lot of different encoders. With this particular label encoder, it's just switching it to 0, 1, 2, 3 and giving it an integer value. In fact, if you look at all the columns, all of our columns are labels. And so we're just going to go ahead and loop through all the columns in the data, and we're going to transform it into a label encoder. And so when we run this, you can see how this gets shifted from XBXXK to 0, 1, 2, 3, 4, 5, or whatever it is. Class is 0, 1, 1 being poisonous, 0 looks like it's editable, and so forth on here. So we're just encoding it. If you were doing this project, depending on the results, you might encode it differently. Like I mentioned earlier, you might actually increase the number of features as opposed to labeling it 0, 1, 2, 3, 4, 5. In this particular example, it's not going to make that big of a difference how we encode it. And then, of course, we're looking for the class, whether it's poisonous or edible. So we're going to drop the class in our X logistics model, and we're going to create our Y logistics model is based on that class. So here's our XY. And just like we did before, we're going to go ahead and split it using 30% for test, 70% to program the model on here. And that's right here. Whoops, there we go. There's our train and test. And then you'll see here on this next setup, this is where we create our model. All the magic happens right here. We go ahead and create a logistics model. I've upped the max iterations. If you don't change this for this particular problem, you'll get a warning that says this has not converged. Because that's what it does, is it goes through the math and it goes, hey, can we minimize the error? And it keeps finding a lower and lower error, and it still is changing that number. So that means it hasn't converged yet. It hasn't found the lowest amount of error it can. And the default is 100. There's a lot of settings in here. So when we go in here to, let me pull that up from the sklearn. So we pull that up from the sklearn model. You can see here we have our logistic. It has our different settings on here that you can mess with. Most of these work pretty solid on this particular setup, so you don't usually mess a lot. Usually I find myself adjusting the iteration, and I'll get that warning and then increase the iteration on there. And just like the other model, you can go, just like you did with the other model, we can scroll down here and look for our methods. And you can see there's a lot of methods available on here. And certainly there's a lot of different things you can do with it. But the most basic thing we do is we fit our model, make sure it's set right, and then we actually predict something with it. So those are the two main things we're going to be looking at on this model, is fitting and predicting. There's a lot of cool things you can do that are more advanced, but for the most part, these are the two which I use when I'm going into one of these models and setting them up. So let's go ahead and close out of our sklearn setup on there. And we'll go ahead and run this. And you can see here it's now loaded this up there. We now have a logistic model. And we've gone ahead and done a predict here also, just like I was showing you earlier. So here's where we're actually predicting the data. So we've done our first two lines of code as we create the model. We fit the model to our training data. And then we go ahead and predict for our test data. Now, in the previous model, we didn't dive into the test score. I think I just showed you a graph, and we can go in there, and there's a lot of tools to do this. We're going to look at the model score on this one. And let me just go ahead and run the model score. And it says that it's pretty accurate. We're getting a roughly 95% accuracy. Wow, that's good. 95% accuracy. 95% accuracy might be good for a lot of things. But when you look at something as far as whether you're going to pick a mushroom on the side of the trail and eat it, we might want to look at the confusion matrix. And for that, we're going to put in our Y logistic test, the actual values of edible and unedible, and we're going to put in our prediction value. And if you remember on here, let's see, I believe it's poisonous was 1, 0 is edible. So let's go ahead and run that, 0, 1. 0 is good. So here is a confusion matrix, and this is, if you're not familiar with these, we have true, 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 false, true, false, false, false. So it says out of the edible mushrooms, we correctly labeled 1,201 mushrooms edible that were edible. And we correctly measured 1,113 poisonous mushrooms as poisonous. But here's the kicker. I labeled 56 edible mushrooms as being poisonous. Well, that's not too big of a deal. We just don't eat them. But I measured 68 mushrooms as being edible that were poisonous. So probably not the best choice to use this model to predict whether you're going to eat a mushroom or not. And you'd want to dig a little deeper before you start picking mushrooms off the side of the trail. So a little warning there when you're looking at any of these data models, looking at the error and how that error fits in with what domain you're in. Domain in this case being edible mushrooms. Be a little careful. Make sure that you're looking at them correctly. So we've looked at edible or not edible. We've looked at regression model as far as the end values, what's going to be the cost and what our predicted cost is, so we can start figuring out how much to charge these people for their insurance. And so these really are the fundamentals of data science. When you pull them together, when I say data science, I'm talking about your machine learning code. And hopefully you got a little bit out of here. Again, you can contact our Simplilearn team and get a copy of these files or get more information on this.
If you want to become an AI expert and gain handsome salary packages, look at the wide range of AI ML courses by Simplilearn in collaboration with top universities across the globe. By enrolling in any of these certification programs, you will gain expertise in skills like generative AI, prompt engineering, ChatGPT, explainable AI, machine learning algorithms, supervised and unsupervised learning, model training, and optimization, and there's much more on the list. With hands-on experience in the tools like ChatGPT, DALL-E, Python, OpenCV, and TensorFlow, you will catch the eyes of top recruiters. So what are you waiting for? Hurry up and enroll now. An year of experience is preferred to enroll in these courses. Find the course link in the description box.
A confusion matrix represents a table layout of the different outcomes of prediction and results of a classification problem and helps visualize its outcomes. And so you see here we have our simple chart, predicted and actual. The confusion matrix helps us identify the correct predictions of a model for different individual classes, as well as the errors. So you'll see here that the values predicted by our classifier are along the rows. This is what we're going to guess it is, or our model is guessing what this is based on its training. So we've already trained the model to guess whether it's spam or not spam or whatever it is you're working on. And then the actual values of our data set are along the columns. So this is the actual value it's supposed to be. People who can speak English will be classified as positives. So, because they have remember 0 or 1. Do you speak English? Yes, no. And you could extend this that they might have, do you speak French? Do you speak whatever languages? And so you might have a whole lot of classifiers that you would look at each one of these. People who cannot speak English will be classified as negatives. So there'll be a 0. So, 0 ones. The number of times our actual positive values are equal to predicted positive values gives us true positive, TP. The number of times our actual negative values are equal to predictive negative values gives us true negative, TN. The number of times our model wrongly predicts negative values as positives gives us a false positive, FP. And you'll see when you're working with these a lot, memorizing that it's false positive, you can easily figure out what that is, and pretty soon you're just looking at the FP or the TP, depending on what you're working on. And the number of times our model wrongly predicts positive values as negatives gives us a false negative, FP. Now, I'm going to do a quick step out here. Let's say you're working in the medical and we're talking about cancer. Do you really want a bunch of false negatives? You want 0 under false negative. So when we look at this confusion matrix, if you have 5% false positives and 5% false negatives, it'd be much better to even have 20% false positives because they go in and test it and 0 false negatives. The same might be true If you're working on, say, a car driving, is this a safe place for the car to go? Well, you really don't want any false positives. Yes, this is safe right over the cliff. So again, when you're working on the project or whatever it is you're working on, this chart suddenly has huge value. We were talking about spam email. How many important emails, say from your banking overdraft charge coming in, that you want to be a true false negative? You don't want it to go in the spam folder. Likewise, you want to get as much of the spam out of there, but you don't want to miss anything really important. Confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics: accuracy, precision, recall, and F1 score. The F1 score is the one I usually hear the most, and accuracy is usually what you put on your chart when you're sending in front of the shareholders. How accurate is it? People understand accuracy. F1 score is a little bit more on the math side, and so you got to be a little careful when you're quoting F1 scores in the when you're sitting there with all the shareholders, because a lot of them will just glaze over. So confusion matrix metrics are performance measures which help us find the accuracy of our classifier. There are 4 main metrics. Accuracy. The accuracy is used to find the portion of the correctly classified values. It tells us how often our classifier is right. It is the sum of all true values divided by the total values. And this makes sense. Again, it's one of those things. I don't want to, it depends on what you're looking for. Are you looking for not to miss any spam mails? Are you looking to drive down the road and not run anybody over? Precision is used to calculate the model's ability to classify positive values correctly. It answers the question, when the model predicts a positive value, how often is it right? It is the true positive divided by the total number of predicted positive values. Again, this one depends on what project you're working on, whether this is what you're going to be focusing on. So recall, it is used to calculate the model's ability to predict positive values. How often does the model actually predict the correct positive values? It is the true positives divided by the total number of actual positive values. And then your F1 score. It is the harmonic mean of recall and precision. It is useful when you need to take both precision and recall into account. Consider the following 2 confusion matrices, derived from 2 different classifiers. To figure out which one performs better, we can find the confusion matrix for both of them. And you can see we're back to, does it classify whether they can speak English or non-speaker? They don't know the English language. And so we put these 2 confusion matrices out here. We can go ahead and do the math behind that. We can look up the accuracy. That's the TPN plus TN over the TF plus TN plus FP plus FN. And so we get an accuracy of 0.8125. And we have a precision. If you do the precision, which is your TP, truth positive, over TP plus FP, we get 0.891. And if we do the recall, we'll end up with the 0.825. That's your TP over TP plus FN. And then, of course, your F1 score, which is 2 times precision times recall over precision plus recall. And we get the 0.857. And if we do that with another model, let's say we had 2 different models and we're trying to see which one we want to use for whatever reason, we might go ahead and compute the same things. We have our accuracy, our precision, and our recall, and our F1 score. And as we're looking at this, we might look at the accuracy, because that's really what we're interested in, is how many people are we able to classify as being able to speak English. I really don't want to know I really don't want to know if they're non-speakers. I'd rather miss 10 people speaking English instead of 15. And so you can see from these charts, we probably go with the first model because it does a better job guessing who speaks English and has a higher accuracy, because in this case, that is what we're looking for. So with that, we'll go ahead and pull up a demo so you can see what this looks like in the Python setup in the actual coding. For this, we'll go into Anaconda Navigator. If you're not familiar with Anaconda, it's a really good tool to use as far as doing display and demos. and for quick development. As a data scientist, I just love the package. Now, if you're going to do something heavier lifting, there's some limitations with Anaconda and with the setup, but in general, you can do just about anything in here with your Python. And for this, we'll go with Jupyter Notebook. Jupyter Lab is the same as Jupyter Notebook. You'll see they now have integration with PyCharm if you work in PyCharm. Certainly there's a lot of other integrations that Anaconda has. And we've opened up my Simplilearn files I work on and create a new file called Confusion Matrix Demo. And the first thing we want to note is the data we're working with. Here I've opened it up in a WordPad or Notepad or whatever. You can see it's got a row of headers, comma separated, and then all the data going down below. And then I save this in the same file so I don't have to remember what path I'm working on. Of course, if you have your data separated and you're working with a lot of data, you probably want to put it into a different folder or file depending on what you're doing. And the first thing we want to do is go ahead and import our tools. We're going to use the pandas. That's our data frame. If you haven't had a chance to work with the data frame, please review Pandas data frame and go into Simplilearn. You can pull up the Pandas data frame tutorial on there. And then we're going to use the Scikit framework, which is all denoted as sklearn. And I can just pull this in. You can see here's the scikit-learn.org with the stable version that you can import into your Python. And from here, we're going to use the train test split for splitting our data. We're going to do some pre-processing. We're going to use the Logistic Regression model. That's our actual machine learning model we're using. And then what this particular setup is about is we're going to do the accuracy score, the confusion matrix, and the classifier report. So let me go ahead and run that and bring all that information in. And just like we opened the file, we need to go ahead and load our data in here. So we're going to go ahead and do our pandas read CSV. And then just because we're in Jupyter Notebook, we can just put data to read the data in here. A lot of times we'll actually, let me just do this. I prefer to do just the head of the data, or the top part. And you can see we have age, sex, I'm not sure what CP stands for, test BPS, cholesterol. So a lot of different measurements. If you were in this domain, you'd want to know what all these different measurements mean. I don't want to focus on that too much because when we're talking about data science, a lot of times you have no idea what the data means. If you've ever looked up the breast cancer measurement, it's just a bunch of measurements and numbers. Unless you're a doctor, you're going to have no idea what those measurements mean. But if it's your specialty in your domain, you better know them. So we're going to go ahead and create y, and we're going to set it equal to the target. So here's our target value here, and it's either 1 or 0. So we have a classifier. If you're dealing with 1, 0, true, false, what do you have? You have a classifier. And then our x is going to be everything except for the target. So we're going to go ahead and drop the target. Axis equals 1. Remember, that's columns versus the index or rows. Axis equals 0 would give you an error, but you would drop like row 2. And then we'll go ahead and just print that out so you can see what we're looking at. And here we have y data, x data, and you can see from the x data we have the x head, and we can go ahead and just do print the y head data and run that. So this is all loading the data that we've done so far. If there's a confusion in there, go back and rewind the tape and review it. And then we need to go ahead and split our data into our x-train, x-test, y-train, y-test. And then keep in mind you always want to split the data before we do the scalar. And the reason is that you want the scalar on the training data to be set on the training data or fit to it, but not on the test data. Think of this as being out in the field. It could actually alter your results. So it's always important to make sure whatever you do to the training data or whatever fit you're doing is always done on the training, not on the test. And then we want to go ahead and scale the data. Now, we are working with a linear regression model. And I'll mention this here in a minute when we get to the actual model. So sometimes you don't need to scale it when you're working with linear regression models. It's not going to change your result as much as, say, a neural network where it has a huge impact. But we're going to go ahead and here's our X train, X test, Y train, Y test. We create our scalar. We go ahead and scale. The scale is going to fit the X train. And then we're going to go ahead and take our X train and transform it. And then we also need to take our X test and transform it based on the scale on here, so that our X is now between that nice -1 to 1. And so this is all our pre-data setup. And hopefully all of that looks fairly familiar to you if you've done a number of our other classes and you're up to the setup on here. And then what we want to go ahead and do is create our model. And we're going to use a logistic regression model. And from the logistic regression model, we're going to go ahead and fit our X train and Y train, and then we'll run our predicted value on here. And so let's go ahead and run that. And so now we actually have like our X test and our prediction. So if you remember from our matrix, we're looking for the actual versus the prediction and how those compare. And if I take us back up here, you're going to notice that we imported the accuracy score, the confusion matrix, and the classification report. And there's, of course, our logistic regression, the model we're using for this. And I did mention I was going to talk a little bit about scalar and the regression model. The scalar, on a lot of your regression models, your basic math standard regression models, and I'd have to look it up for the logistic regression model. When you're using a standard regression model, you don't need to scale the data. It's already just built in by the way the model works in most cases. But if you're in a neural network and there's a lot of other different setups, then you really want to take this and fit that on there. And so we can go in and do the accuracy. And this is, if you remember correctly, we were looking at the accuracy with the English speaking. So this is saying our accuracy as to whether this person is, I believe this is the heart data set. It's going to be accurate about 85% of the time as far as whether it's going to predict the person's going to have a heart condition, or the 1 as it comes up with the 0, 1 on there. Which would mean at this point that you have an 85% being correct on telling someone they're extremely high risk for a heart attack kind of thing. And so we want to go ahead and create our confusion matrix. And let me just do that. Of course, the software does everything for us. So we'll go ahead and run this. And you can see right here, here's our 25 correct predictions right here. And if you remember from our slide, I'll just bring this over so it's a nice visual. We have our true positive, false positive. So we had 25 which were true, that it said, hey, this person's going to be high risk at heart. And we had 4 that were still high risk that it said were false. So out of these 25 people, or out of these 29 people, and that makes sense because you have 0.85, out of 29 people, it was correct on 25 of them. And so here's our accuracy score. We were just looking at that. Our accuracy is your true positive and your true negative over all of them. So how true is it? And there was our accuracy coming up here, 0.85. And then we have our nice matrix generated from that. And you can see right here is a similar matrix we had going from the slide. And this should start asking questions at this point. So if you're in a board meeting or you're working with this, you really want to start looking at this data here and saying, well, is this good enough? Is this number of people, and hopefully you'd have a much larger data set, is my confusion matrix showing for the true positive and false positive, is that acceptable for what we're doing? And of course, if you're going to put together whatever data you're putting out, you might want to separate the true negative, false positive, false negative, true positive. And you can simply do that by doing the confusion matrix. And then, of course, the Ravel part lets you set that up. So you can just split that right up into a nice tuple. And the final thing we want to show you here in the coding on this part is the confusion matrix metrics. And so we can come in here and just use the matrix equals classification report, the y-test and the predict. And then we're going to take that classification report and go ahead and print that out. And you can see here it does a nice job giving you your accuracy, your micro average, your weighted average, you have your precision, your recall, your F1 score, and your support all in one window, so you can start looking at this data and saying, oh, okay, our precision's at 0.83, 0.87 for getting a positive, and 0.83 for the negative side for a 0. And we start talking about whether this is a valid information or not to use. And when we're looking at a heart attack prediction, we're only looking at one aspect. What's the chances of this person having a heart attack or not? You might have something where we went back to the languages. Maybe you also want to know whether they speak English or Hindi or French. And you can see right here that we can now take our confusion matrix and just expand it as big as we need to, depending on how many different classifiers we're working on.
What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the two different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy, E1 from the top, and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has two or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with the gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals, and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy, and the entropy is high in this case. So let's look at a training set, or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like, and how do we split the data? We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is a measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as the condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here. We have to make a couple changes as we go through this first part of the import. The first thing we bring in is numpy as np. That's very standard when we're dealing with mathematics, especially with very complicated machine learning tools. You almost always see the numpy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file because it's a comma separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or OpenOffice Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in x equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database, so it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And it's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y test, that's the one we ran the predict on, and then we put in our y predict en, that's the answers we got, and we're just going to multiply that by 100, because this is just going to give us an answer as a decimal, and we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, and we're going to create a data set 1 and a data set 2. We just split it in 2. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far, we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work? So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, there's very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step, which is loading the different modules into Python, and let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there. And let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets, import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble, import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. We're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter Notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25% we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans. And let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a panda thing, the df columns, and we know the first 4 of them, 0, 1, 2, 3, that'd be the first 4, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first 4. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What is factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this just like when we were up here and I typed in y and it printed out y instead of print y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see in jobs equals 2. You can see the random state equals 0. Those are the two that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have, we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today, though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the setosa, the virginica, and the versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal length, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, setosa, virginica, and versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for setosa. It predicts a 0 for virginica, and it predicts a 0 for versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predictTestFeatures. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25 just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter notebook, I can do a Control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names. And we're going to run the prediction. And we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this. And this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets. And I could actually create data, maybe let's just do 2 flowers. So maybe I'm processing more data coming in. And we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as versicolor and versicolor. Not surprising since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. And let's just go ahead and take a look at the key takeaways with today's tutorial.
If you want to become an AI expert and gain handsome salary packages, look at the wide range of AI ML courses by Simplilearn in collaboration with top universities across the globe. By enrolling in any of these certification programs, you will gain expertise in skills like generative AI, prompt engineering, ChatGPT, explainable AI, machine learning algorithms, supervised and unsupervised learning, model training, and optimization, and there's much more on the list. With hands-on experience in the tools like ChatGPT, DALL-E, Python, OpenCV, and TensorFlow, you will catch the eyes of top recruiters. So what are you waiting for? Hurry up and enroll now. An year of experience is preferred to enroll in these courses. Find the course link in the description box.
By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values, our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those 2 characteristics. Now tell me if it is a cat or a dog. An odd question. Usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN Classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or it's not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there. I said we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of k is a process called parameter tuning and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where you might get into a gig of data if it's really clean, doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import numpy as NP. Pandas is the pandas data frame, and numpy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our numpy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data just to see how good it is. Preprocessing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results. So we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put it in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, you know, the dataset 1 head, dataset 2 head, it only prints out the last one. So I always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those, you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do a direct. There's also one that you look for your NAN. A lot of different options in here. But the NAN, numpy NAN is what that stands for, is none. It doesn't exist. So the first thing we're doing here is we're replacing the 0 with a numpy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column .mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NAN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value or those missing values out of the equation. Let's go ahead and take this and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you want to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle. Because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set we want to look at the I location and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far we haven't had any printout other than to look at the data. But that is, a lot of this is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there, but the actual running of our KNN, we need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using K-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take 1 away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the K-neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not. And we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean is the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score, and finally accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED, predicted across the top, and actual going down. Actual. It's always hard to write in here, actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have the and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and find out why support vector machine. So in this example, last week, my son and I visited a fruit shop. Dad, is that an apple or a strawberry? So the question comes up, what fruit did I just pick up from the fruit stand? After a couple of seconds, you could figure out that it was a strawberry. So let's take this model a step further, and let's, why not build a model which can predict an unknown data? And in this, we're going to be looking at some sweet strawberries or crispy apples. We want it to be able to label those two and decide what the fruit is. And we do that by having data already put in. So we already have a bunch of strawberries, we know our strawberries, and they're already labeled as such. We already have a bunch of apples, we know our apples and are labeled as such. Then once we train our model, that model then can be given the new data, and the new data is this image. In this case, you can see a question mark on it, and it comes through and goes, it's a strawberry. In this case, we're using the support vector machine model. SVM is a supervised learning method that looks at data and sorts it into one of two categories. And in this case, we're sorting the strawberry into the strawberry side. At this point, you should be asking the question, how does the prediction work? Before we dig into an example with numbers, let's apply this to our fruit scenario. We have our support vector machine. We've taken it and we've taken labeled sample of data, strawberries and apples, and we draw a line down the middle between the two groups. This split now allows us to take new data, in this case an apple and a strawberry, and place them in the appropriate group based on which side of the line they fall in. And that way we can predict the unknown. As colorful and tasty as the fruit example is, let's take a look at another example with some numbers involved, and we can take a closer look at how the math works. In this example, we're going to be classifying men and women, and we're going to start with a set of people with a different height and a different weight. And to make this work, we'll have to have a sample data set of female, where we have their height and weight, 174, 65, 174, 88, and so on. And we'll need a sample data set of the male. They have a height 179, 90, 180 to 80, and so on. Let's go ahead and put this on a graph so we have a nice visual. So you can see here we have two groups based on the height versus the weight. And on the left side, we're going to have the women. On the right side, we're going to have the men. Now, if we're going to create a classifier, let's add a new data point and figure out if it's male or female. So before we can do that, we need to split our data first. We can split our data by choosing any of these lines. In this case, we draw in two lines through the data in the middle that separates the men from the women. But to predict the gender of a new data point, we should split the data in the best possible way. And we say the best possible way because this line has a maximum space that separates the two classes. Here you can see there's a clear split between the two different classes, and in this one there's not so much a clear split. This doesn't have the maximum space that separates the two. That is why this line best splits the data. We don't want to just do this by eyeballing it. And before we go further, we need to add some technical terms to this. We can also say that the distance between the points in the line should be as far as possible. In technical terms, we can say the distance between the support vector and the hyperplane should be as far as possible. And this is where the support vectors are the extreme points in the data set. And if you look at this data set, they have circled 2 points which seem to be right on the outskirts of the women and one on the outskirts of the men. And hyperplane has a maximum distance to the support vectors of any class. Now you'll see the line down the middle, and we call this the hyperplane because when you're dealing with multiple dimensions, it's really not just a line but a plane of intersections. And you can see here where the support vectors have been drawn in dashed lines. The math behind this is very simple. We take d plus, the shortest distance to the closest positive point, which would be on the men's side, and d minus is the shortest distance to the closest negative point, which is on the women's side. The sum of d plus and d minus is called the distance margin, or the distance between the two support vectors that are shown in the dashed lines. And then, by finding the largest distance margin, we can get the optimal hyperplane. Once we've created an optimal hyperplane, we can easily see which side the new data fits in. And based on the hyperplane, we can say the new data point belongs to the male gender. Hopefully that's clear how that works on a visual level. As a data scientist, you should also be asking what happens if the hyperplane is not optimal. If we select a hyperplane having low margin, then there is a high chance of misclassification. This particular SVM model, the one we discussed so far, is also called or referred to as the LSVM. So far so clear, but a question should be coming up. We have our sample data set, but instead of looking like this, what if it looked like this, where we have two sets of data, but one of them occurs in the middle of another set? You can see here where we have the blue and the yellow, and then blue again on the other side of our data line. In this data set, we can't use a hyperplane. So when you see data like this, it's necessary to move away from a 1D view of the data to a two-dimensional view of the data. And for the transformation, we use what's called a kernel function. The kernel function will take the 1D input and transfer it to a two-dimensional output. As you can see in this picture here, the 1D when transferred to a two-dimensional makes it very easy to draw a line between the two data sets. What if we make it even more complicated? How do we perform an SVM for this type of data set? Here you can see we have a two-dimensional data set where the data is in the middle surrounded by the green data on the outside. In this case, we're going to segregate the two classes. We have our sample data set, and if you draw a line through, it's obviously not an optimal hyperplane in there. So to do that, we need to transfer the 2D to a 3D array. And when you translate it into a three-dimensional array using the kernel, you can see where you can place a hyperplane right through it and easily split the data. Before we start looking at a programming example and dive into the script, let's look at the advantage of the support vector machine. We'll start with high-dimensional input space, or sometimes referred to as the curse of dimensionality. We looked at earlier 1 dimension, 2 dimension, 3 dimension. When you get to 1,000 dimensions, a lot of problems start occurring with most algorithms that have to be adjusted for. The SVM automatically does that in high dimensional space. One high dimensional space that we work on is sparse document vectors. This is where we tokenize the words in documents so we can run our machine learning algorithms over them. I've seen ones get as high as 2.4 million different tokens. That's a lot of vectors to look at. And finally, finally, we have regularization parameter. The regularization parameter, or lambda, is a parameter that helps figure out whether we're going to have a bias or overfitting of the data, whether it's going to be overfitted to a very specific instance or it's going to be biased to a high or low value. With the SVM, it naturally avoids the overfitting and bias problems that we see in many other algorithms. These three advantages of the support vector machine make it a very powerful tool to add to your repertoire of machine learning tools. Now, we did promise you a use case study where we're actually going to dive into some Python programming. And so we're going to go into a problem statement and start off with the zoo. So in the zoo example, we have family members going to the zoo and we have the young child going, "Dad, is that a group of crocodiles or alligators?" Well, that's hard to differentiate. And zoos are a great place to start looking at science and understanding how things work, especially as a young child. And so we can see the parents sitting here thinking, well, what is the difference between a crocodile and an alligator? Well, one, crocodiles are larger in size, alligators are smaller in size. Snout width, the crocodiles have a narrow snout and alligators have a wider snout. And of course, in the modern day and age, the father is sitting here thinking, how can I turn this into a lesson for my son? And he goes, let a support vector machine segregate the two groups. I don't know if my dad ever told me that, but that would be funny. Now, in this example, we're not going to use actual measurements and data. We're just using that for imagery. And that's very common in a lot of machine learning algorithms and setting them up. But let's roll up our sleeves, and we'll talk about that more in just a moment as we break into our Python script. So here we arrive in our actual coding. And I'm going to move this into a Python editor in just a moment. But let's talk a little bit about what we're going to cover. First, we're going to cover in the code the setup, how to actually create our SVM. And you're going to find that there's only 2 lines of code that actually create it, and the rest of it is done so quick and fast that it's all here on the first page. And we'll show you what that looks like as far as our data, because we're going to create some data. I talked about creating data just a minute ago. And so we'll get into the creating data here, and you'll see this nice correction of our 2 blobs, and we'll go through that in just a second. And then the second part is we're going to take this and we're going to bump it up a notch. We're going to show you what it looks like behind the scenes. But let's start with actually creating our setup. I like to use the Anaconda Jupyter Notebook because it's very easy to use, but you can use any of your favorite Python editors or setups and go in there. But let's go ahead and switch over there and see what that looks like. So here we are in the Anaconda Python Notebook, or Anaconda Jupyter Notebook with Python. We're using Python 3. I believe this is 3.5, but it should be work in any of your 3x versions. And you'd have to look at the sklearn and make sure if you're using a 2x version or an earlier version. Now let's go ahead and put our code in there. And one of the things I like about the Jupyter Notebook is I can go up to View, and I'm going to go ahead and toggle the line numbers on to make it a little bit easier to talk about. And we can even increase the size because this is edited in this case I'm using Google Chrome Explorer, and that's how it opens up for the editor. Although like I said, any editor will work. Now the first step is going to be our imports. And we're going to import 4 different parts. The first 2 I want you to look at are line 1 and line 2 are numpy as np and matplotlibary.pyplot as plt. Now, these are very standardized imports when you're doing work. The first one is the numbers Python. We need that because part of the platform we're using uses that for the numpy array. And I'll talk about that in a minute so you can understand why we want to use a numpy array versus the standard Python array. And normally it's pretty standard setup to use np for numpy. The matplot library is how we're going to view our data. So this has, you do need the NP for the sklearn module, but the matplot library is purely for our use for visualization. And so you really don't need that for the SVM, but we're going to put it there so you have a nice visual aid and we can show you what it looks like. That's really important at the end when you finish everything, so you have a nice display for everybody to look at. And then finally, I'm going to jump one ahead to line number 4. That's the sklearn.datasets.samples generator import make blobs. And I told you that we were going to make up data. And this is a tool that's in the sklearn to make up data. I personally don't want to go to the zoo, get in trouble for jumping over the fence, and probably get eaten by the crocodiles or alligators as I work on measuring their snouts and width and length. Instead, we're just going to make up some data. And that's what that make blobs is. It's a wonderful tool if you're ready to test your setup and you're not sure about what data you're going to put in there. You can create this blob and it makes it real easy to use. And finally, we have our actual SVM, the sklearn import SVM on line 3. So that covers all our imports. We're going to create, remember I used the make blobs to create data. And we're going to create a capital X and a lowercase y equals make blobs in samples equals 40. So we're going to make 40 lines of data. It's going to have 2 centers. with a random state equals 20. So each group's going to have 20 different pieces of data in it. And the way that looks is that we'll have under X an XY plane. So I'll have two numbers under X, and Y will be 0 or 1. That's the two different centers. So we have yes or no, in this case alligator or crocodile. That's what that represents. And then I told you that the actual sklearn, or the SVM, is in 2 lines of code. And we see it right here with CLF equals SVM.svc kernel equals linear, and I set C equal to 1. Although in this example, since we are not regularizing the data, because we want it to be very clear and easy to see, I went ahead, you can set it to 1,000 a lot of times when you're not doing that. But for this thing, linear, because it's a very simple linear example, we only have the 2 dimensions, and it'll be a nice linear hyperplane. Will be a nice linear line instead of a full plane. So we're not dealing with a huge amount of data. And then all we have to do is do clf.fit x, y. And that's it. CLF has been created, and then we're going to go ahead and display it. And I'm going to talk about this display here in just a second, but let me go ahead and run this code. And this is what we've done, is we've created 2 blobs. You'll see the blue on the side and then kind of an orangish on the other side. That's our 2 sets of data. They represent, one represents crocodiles and one represents alligators. And then we have our measurements. In this case we have like the width and length of the snout. And I did say I was going to come up here and talk just a little bit about our plot. And you'll see PLT, that's what we imported. We're going to do a scatter plot. That means we're just putting dots on there. And then look at this notation. I have the capital X, and then in brackets I have a colon, comma, 0. That's from NumPy. If you did that in a regular array, you'll get an error in a Python array. You have to have that in a NumPy array. It turns out that our makeblobs returns a NumPy array. And this notation is great because what it means is the first part is the colon. It means we're going to do all the rows. That's all the data in our blob we created under capital X. And then the second part has a comma, 0. We're only going to take the first value. And then if you notice, we do the same thing, but we're going to take the second value. Remember, we always start with 0 and then 1. So we have column 0 and column 1. And you can look at this as our XY plots. The first one is the X plot, and the second one is the Y plot. So the first one is on the bottom, 0, 2, 4, 6, 8, and 10. And then the second one, X of the 1, is the 4, 5, 6, 7, 8, 9, 10 going up the left-hand side. S equals 30 is just the size of the dot, so we can see them instead of real tiny dots. And then CMap equals plt.cm.paired. And you'll also see the C equals Y. That's the color. We're using 2 colors, 0, 1, and that's why we get the nice blue and the 2 different colors for the alligator and the crocodile. Now you can see here that we did this, the actual fit was done in 2 lines of code. A lot of times there'll be a third line where we regularize the data. We set it between like -1 and 1, and we reshape it. But for this, it's not necessary, and it's also kind of nice because you can actually see what's going on. And then if we wanted to actually run a prediction. Let's take a look and see what that looks like. And to predict some new data, and we'll show this again as we get towards the end of digging in deep, you can simply assign your new data. In this case, I am giving it a width and length 3, 4 and a width and length 5, 6. And note that I put the data as a set of brackets, and then I have the brackets inside. And the reason I do that is because when we're looking at data, it's designed to process a large amount of data coming in. We don't want to just process 1 line at a time. And so in this case, I'm processing 2 lines. And then I'm just going to print, and you'll see clf.predict new data. So the clf and the .predict part is going to give us an answer, and let's see what that looks like. And you'll see 0, 1. So predicted the first one, the 3, 4, is going to be on the one side, and the 5, 6 is going to be on the other side. So one came out as an alligator, and one came out as a crocodile. Now that's a pretty short explanation for the setup, but really we want to dig in and see what's going on behind the scenes. And let's see what that looks like. So the next step is to dig in deep and find out what's going on behind the scenes. And also put that in a nice pretty graph. We're going to spend more work on this than we did actually generating the original model. And you'll see here that we go through a few steps, and I'll move this over to our editor in just a second. We come in, we create our original data. It's exactly identical to the first part, and I'll explain why we redid that and show you how not to redo that. And then we're going to go in there and add in those lines. We're going to see what those lines look like and how to set those up. And finally, we're going to plot all that on here and show it. And you'll get a nice graph with what we saw earlier when we were going through the theory behind this, where it shows the support vectors and the hyperplane. And those are done where you can see the support vectors as the dashed lines and the solid line, which is the hyperplane. Let's get that into our Jupyter notebook. Before I scroll down to a new line, I want you to notice line 13. It has plot show. And we're going to talk about that here in just a second, but let's scroll down to a new line down here, and I'm going to paste that code in. And you'll see that the plot show has moved down below. Let's scroll up a little bit. And if you look at the top here of our new section, 1, 2, 3, and 4 is the same code we had before. And let's go back up here and take a look at that. What is naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing 2 coins. Here we have 2 quarters, and if we look at all the different possibilities of what they can come up as, we get that they can come up as heads, they can come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting 2 heads equals 1/4. You can see on our data set we have 2 heads, and this occurs once out of the 4 possibilities. And then the probability of at least 1 tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting 2 heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with 2 coins it's easy to see, but when you have something more complex you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case the first coin toss will be B and the second coin toss A. This can be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4 or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also a reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the two heads and two tails and head, tail, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like. And then we're going to solve it in Python. And in here, we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Did we have a free delivery, yes or no? On those days, how many people made a purchase and how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now, let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays, there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB. If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all 3 independent variables. Now we can construct the likelihood tables for all 3 of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. And we filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these 3 likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We are actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B being all three categories. Did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29% given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do 2 steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network, or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjust for that. Those formulas are very automatic, and so you can still get a very solid predictability even if you're missing data or you have overlapping data for 2 completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the 2 overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time, so you can walk through it, since we walk through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines in classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, or inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplot library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since this is an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplot library inline. And then we're going to import NumPy as NP. That's NumPy, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplot library.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of pyplot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 newsgroups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 newsgroups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.target names. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this newsgroup. And it's called Fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 newsgroups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 newsgroups, subset equals test, and categories equals categories. And let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58 in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes, pretty easy to understand that, where that comes from. And then finally we have the sklearn pipeline import make pipeline. Now the make pipeline is just a cool piece of code because we're going to take the information we get from the tf-idf vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the TF-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights, from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So, make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here from sklearn metrics import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborn, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS or the seaborn sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does, is you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predict s. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now, note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF, IDF vectorizer. We threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF, IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model.
So first we will import some major libraries of Python. So here I will write import pandas as pd and import numpy as np. Then import cborn as sns. Okay. Then import sklearn dot model selection import train underscore test underscore split. Before that I will import matplotlib dot pyplot as plt. Okay, then I will write here from sklearn dot matrix import accuracy score, then from sklearn dot matrix import classification to report, and import re, then import string. Okay, then press enter. So it is saying, okay, here I have to write from. Everything seems good. Loading. Let's see. Okay, till then, NumPy is a Python library used for working with arrays. It also has function for working with the domain of linear algebra and matrices. It is an open source project and you can use it freely. NumPy stands for Numerical Python. Pandas. So Panda is a software library written for Python programming language for data manipulation and analysis. In particular, it offers data structure and operation for manipulating numerical tables and time series. Then, Seaborn. An open source Python library based on Matplotlib is called Seaborn. It is utilized for data exploration and data visualization. With data frames and the Pandas library, Seaborn functions with ease. Then Matplotlib. For Python and its numerical extension NumPy, Matplotlib is a cross-platform for the data visualization and graphical charting package. As a result, it presents a strong open source suitable for MATLAB. The APIs for Matplotlib allow programmers to incorporate graphs into GUI applications. Then this train test split. We may build our training data and the test data with the aid of sklearn train test split function. This is so because the original dataset often serves as both the training data and the test data. Starting with a single dataset, we divide it into two datasets to obtain the information needed to create a model, like hone and test. Accuracy score. The accuracy score is used to gauge the model's effectiveness by calculating the ratio of total true positive to total true negative across all the model prediction. This RE, regular expression. The functions in the model allow you to determine whether a given text fits a given regular expression or not, which is known as RE. Okay, then string. A collection of letters, words, or other characters is called a string. It is one of the basic data structure that serves as the foundation of manipulating data. The str class is a built-in string class in Python. Because Python strings are immutable, they cannot be modified after they have been formed. Okay, so now let's import the dataset. We will be going to import two datasets, one for the fake news and one for the true news, or you can say not fake news. Okay, so I will write here ef underscore fake equals to pd dot read underscore csv, or what can I say, df fake. Okay, data underscore fake. Okay, then fake dot csv. You can download this dataset from the description box below. Then data dot true equals to pd dot read underscore csv. Sorry, csv. Then fake news. Sorry, true. True dot csv. Okay. Then press enter. So these are the two datasets. You can download these datasets from the description box below. So let's see the board dataset. Okay. Then I will write here data underscore fake dot head. So this is the fake data. Okay. Then data underscore true dot head. and this is the true data. Okay, this is not fake. So if you want to see your top 5 rows of the particular data set, you can use head. And if you want to see the last 5 rows of the data set, you can use tail instead of head. Okay. So let me give some space for the better visual. So now we will insert column class as a target feature. Okay. Then I will write here data underscore fake class equals to 0. Then data underscore true and class equals to 1. Okay. Then I will write here data underscore fake dot shape and data underscore true dot shape. Okay. Then press enter. So the shape method returns the shape of an array. The shape is a tuple of integers. These numbers represent the length of the corresponding array dimension. In other words, a tuple containing the quantities of entries on each axis is an array shape dimension. So what's the meaning of shape? In the fake world, in this dataset, we have 2, 3, 4, 8, 1 rows and 5 columns. And in this dataset, true, we have 2, 1, 4, 1, 7 rows and 5 columns. Okay, so these are the rows, column for the particular dataset. So now let's move and let's remove the last 10 rows for the manual testing. Okay, then I will write here data underscore fake underscore manual testing equals to data underscore fake dot tail. For the last 10 rows, I have to write here 10. Okay, so for I in range 2, 3, 4, 8, 1, sorry 0, comma 2, 3, 4, 7, 0, comma -1. Okay, then df underscore not df data underscore fake dot drop 1. Yeah, instead of 1 I can write here I, comma axis equals to 0, in place equals to true. Then data not here data underscore same I will copy from here and I will paste it here and I will make the particular changes. So here I can write true, here I can write true. Okay, then I have to change a number 2 1 4 1 6. Write 2 1 4 0 6 -1. Same. So press enter. X is equals to 0. Valid syntax. Maybe you mean 00 or show of this. Okay, we will put here double equals. where I'm putting this. Fake dot drop ix is equal to 0. अच्छा, in place. Okay. Here also write equals to and equals to. Yeah. So okay, axis is not defined. Now it's working. So let me see now. Data underscore fake dot shape. Okay, and data dot true and data underscore true dot shape. As you can see, 10 rows are deleted from each dataset. Yeah. So I will write here data underscore fake underscore manual testing class equals to 0 and data underscore true underscore manual underscore testing class equals to 1. Okay. Just ignore this warning. And let's see data underscore fake underscore manual testing dot head. As you can see, we have this, and then data dot underscore true underscore manual testing dot head. Done. Okay. This is the true data set. So here I will merge data underscore merge equals to pd dot concat. Concat is used for the concatenation. Data underscore fake data underscore true comma axis equals to 0. Then data underscore merge dot head the top 10 rows. Yeah, as you can see, the data is merged here. Okay. First it will come for the fake news and then with the for the true news. And let's merge true and fake data frames. Okay, we did this, and let's merge the column. Then data dot merge dot columns, or let's see the columns. It is not defined, but I did data underscore merge. These are the columns name, title, text, subject, date, class. Okay, now let's remove those columns which are not required for the further process. So here I will write data underscore or equals to data underscore merge prop title we don't need, then subject we don't need, then so 1. So let's check some null values. It's giving error where because of this. That's good. Then data dot is null dot sum center. So no null values. Okay. Then let's do the random shuffling of the data frames. Okay. For that we have to write here data equals to data dot sample 1. Then data, okay, data dot hat. Okay. Now you can see here the random shuffling is done, and 1 for the true data set and 0 for the fake news one. Okay. Then let me write here data dot reset underscore index place equals to true. Data dot drop comma axis equals to 1, then comma in place equals to true. Okay. Then let me see columns now. Data dot columns. So here we have 2 columns only, rest we have deleted. Okay. So let me see data dot add. Yeah, everything seems good. Let's proceed further and let's create a function to process the text. Okay. For that I will write here but okay, you can use any name text, and text equals to text dot lower. Okay. And text equals to re dot for the substring remove these things from the datas. Okay. So for that I'm writing here comma okay, then text equals to re dot substring comma comma text. Okay. Then I have to write text equals to re dot substring www dot s plus comma, comma text. Okay, then text equals to re dot substring, then oh, comma, okay, then text equals to re dot substring, then percentage as again percentage for re dot escape function, right here string dot punctuation, okay, comma then text, right? Then text equals to re dot substring and n comma text equals to re dot substring right here, and again d, then again, okay, then comma, then again text here, okay, then at the end I have to write here return text. So everything like this these type of special character will be removed from the data set. Okay, let's run this. Let's see. Yeah, so here I will write df, sorry, not df, data, then text equals to data, okay, dot apply to the function name word opt, okay, press enter. Yeah, so now let's define the dependent and independent variables. Okay, x equals to data text and y equals to data class. Okay, then splitting training and testing data. Okay, sorry. So here I will write x underscore train comma x underscore test, then y underscore train comma y underscore test equals to train underscore test underscore split, then x comma y comma test underscore size equals to 0.25. Okay, press enter. So now let's convert text to vectors. For that I have to write here z, it's x, so here I will write from sklearn dot feature extraction dot text import t vectorizer. Okay, then vectorization equals to TFID vectorizer. Okay, then SV underscore train equals to vectorization vectorization dot fit, then transform x underscore train. Okay, then xv underscore test equals to vectorization dot transform x underscore test. Okay, then press enter. So now let's see our first model, logistic regression. So here I will write from sklearn dot linear underscore model. Okay, import logistic regression. Okay. Then lr equals to logistic regression, and I have to write here lr dot fit, then xv dot not dot xv dot train comma xv underscore test. Okay, press enter. Lr dot xv dot train. Okay, here I have to write y train. Okay, then press enter. Will work. So here I will write prediction underscore linear regression equals to lr dot predict xv underscore test. Okay, let's see the accuracy score. For that I have to write lr dot score, then xv underscore test comma y underscore test. Okay, let's see the accuracy. So here as you can see, accuracy is quite good, 98%. Okay, now let's print the classification port y underscore test comma prediction of linear regression. Okay, so this is, you can see, precision score, then f1 score, then support value, accuracy. Okay, so now we will do this same for the decision tree gradient boosting classifier, random forest classifier. Okay, then we will do model testing, then we will predict the score. Okay, so now for the decision tree classification. So for that I have to import from sklearn dot tree import decision tree classifier. Okay, then at the short form I will write here, I will copy it from here, then okay, then I have to write the same as this, so I will copy it from here and here. Let's change linear regression to decision tree classifier. Okay. Then I will write here same. So dt equals to dt dot predict xv underscore test. It's e till loading. It will take time. Okay. Till then, let me write here for the accuracy dt dot score v underscore test comma y. Okay. Let's wait. Okay, let's run the accuracy. So as you can see, accuracy is good than this linear regression. Okay, logistic regression. Okay, so let me show you the. Let me predict print. Okay, so this is the accuracy score. This is the all the report. Yeah. So now let's move for the gradient boosting classifier. Okay, for that I've write from sklearn dot ensemble port gradient boosting classifier. Classifier. I will write here GB equals to, let me copy it from here. Okay. I will give here random underscore state equals to 0. Wait. So I will write here GB dot fit xv underscore train comma y underscore train. Okay, then press enter. Here I will write predict underscore GB equals to GB dot fit, predict xv dot test, not dot underscore test. Till then it's loading, so I will write here for the score. Then I will add GB dot score, then xv underscore test comma y underscore test. Okay, so let's wait. It is running this part. Till then, let me write for the printing this. Okay, it's taking time. Still taking time. What if I will run this? It's not coming because of this. Yeah, it's done now. So you can see the accuracy is not good than decision tree, but yeah, it is also good, 99.4 something. Okay, so now let's check for the last one, random forest. First I will do, for the random forest we have to write from sklearn dot ensemble import random forest classifier. Okay, and here I will write rf equals to, right, I will copy it from here. Then random state equals to 0. Then rf dot fit v underscore train comma y underscore train. Okay, then press enter and predict underscore rc or f equals to rf dot predict sv underscore test. Okay, till then I will write here, it's still loading, it will take time. So till then I will write for the score accuracy score xv underscore test comma y underscore test. Okay, then I will write here till then print classification port and y underscore test comma it will take time little bit. So it run, the accuracy score is 99, it is also good. So now I will write the code for the model testing, so I will get back to you but after writing the code. So I have made two functions, one for the output label and one for the manual testing. Okay, so it will predict the all the from the all models from the repeat. So it will predict the news is fake or not from all the models. Okay, so for that let me write here news was to string put. Okay, then I will write here manual underscore testing. Okay. So here I will, you can add any news from the, you can copy it from the internet or whatever, from wherever you want. So I'm just copying from the internet. Okay, from the Google, the news which is not fake. Okay, I'm adding which is not fake because I already know, I searched on Google, so I'm entering this. So just run it, let's see what is showing. Okay, string input object is not callable. Okay, let me check this first. Okay, I have to give here str only. Yeah, let's check. Okay, I have to add here again the script. Yeah, the manual testing is not defined. Let me see manual testing. Okay, I have to edit something. It is just GB and it is just RF. Still GBC is not defined. Okay, okay. So what I have to do? I have to remove this. Okay, everything seems sorted now. As I said to you, I just copied this news from the internet. I already know the news is not fake, so it is showing not a fake news. Okay. So now what I will do, I will copy one fake news from the internet, and let's see it is detecting it or not. Okay. So let me run this, and let me add the news for this. So all the models are predicting right it is a fake news, or you can add your own script like this is the fake news. Okay. I hope you guys understand till here. So I hope you guys must have understand how to detect a fake news using machine learning. You can copy any news from the internet and you can check it is fake or not.
If you want to become an AI expert and gain handsome salary packages, look at the wide range of AI ML courses by Simplilearn in collaboration with top universities across the globe. By enrolling in any of these certification programs, you will gain expertise in skills like generative AI, prompt engineering, chat GPT, explainable AI, machine learning algorithms, supervised and unsupervised learning, model training, and optimization, and there's much more on the list. With hands on experience in the tools like ChatGPT, DALI, Python, OpenCV, and TensorFlow, you will catch the eyes of top recruiters. So, what are you waiting for? Hurry up and enroll now. An year of experience is preferred to enroll in these courses. Find the course link in the description box.
OpenCV, Open Source Computer Vision Library, is an open source computer vision and machine learning software library. It is written in C++ but has a binding for various programming languages such as Python, Java, MATLAB. OpenCV was designed with the goal of providing a common infrastructure for computer vision applications and to accelerate the use of machine learning perception in commercial product. OpenCV is widely used in a variety of industries, including robotics, automotive, and healthcare. It's supported by a large community of developers, researchers, and users who contribute to its development and provide support to its users. It is supported by a large community of developers, researchers, and users who contribute to its development and provide support to its users. So now let's see what is object detection. Object detection is a computer vision technology that involves identifying and localizing the object of interest within an image or a video. It is a challenging task as it involves not only recognizing the presence of an object but also detecting its precise location and size within the image or video. Object detection algorithm typically use deep learning techniques such as CNN to analyze the image or video for identifying the objects. These algorithms can also determine the boundaries of the object by drawing a bounding box around them. So after understanding what is object detection, now let's move on to the programming part. So this is a kernel, Python kernel. Here we will change this name. So here I will write object detection demo. Okay. So first we will import some major library like OpenCV. So for that we will write import CV2, and the next one is import matplotlib .pyplot as PLT. So why we are writing PLT? Because we can't write again and again matplotlib.pyplot. Okay, it's a long one, so we can write a short form PLT. So yeah, so let's run this. So what is OpenCV? OpenCV is an open source software library for computer vision and machine learning. The OpenCV full form is Open Source Computer Vision Library. It was created to provide a shared infrastructure for application for computer vision and to speed up the use of machine learning perception in consumer products. OpenCV as a BSD licensed software make it simple for companies to use and change the code. Okay, so there are some predefined packages and libraries that make our life simple, and OpenCV is one of them. Second one is Matplotlib. Matplotlib is a easy to use and an amazing visualize library in Python. It is built on NumPy array and designed to work with broader SciPy stack and consists of several plots like line, bar, scatter, histogram, and many others. Okay, so moving forward, we will import our file. Okay, so here I will write config file equals to, this is our file name, ssd underscore
MobileNet V3 large Coco 2014.pb. Okay, so you can find this file on the description box below. Frozen model equals to, I will explain you every single thing. Inference graph dot pb. Okay, so let me run it first. MobileNet. As a name applied, the MobileNet model is designed to use in mobile application and it's TensorFlow first mobile computer vision model. MobileNet used depth-wise separable convolutions. It significantly reduces the numbers of parameters when compared to the network with regular convolutions with the same depth in the nets. This results in the lightweight of the deep neural network. So MobileNet is a class of CNN that was open sourced by Google, and therefore this gives us an excellent starting point for training our classifiers that are insanely small and insanely fast. Okay, so what is this large COCO? This is a dataset, COCO dataset. Like with applications such as object detection, segmentation, and captioning, the COCO dataset is widely understood by the state of the art of neural network. Its versatility and the multi-purpose scene variations serve best to train a computer vision model and benchmark its performance. Okay, so what is COCO? The common object in context is one of the most popular large-scale labeled images dataset available for public use. It represents a handful of objects we encounter on a daily basis and contains image annotations in 80 categories. I will show you the categories I have with over 1.5 million object instances. Okay, so modern day AI driven solutions are still not capable of producing absolute accuracy in result, which comes down to the fact that COCO dataset is a major benchmark for CV to train, test, and polish refined models for faster scaling of the annotation pipeline. On the top of that, the COCO dataset is a supplement to transfer learning where the data used for one model serves as a starting point for the another. So what is frozen inference graph? Like freezing is the process to identify and save all the required graphs like weights and many others in a single file that you can easily use. A typical TensorFlow model contains 4 files and this contains a complete graph. Okay, so forward, let's create one model. Here I will write model equals to cv2.dnn model frozen model and then config file. So here I am giving the parameters, two parameters like frozen model and config file. Let's go here. Yeah, we run it first. Okay, there is error. Return error. Okay, so error is cv2.dnn detection model returned as result with an exception set. The question comes, what is the meaning of detection model or DNN detection model? So this class represents a high-level API for object detection networks. Detection models allows to set parameters for pre-processing input image. Detection model creates net from file and with trained weights and config, sets its processing input, runs forward pass and return the result detection. Okay, moving forward, let's set the class labels. Okay, class labels. File name also labels.txt. I will put this file on the description box below. You can download from there. Open file name. Class labels. Strip. So here I created one array of name class labels. So this is the file name. What I'm doing, I'm putting this label file into this class labels. Okay, so here if I will print class labels, so these are the 80 categories in the Coco dataset. Okay, this person, bicycle, car, motorbike, aeroplane, bus, train, these all are the 80 categories. I will put this file label.txt in the description box below. You can download from there. Okay, fine. So let's print the length of the Coco dataset, or you can see class labels. This is 80. As you can see, I have already told you the length will be 80. So here let's set this some model input size, scaling, mean, and all. So I will write here model dot set input size 320 comma 320. Model dot set input scale 1.0 slash 127.5. Okay, I will explain you, don't worry. Model dot set input mean 127.5 comma 127.5 comma 127.5. Okay, and then model dot set input swap b will be, what is set input size? Okay, so set input size is a size of new frame. It has shape of the new blob less than 0. Okay, so this is the size of the new frame. The second one is set input scale. So set input scale is a scale factor of the value for the frame, or you can say the parameter will be the multiplier of the frame values, or you can say multiplier for the frame values. Okay, so set input mean, so it set the mean value for the frame in which the photo will come, the video will come, or my webcam will come. So it set the mean value for the frame, or the for parameters mean is scalar with the mean values which are subtracted from the channels, you can say. And the last one is set input swap RB. So it set the flag swap RB for the every frame. We don't have to put every time a single frame for a particular image. It will be set the true for the all the images. Okay, so parameters will be swap RB flag, which indicates the swap first and the last channels. So moving forward, we will port one image. Read boy.jpg dot I am show. So this is the size of 320 by 320. Okay, so first thing is you can download this the random picture from the Google. I took from Google itself. So now what we will do, we will set the class index, the confidence value, the B box. B box is the boundary box which I will create for that particular person, cycle, motorbike, and the car. Okay, B equals to model get the confidence threshold. Threshold is used for if my model will confirm it's the particular image which is detecting is correct, it will print the name. Okay, so let me print
class index is coming 1 2 3 4. Okay, so 1 means person, 2 means bicycle, 3 means car, and 4 means motorbike. This is the class index for particular label. What I will do, I will print the boxes font scale equals to 3 and the font equals to cv2 dot font Hershey plain for class index and the confidence and the boxes and x dot pattern confidence pattern box, the boundary box. Okay, then I will write here cv2 dot rectangle to make the rectangle, set the image and the boxes 5 comma 0 comma 0. This is the color of the box and this will be the thickness. Okay, then I will write cv2 dot put text image, then class labels. I will write class index -1 because always index start with 0, that's why, and the boxes 0 and comma boxes 1 body. Okay, font comma scale so font scale color equals to, this will be the text color 0 comma 255 comma 0 and the thickness so 3. Let me run it. No error. Okay, now plt dot I am show, then cv2 dot cvt color, then comma cvt2 dot color, then bgr to brg. That is why we wrote swap rb equals to true, because every time we will convert bgr to brg, sorry, gb rgb, so we don't have to write again and again. It will convert all the files into rgb. Okay, run it. Okay, as you can see, the motorbike is coming, bicycle is coming, the person is coming, the car will come, the car is coming. Okay, so it's detecting the right for the image. Now we will do this for the video and for the webcam. We are done with this image one, and then now I will write here. Okay, so this is will do for the video. For the video, I will write here cap equals to capture. You can write any name. So cv2 dot video capture So you can take any random video. I took this Pixels George. You can comment down. Share the link. Before. App dot is open. So here I will write cap equals to CV2 dot video capture 0, and if not cap dot is open, then raise output error can't open the video. Can't open the video. Here everything will be the same. Font scale equals to 3. Okay, font equals to CV2 dot font Hershey 10. Okay, so here I will write while true comma frame equals to cap dot read. This is for the reading of the file. The same I will write class index comma confidence comma boundary box equals to model dot detect flame, and the confidence threshold equals to 0.55. Okay, everything is the same we did before. So here I will print class index. Okay, so here I will write if and the class index does not equals to 0, and what to perform is here after that for class index comma confidence comma boxes in zip class index dot flatten is the layers. Okay, confidence dot flatten box, and if class index is greater than equals to 80, then what to do? Then I will copy from here okay, the same thing I have to write here. So here I will write CV2 dot I am sure this will be the return in the frame object detection by Simplilearn, and frame. So if cv2 dot weight key 2 and 0 ffx equals to ordq. Okay, then here I will write break. Will you break when it gets into 2? The weight key will be 2. Okay, I will tell you what is the weight key. So here I will write cap dot release and cv2 dot destroy all windows. Okay, so now let me run. Let's see error. There will be error. Okay, CV Python programming language modules. Let me run it again. Are the weight keys. Okay, so video is here. The video is here. As you can see bicycle, the person, the bus, car, traffic light, the person. So our object detection for the video is coming right. Okay, person, okay, person, traffic light, bus. So this is how you can do for the video. Okay, so now we will do for the webcam live. So this is for the video. So if we want to do for the webcam, okay, so we need to just change one thing only. We have to change. Instead of giving the file, we have to write one here. Okay, the rest will be the same. Got it? So I have to just shut down my webcam. So let me shut down the webcam and get back to you. So as you can see, this is a 320 by 320 box. So this is coming right. Okay, so if I will show this, the mobile phone is coming right now. Okay, so this is how you can do the correct object detection. Okay,
So first we will open command prompt to write a command to open Jupyter Notebook. So here we will write Jupyter Notebook. Then press enter. So it will take some time. Yeah. So this is the landing page of Jupyter Notebook, and here we have to new, then Python 3. So this is how the Jupyter Notebook UI look like. So at first we will import some major libraries of Python, which help in creating a mass detection system. So here I will write import cv2, os, and press enter. Then I will give the path, then data path equals to c, then slash users, then slash slp 09375, then slash desktop, then slash, then face, mask detection, then slash dataset. Okay, so here it will be slash, my bad, sorry, then slash. Okay, it's look fine. So here I will write categories equals to os dot list directory list dir. Then I will assign data underscore path. Then I will create some labels equals to here I will write here I for I in range. Then here I will give length of categories. Yeah. Then press enter. Then here I will write label. Then dict directory equals to directory. Then zip. Then categories comma labels. Yeah. So here I will write print. Then label directory. Okay. Then I will print categories. Then I will print labels. Okay, then press enter. Yeah. So here CV means capturing video. The CV2 function in OpenCV can read video capture by using pass 0. As a function parameter, we can access our webcam. We may pass RTSP URL in the function parameter to capture CCTV footage, which is quite helpful for video analysis. Then OS, this OS module. The OS module in Python has function for adding and deleting folders, retrieving their contents, changing the directory, locating the current directory, and more. Before you can communicate with the underlying operation system, you must import the OS module and this OS list directory to retrieve a list of all files and folders in the given directory. Use Python os.list directory method. The list of files or directory in the current working directory will be returned if no directory is specified. Then label. The, the tkinterWidget class called a label is used to show text or an image. The user views the label, they cannot be interact with it. So moving forward, I will write code. So just stay with me. After that, I will explain you line wise. Okay. So here I will write that image underscore size equals to 100. Then I will create two classes, data, then target. Okay, arrays. Then I will write here for category in categories folder underscore path equals to os dot path, then dot join, then data underscore path comma category. Okay, then img image names equals to os dot list directory, then folder path. Just stay with me. I will explain you line wise. Okay, so here I will write for img name in img names img underscore path equals to os dot path dot join. Then I will write here folder. I repeat. So here we write folder underscore path, then img underscore name. So img equals to cv2 dot imread, then img underscore path. So here I will write try that gray equals to cv2 dot cvt, then capital C color, then img comma cv2 dot then color, then underscore bgr to rgb. Okay, so I will go for the gray one, cvt color bgr to rgb. Yeah, so I will write here resize. Okay, not in capital letter. Resize equals to cv2 dot resize, then gray comma img size comma img size. Why this 2 img size? Because like length and like width and breadth would be same, like 100. So press enter. So I will write data dot append, then resized, then target dot append, then label, then directory of category. Okay, so I will write here exception as E. So here I will print then exception comma E. Okay, then press enter. Let's see, there should be no error. So it is loading. Let's wait. Okay, no error. So image size should be like 100 by 100. So that is why I wrote here 100, then image size 100 by 100. And I made two arrays, like for one for data, then one for targets. So this for this gray equals to cvt.cvt color image. So converting the image into grayscale. Okay, then this line resize equals to cvt.resize gray img. So resizing the grayscale into like 100 by 100, since we need a fixed common size for all the images in the dataset. Okay, then this target dot append label directory. So appending the image like and the label categories into the list. What is list? Dataset. So like for the last print exception E. So if any exception raised, the exception will be printed here and the pass to the next image. Okay. So moving forward, let's import NumPy and save this data and the target. Okay. So I will write here import NumPy as np. Right. Then I will write here data equals to np dot array then again data by 255.0. Okay, then again data equals to np dot reshape, then data comma data dot shape, then 0 comma img size comma img size comma 1. Okay, then press enter. Then for target, let me put do just like this, then target equals to np dot array, then target. Okay, so here I will write from keras dot utils import np utils. Okay, so here I will write new underscore target equals to np underscore utils dot to underscore categories categorical, I guess categorical, then target. Okay, then press enter. So here I will save np dot save this data comma data. Okay, and np dot save this target comma new target. Okay, so press enter. Yeah, so NumPy is a Python library used for working with arrays. It also has a function for working with in the domain of linear algebra and matrices. It is an open source project and you can use it freely. NumPy stands for Numerical Python and is Keras. A Python interface for artificial neural network is provided by the open source software package known as Keras. The TensorFlow library interface is provided by the Keras. A number of backends were supported by Keras up until version 2.3, including TensorFlow, Microsoft Cognitive. So this is the part of the data processing. This part of the data processing. So let me write here data preprocessing. So the data preprocessing part is done. Now we will create the another file of this Python for the training CNN. CNN means convolutional neural network. Okay, test data comma train underscore target comma test underscore target equals to train underscore split. Then we will split on data and target comma test size should be 0.1. Okay, so now I will give press enter. Okay, train split is not defined. Okay, it is train test split. Yeah, so now I will write checkpoint equals to model checkpoint, then again model I repeat. So here I will write model, comma, epoch, then 0 3D dot model. Okay. So here I will write comma monitor equals to value loss underscore loss comma verbose equals to 0 comma save best only equals to true comma mode equals to mode should be auto. Okay, then I will press enter. Then here I will write history equals to model dot fit to train underscore data comma okay train underscore target comma apochs equals to 20 comma callbacks equals to checkpoint comma validation underscore split equals to 0.2, the best ratio. Okay, so let me present. Okay, there is one error. Model dot fit got 10x. Okay, there should be a spelling mistake. epoch pochs equals to 20. Dot model, it is fine. Then monitor equals to value loss. Then verbose equals to 0. Save best only equals to true. Then mode. Okay, so here I have to write. Maybe it will. So it will take some time to go till 20. Okay, so it will download one by one. So we will wait for a while. So the model checkpoints are completed. So here I will write print, then model dot evaluate. Okay, here I will write test underscore data comma test underscore target. Then press enter. Okay, so I hope you guys understand till here. If you have any question or any query regarding any code, just put as in comments. Our team will shortly provide you the correct solution. Okay, so moving forward, we will create another file for detecting mask. Okay, so I will go here and then new file Python. So I will write here detecting mask file. Okay, yeah. So I will import some libraries here. Keras dot models import load models. We will import cv2 and we will import numpy as np. So press enter. Okay, numpy as np. Okay, so press enter. So what I will do, I will write here model equals to load underscore model, then okay, Keras model from Keras cannot import name. Okay, so it is model only. Yeah. So here I will write model equals to load model. So I will write here model 017 dot model. Okay. Okay, so here I will write face underscore classifier equals to cv2 dot cascade classifier. So this is one file for frontal face default. So you can find this file on the description box below. So I will write here r cascade underscore frontal face underscore default dot xml. Okay, so source equals to cv2 dot video capture 0. It will open our camera. So labels underscore directory equals to 0 mask and 1 for no mask. Okay, so color directory equals to like no mask for red and mask for green. Okay, so here at 0, then 0 comma 2 55 comma 0, then again comma for 1 there should be 0 comma 0 comma 255. Okay, so I hope you guys understand till here. So if you have any question or any query regarding any code, so just put as in comments. Our team will shortly provide you the correct solution. So the code is written. So let me run this. For this, first I have to first I have to close my this person on screen camera. So the code is running fine. Now it is showing no mask. Now it is showing mask. So I hope you guys understand till here. If you have any queries, any question regarding any code, just put as his comment. Our team will shortly provide you the correct solution. So in today's session, we will discuss what image classification is, and moving ahead, we will discuss what CNN is, and at the end, we will do a hands-off lab demo of image classification using CNN. So before we move on to the programming part, let's discuss what image classification is and proceed further for the same. What is image classification? The process of classifying an entire image is known as image classification. Images are anticipated to have just one class per image. Models for image classification take an image as input and produce a prediction of the class to which the image belongs. So we can utilize image classification models when we are not interested in individual instance of items with position information or their shape. So let's see what is CNN. Machine learning includes convolutional neural networks, also known as convents or CNNs. It is a subset of the several artificial neural network models that are employed for diverse purpose and datasets. A CNN is a particular type of network design for deep learning algorithm that is utilized for tasks like image recognition and pixel data processing and so more. Okay. Although there are different kinds of neural network in deep learning, CNNs are preferred neural architect for identifying and recognizing objects. Therefore, they are really suited for computer vision activities and applications where accurate object recognition is crucial, such as facial and self-driving automobile system. So moving ahead, so dear learners, if you want to upskill your AI and machine learning skills, so give yourself a chance to simply learn professional certificate program in AI and machine learning, which comes with the completion certificate and in-depth knowledge of AI and machine learning. Check this course out details from the description box below. So now let's move to our programming part of how to do image classification using CNN.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So first we will open a command prompt to write a command to open Jupyter Notebook. So here we will write Jupyter Notebook. Press enter. So this is the landing page of Jupyter Notebook. So here you can select new Python file. So this is how the kernels look like. Okay, Jupyter Notebook kernels look like. So first we will import some major libraries of Python which will help us in like analyzing the data. Okay. So in this file we will classify small images of CIFAR 10 dataset from TensorFlow Keras dataset. There are total 10 classes as shown below. So we will use CNN for the classification purpose. Okay. So here I will write import TensorFlow as TF. Okay. So from TensorFlow dot Keras import datasets comma layers models. Okay. So we will import NumPy as NP, right? And import Matplotlib as PLT, right? Okay, so here I will write pyplot as PLT, right? So TensorFlow, this. So TensorFlow is a free and open source machine learning and artificial intelligence software library. It can be used for a variety of applications, but it focuses on mainly deep neural network training and the inference purpose. Okay, got it? And this NumPy. NumPy is a Python library used for working with arrays. It also has a function for working with the domain of linear algebra and matrices. It is an open source project and you can use it freely. NumPy stands for numerical Python. And this third one, Matplotlib. For Python and its numerical extension NumPy, Matplotlib is a cross-platform data visualization and graphical charting package. As a result, it presents a strong open source substitute for MATLAB. The APIs, application programming interfaces for Matplotlib allow programmers to incorporate graphs into GUI applications. Got it? So let's run this. Let me change image classification using CNN. Okay. So let's load the dataset. Okay, we will load the dataset from the load data function. So here I will write x underscore train comma y underscore train. Okay, and one for test x underscore test comma y underscore test. Okay, then equals to dataset data sets dot we are using cipher 10 cipher 10 far 10 dot load dot underscore data. Okay, so it will load our data. So let's load the data. So data is loaded. Let's see x underscore test dot shape. Okay, yeah. So as you can see, so we have 1000 rows and one more x underscore train dot shape. Let me run this. So here you can see, like we see like training data, like training images are 50,000 and the test images are 10,000. Okay, so this is for testing, this is for training. And so moving ahead, we will see for the y train dot shape. Okay, 1000, and here we will see the array. So y underscore train no, 5. Okay, let's run this first. Let me give some space. Yeah. So here y underscore train is a 2D array. Like for our classification, having 1D array is a good enough. So what we will do, we will convert this to now 1D array. This is 2D array. We will convert into 1D array. Okay. For that, we will write here y underscore train equals to y underscore train dot reshape -1 comma. Okay. Then y underscore train and again semicolon 5. Let's run this. Okay, so now this is 1D array. So y underscore test equals to y underscore test dot reshape in -1. Here I will write classes equals to, there are some classes, okay, in the data set, like airplane, comma, automobile, comma, bird, comma, cat, comma, deer, comma, dog, and frog, horse, ship, the truck. Okay, so these are the some classes like airplane, automobile, bird, cat, deer. So it will be help in classifying the images. So let's plot some images to see like what they exactly are. Okay. So what we will do, we will create one function for that. Let me write here def plot underscore sample. Okay. Then x comma y comma index. Okay. Then I will write here plot dot figure plt dot figure. then figure size should be comma 2 equals to plt dot show image show to I am show x index plt dot x label classes y index. Okay, so let's see some samples of the images. So I will write a plot underscore sample x underscore train comma y underscore train. Okay, comma let's see the fifth image. Okay, then enter. Should be capital. So as you can see, this is a car, so it is showing automobile. Okay, so let's see once more, like plot underscore sample x underscore train comma y underscore test comma we'll see the 10th one. Okay, it is not quite visible, so we'll go for the 11. Okay. Okay, why it is showing wrong, because I use here test. I have to use here train instead of test, then it will show, I think, correct. Yeah, you can see horse, then horse. Then what about 201 image? See, you can see. So we will see once more. 500. You can see frog. Okay, it's not quite visible. Yeah. So you can see here the proper shape. Okay. So what we will do now, we will normalize the images to a number from 0 to 1. Image has 3 channels like RGB colors. So, and each value in the channel can range from 0 to 255. Hence, to normalize in 0 to 1 range, we need to divide it by 255. Okay. So now what we will do, we will normalize the data. So here, what we will do at x underscore train equals to x underscore train divided by 255.0. Okay. And same for test equals to x underscore test divided by 255.0. Okay, to range between 0 to 1. Yeah, we will build simple artificial neural network for image classification first. Okay, so we will write here ANN equals to models dot sequential. Okay, then I will write here layers dot flatten input underscore shape equals to 32 comma 32 comma 3. Okay, then again layers dot dense 3000 comma activation equals to ReLU. Got it? Then again for the 1000, so what I will do, I will copy it and paste it here. Okay, so here 1000. So let me add one more layer dot dense, then we'll add 10 comma activation equals to softmax. Okay, here I will, okay, let me give for the better visuals. Yeah, so ann dot compile optimizer, okay, equals to sgd, then comma, I will write here loss equals to sparse categorical cross entropy. Okay, so here I will write comma, then matrix equals to accuracy, and ann dot fit underscore train comma y underscore train comma epochs. Okay, so number I will give epochs equals to 5, right? So it will take time to run. It's running. Here there is some issue. Underscore train epochs equals to 5. What it is saying, end user code, the file program C engine. Okay, so I will copy it and paste it again. Run it again. Okay, now it's working. Okay, so it will take time and then I will get back to you. Okay, then import numpy. You guys already know what numpy is. Np y underscore prediction equals to ann dot predict x underscore test. Okay, then y underscore prediction underscore classes equals to np dot argument max element or element in y underscore prediction. Print classification port comma classification underscore report, then y underscore test comma y underscore prediction underscore classes. Okay, so let me run this. This is capital. Yeah, it will take less time. Now we will create a graph. Okay, Like X text is like we have 1,000 images, so graph will be like messed up. Still, let's see. So I write here import cborn as SNS. Okay, okay, cborn. Yeah, let me give some space. Here I will write plt dot figure, because size should be 14,7. Okay, then SNS we will create a heat map for this. Then y underscore prediction not equals to true. Then plt dot y label is truth. Okay. Plt dot x label prediction. Then plt dot title should be fusion. Okay, then plt dot show. Let me run this. Okay. See, y prediction has x text. It's still running. Let's wait. So now let's make CNN model, okay, to train our images. So for that, I will write CNN equals to models dot sequential. Okay, right here, go paste here. Yeah. So let me run this. So this is our CNN model from which we will train our images, and CNN like compile, then optimizer equals to Adam. Okay. Okay, comma right here. Then loss equals to sparse categorical. Okay, then cross entropy. Okay, and comma. I will write here matrix equals to accuracy. Run this. Okay, loss. Yeah, same goes for you. Okay, loss. What will I do? I will rewrite this. Okay, now let's check CNN model for the 10 epochs. Okay, let's see the accuracy is increasing or not. CNN dot. Let's go train. comma y underscore train, comma box equals to it is started. It will take less time than the previous one. Okay. See, you want this whole code, you can comment down the same. Okay. So after completing this, I will get back to you. So it is almost done, like 27 seconds with 10 epochs. Till then, let me write CNN dot evaluate x underscore test, comma y underscore test. Okay. So with CNN, the end 5 epoch accuracy was around like 70%, and which is a significant improvement over ANN. Okay, ANN we have like just 49. Okay, and CNNs are the best for image classification and gives the superb accuracy. Also, computation is the much less compared to simple ANN, as max pooling reduces the image dimension while still preserving these features. Okay, so let me run this. It'll take some time. Till then, I will write y underscore prediction equals to CNN dot predict and x underscore test. Okay. Then I will write a y underscore prediction, then colon 5. Let me run this. So you can see the accuracy and all, the array. Okay. Yeah. So let's classes equals to np dot arg max element or element in y prediction. Okay. Then y underscore classes, then these are the number of classes, then y underscore test is column 5. These are the array, so it's converted into array. Then now let's see the it is predicting right image or wrong image. Okay, by not with the training data. Here we predict from the training data, y training, x train. Okay, now we will predict from the test data. So here I will write plot underscore sample, then x underscore test, comma y underscore test, and you can write the random one. So here I will write 60. Let's see. So you can easily see here this is horse and it is predicting right horse. And let me okay, plot underscore sample, then x underscore test, comma y underscore test, comma 100. Okay, press enter. Okay, x is capital. Yeah, so you can see this is deer. Okay, so our model is predicting the correct image. Okay, then what we like, let's see it is predicting the right class or not. Okay, we made the classes like random classes. Okay, where are these? So let's see it is predicting right or wrong. Okay, for that I have to write classes y underscore classes. It's like which number? 60. Okay, 60. Okay, 60 is not defined because like number of classes. Okay, okay. So there are 1, 2, 3, 4, 5, 6, 7. Okay, 0 to 9. I can choose. So here what I will do, I will take the small one, like I will 5. Okay, this is frog. Okay, it's frog, right? So I will take instead of 60 here I will see frog. Okay, y class is not defined. Y underscore classes. Is defined. See, okay, there are 3s. Yeah. So as you can see, frog. This is frog. So our class is defining right. So here I will write it again like 60. It was horse. And let me write here 60. You can see the right prediction. Okay. So this is what how you can do image classification using CNN. I hope you guys must have understood this concept, like how to do image classification using CNN. In today's session, we will go through what is movie recommendation system. After that, we will see how movie recommendation system work. Moving forward, we will see filtering strategies for movie recommendation system, and at the end, we will see hands-on lab demo like how to create movie recommendation system using Python in detail. We already have dataset with us. We will perform different function and implement a movie recommendation system using Python. Before we move on to the programming part, let's discuss what is movie recommendation system actually is and proceed further for the same. So, renting CDs and DVDs, reading local TV listenings, watching film strip projectors or recordings. All of this is a thing of the past today. All of the world's biggest film collections have been digitized and moved to the online streaming services like Netflix, HBO or YouTube. These platforms can now help us with what is possibly the most difficult task of all, choosing a movie. They have been enhanced with AI powered capabilities. Well, that is no longer a concern for you. It is finally time for machine learning to put its skills on display in the modern cinematic landscape. To create advanced predictive system for true movie expert, data scientists are prepared to investigate our behavioral patterns and those of movies. A movie recommendation system, also known as a movie recommender system, uses machine learning to predict or filter user film preferences based on their prior decision and actions. It is an advanced filtration system that anticipates the consumer in question potential, like selection for a domain specific item, a movie. So after seeing what is movie recommendation system, let's move forward and see how movie recommendation system actually works. A movie recommendation system fundamental idea is a pretty straightforward. Every recommender system primarily consists of two components, users and items. User receive more prediction from the system and the actual movies are the products. Filtering and predicting only the movies that a matching user is most likely to wish to see in the main objective of movie recommendation system. The user information from the system database is used by the ML algorithm for these recommendation system. Based on information from the past, this data is used to forecast the user in question's behavior in the future. Data should be handled by expert because it is so crucial to ML projects, including the movie recommendation system. After seeing how movie recommendation system works, let's see some filtration strategies for movie recommendation system. To assist user in finding the most relevant films, movie recommendation system employ a variety of filtration techniques and algorithms. The content-based filtering and the collaborative filtering system subcategories of the ML algorithm used for the movie recommendations are the most well-liked ones. Filtering based on content or content-based filtering, a method of filtering movies in a movie recommendation system that makes advantage of the item's data. This information, which is taken from the just one user, is quite important in this case. This technique uses an ML algorithm to suggest movies that are comparable to the user's past choices. Therefore, the information about the prior movie choices and likes just one person is used to generate similarity in content based filtering. And the second one is collaborative filtering. As the name implies, this filtering technique is based on the interaction between the relevant person and the other user. For the best outcomes, the system contrasts and compares these behaviors. It combines the film choices and uses patterns of several people. Like there are two types of collaborative filtering algorithm. The first one is collaborative filtering based on users. The goal is to find patterns in target users and other database users, like movie preferences. And the second one is collaborative item based filtering. The fundamental idea behind this is to find comparable products like movies, that target users rate or interact with. So after seeing the filtering strategies for movie recommendation system, so here is one question for you guys. I will give you 1 minute for this. You can comment or you can give answer in chat section, so I can see if the answers given by you are right or wrong. I'm repeating again. So here is one question for you guys. I will give you 1 minute, exactly 1 minute for this. You can comment or you can give your answer in chat section, so I can see if the answers given by you are right or wrong. So the question is, which is the best language for machine learning programming? Which is the best language for machine learning? The first one is Java. The second one is Python. The third one is R language, and the fourth one is C++. So this is the question. I am repeating again. Which is the best language for machine learning? The option one is Java, second Python, R language, and C++. So I am starting timer of 1 minute. Just type your answers in comment section or in a chat section. Do let me know your answers. Please, I want that everyone should participate in this and make this live session interesting. So I am starting timer. So your time starts now. Please guys, do let me know your answers in chat section or in you can comment down. $42 to go. You can comment or you can give your answer in the chat section, so I can see if the answers given by you are right or wrong. 30 seconds more. Which is the best language for machine learning? You can give your answer in chat section or you can comment, so I can see if the answers given by you are right or wrong. Guys, come on, please. I want that everyone should participate in this and make this live section interesting. Come on guys, 5 seconds more. 1. Yep, time up. So time is over. We will give reply those who gave correct answer, and those who didn't give correct answer, we will give you a reply with the correct answer. So now let's move to our programming part to perform movie recommendation system using Python. So first we will open command prompt to write command to open Jupyter notebook. So we will write Jupyter notebook, press enter. So this is the landing page of Jupyter notebook, and select here new Python file. So this is how Jupyter Notebook UI look like? So at first, we will import some major libraries of Python, which will help us in mathematical functioning. So the first one is NumPy. Import NumPy as NP. So NumPy is a Python library used for working with arrays. It also has a function for working in the domain of linear algebra and matrices. It is an open source project and you can use it freely. NumPy stands for numerical Python. So here NP is denoting NumPy. So we will import the next library. Import pandas as PD. This should be space. Yup. So Pandas is a software library written for the Python programming language for data manipulation and analysis. In particular, it offers data structures and operation for manipulating numerical tables and time series. So after importing libraries, we will move ahead and import dataset. So for importing dataset, we have to write, like we have two dataset with us. Let me show you the dataset. We have two dataset with us. The first one is credits. This one. And the second one is movies one. This one, movies one. So don't worry, you can get these dataset link in the description box. So let me write here credits underscore data frame equals to pd dot read underscore csv. Here you have to give your location of the dataset credits dot csv. The second one is movies. Let's go data frame. This is for movie data frame pd dot read csv. Okay. So here you have to give the movie location, movie dataset location, movies dot csv. Okay, everything seems good. Let me run this. Yeah. So then here PD is for the pandas library, read is used for reading the dataset from the machine, and CSV is used for the type of file which you want to read. So after this, let's write code to see the dataset. So we will write here credits underscore df and we will run it. So this is our credit dataset, and next one is movies underscore. So this is our movie dataset. So this is how our both dataset look like. So here you can see 3 dots, this one, and here also this one. So we are unable to see our full dataset. Like what if we want like full 4803 rows? So at that case we can write here pd dot set underscore option. Okay, and here we will write display dot max underscore columns, this, and here we will write none. Same for the rows, pd dot set option display dot max underscore rows none. Okay, none. Let's run this. So now if we will write credits underscore df. It is running. Yeah. So now you can see your full data set, like full credit data set with 4803 rows or 4802 rows, because there is this is starting from 0, that's why. So what about movies data set? Okay, wait, running. It is still running, you can see here. So here you can see the full data set, movie data set with 4802 rows. Or if you want to see only 5 top rows, so you can write here credits underscore df dot head. So by this, only 5 top rows. So from head we can see our 5 top rows, and if we will use tail instead of head, we can see our last 5 rows. So here let me do with the movies one, df dot tail. Yeah. So here you can see 4798 row, 4799 till 4802. So with tail we can see our last 5 rows. So moving forward, let's merge the credit dataset to movie dataset, because if we will combine them, the confusion will be less, and at the end it will be better for us. So we will write here movies underscore equals to movies underscore data frame and credits underscore df on title. Okay, T is small, I guess. Yeah, perfect. Title. So let me do something like this. Okay, it is saying data frame object is not callable. Credits underscore df movies. Okay, why? Because we haven't wrote merge here. Now it will work. Yeah, perfect. It's working. So data is merged. Let's see the number of rows and column using shape function. So now we have only one. So movies underscore df dot shape. Okay, let's run it. 4809 and 23. But if we see here, like in movies dataset, so in movies dataset, here, here, there are 20, and in here we are 4 columns in credit dataset. So like, so you will be thinking, that's why not 24? Why only 23 columns? That is why on title, you can see here on title, the titles in both titles are same. You can see here both titles are same in both. Okay, let me show you like this. Okay, Avatar, Pirates of the Caribbean, Spectre, and so on. Here you can see Avatar, Pirates of the Caribbean, Spectre, and so on. So that is why on title, written while merging, so title are same. So moving forward, let's see our merged dataset. So we will write only movies underscore data frame dot head. Yeah. So our data is merged. You can see the last cast, crew, movie ID. Yeah, you can see here movie ID, title are the same. They are merged, cast, crew. Okay guys. Let me give some more for the better view. Yeah. So you can see all columns of credit dataset are added to movies one. So moving forward, let's see another function like movies underscore df dot info. So by this, yes, you can see. So by this, the data frame information is printed via the info method. The data includes the total number of columns, their labels, data kinds, memory use, range index, and the number of cells in each column, like non-null values. Note that info method does indeed print the information. So here you can see all the information is printed. Okay, like columns name and the all null values, count and data types too, like this int, object, int, in which we are working most. So after this, let's move forward and select some main column in which we are working most. So we will write movies underscore df equals to movies underscore df underscore d title, comma, and another one is overview. Okay, why? Okay, here we have to get like this. Yeah. So here we have to write genre. Genre is complete, and we will work on what keywords. Keywords are the main keywords. Okay, keywords. Then to cast. Then we will do recommendation with the crew as well. Okay. So by running this, let me see our data again with 7. Okay, there is one error. Okay, this is movie. The movie is idea of genre, no? Yeah, not in index. Okay, got it. Why not genre? It's genres, I guess. What it is, it's genres. That's why. It's genres. Okay. Yeah, so let's see our data again with 7 columns. So I will write here movies underscore df dot head here. Right. So you can see only we have like movies ID same, title, overview, genres, keywords, cast and crew only. So here you can see the selected columns. Okay, so let's move forward and once again let's see the info again, like movies underscore df dot info is come with selected columns, and let's move forward and see how many missing values are present in particular column. So like the columns is full, we can see here, but we don't know about that 4803 values are filled or not. So what we will do it, we will see how many missing values are present there. So here we will write like movies underscore df dot is null dot sum. It's not like this. Yeah, perfect. So the function data frame is null. This one is null. Dot sum. Dot sum returns the number of missing values in the dataset. So here you can see overview have 3 missing values. So what we can do is we can write here movies underscore df dot drop na place equals to true. Okay, we will run it. It's saying okay, it's document drop na equals to true. Okay, fine. Dot underscore drop na, and Yeah, it will not create any issue. So if you set in place equals to true, the drop any method will modify your data frame directly. That means that if you set in place equals to true, the drop any will drop all missing values from your original data set. Let's move forward and see movies underscore df dot duplicated So the duplicate method returns a series with true and false values that describe which rows in the data frame are duplicated or not. Use the subset parameter to specify if any column should not be considered when looking for duplicates. So here let me run this first. So here we are getting 0. Why 0? So if you are like thinking there is no true or false return, so if you write it without sum, like if I will write it without sum, okay, let me copy from here. Yeah, and I will run this. So here you can see false, false, false in whole data set. So sum will combine them and return you a value. At the end, 0 represent false itself. So we do not need this. So we will write something else. So moving forward, let me write first movies underscore df dot I location 0 dot genres. Let me run this. So the ilog function, this one, ilog function. First, let me do something like this. It will go up. Okay, huh. Okay, so from ilog function in Python is defined in the pandas module that helps us to select a specific row or column from the dataset. Using the ilog method in Python, we can easily retrieve any particular value from a row or column by using index value. So here 0th position line is coming, which is here you can see. So name action, like name action, name adventure, name fantasy, this sci fiction, this one science fiction. Yeah. So this is because I am giving here genre. That is why you can see here. See ID 28 name action, name something 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 like that. Okay. So let's import something called AST, abstract syntax tree. So this is one of the major library. Import AST. Let me run this. Import is a class defined is the AST module that is used to express the import statement in Python in the form of abstract syntax tree. So an abstract syntax tree or just syntax tree is a tree representation of the abstract syntactic structure of text written in a formal language. Each node of the tree denotes a construct occurring in the text. So let's convert some like literal to object and append them. So here I will write def convert obj object like L equals to blank array for I in ast dot literal repeat ev bj object. Okay, like L dot append return here we are converting is like here is a convert is a function and L is a array to append by using for loop. We can append them to name. So let me write code, then I will explain like what is happening. So let me write full code. So movies underscore df like genres, okay, equals to movies genres, and then dot apply what. So then movies underscore df, then I will write keywords equals to movies underscore df, keywords apply underscore df dot. So if we will see our old data set, in that, like, we will see old data set, in that genre and that's keyword, this keyword apps id name and so on, like id, that name, like this type of things. So it will create a mess in retrieving them. So by using ast library, we just convert them to the normal one, like title. So got it, guys? So I hope you guys understand till here. If you have any question or any query regarding any code or question, just put as in comment. Our team will shortly provide you the correct solution. I'm repeating again. I hope you guys understand till here. If you have any type of questions regarding any code or something, so just put as in comments. Our team will shortly provide you the correct solution. So moving forward, let's convert cast to and like same as previous way, like this only. So what we will do here, we will write def convert. Yeah, here I am using, so L equals to counter equals to 0, st dot literal if counter does not equals to 3, then L dot L dot append. Okay, then here I have to write I to name. Okay, counter equals to 1. If you want to write like counter is equals to counter plus 1, it is like both the same. Else take done L. So let me run this. Okay, so after this small code, we have to assign the values, like we are doing it for cast now. So movies, okay, movies underscore df, then cast equals to movies underscore df cast dot apply convert. Everything seems good. So let's see the changes are visible or not. So we will write here movies underscore df dot head. You can ignore this, like this is nothing. So here you can see cast is also same like keyword and genre. So like let's do for the crew too. So like we are converting, you can say, in a structured way. So let's do for the crew one too. So let me put some Yeah. So here we will add def like fetch, which is nothing like a function name, fetch director obj. Okay. Colon L equals to for I in ast dot literal obj if I like job also is equals to like we can say director. So then L dot append L dot append mm, L dot append to the same name, but return capital L. So we have to again write that movies crew equals to movies in crew apply h. Just remember fetch director is a function name. Let's see changes. So here I have to write movies, then press enter. So yeah, crew is all set. So changes are visible and data is looking good. So what we like, if I want to see the first movie avatar overview, this like this dot 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 dot. So I have to write here like movies overview at 0th place. So yeah, so this is a full overview of Avatar movie. Like let me read for this. In this 22nd century, a paraplegic marine is dispatched and blah 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 and civilization. So moving forward, that what we want to recommend movie in the basis of overview, genre, keyword, cast. So for that we need a separate words like in the then 22nd century along. So if you will see in other columns, all the words are separated, but like here, if you will see all the words are separated, like action is separated, adventure is separated, fantasy is separated. So there is a long sentence in this one in the overview one. There's a long sentence. So it's difficult to recommend from this. So what we are going to do is, well, we will separate them like other columns. So here we will write movies overview equals to movies then overview and dot apply my bad, sorry, then lambda colon x dot split. Yeah, error. So let's see the results. So movies. Yeah, you can see in the set one. So now you can see all the words are separated by comma. So now it will easy to match overview to recommend a particular movie. So moving forward, so what we are going to do is, if there is a two word and space between there, so we are going to remove that space. So here you can see science fiction are separate. Okay, so we are going to remove this one, this space. So let's write code for that. So here I will write like overview is already done, so we will not do for that. So let's write code for the rest columns. So here I have to write movies, like genres equals to movies, and again genres dot apply lambda x I dot replace space to no space. It seems good. Then I have to write for everywhere. So for I in X. It's for I in X. For I in X. Movies genres equals to movie genres dot apply lambda X. I dot replace this to this for. Seems good. So let's copy paste this. See. One for keywords and one for cast and crew. Cast first, then you test is same. So let me run this. Okay, no error, seems good. So let's see the changes. So movies, yeah. So now you can see the science fiction space is gone. Like here is science fiction space is there. Now science fiction space is gone. Yep. So like, okay, let's move forward and create one new column name as tag and put all the column data in a particular column. Okay, let me do first. Yeah, let me write movies. This is a column or one column name equals to movies. Then first we will put overview plus movies and genres and movies. And what we have to give, keywords, then again movies, then cast, me run this. Okay, so let's see the data frame. Movies. Okay, still coming. So like there is one problem, I guess. Yeah, no. So here you can see all the data is merged in a under tag column. Yes, you can see like in the second century, blah blah blah. So I hope you guys understand till here. If you have any question or any query regarding any code or anything, just put as in comment or our team will shortly provide you the correct solution. Okay, so I'm repeating again. I hope you guys understand till here. If you have any question or any query regarding any code or like any question, just put as in comment. Our team will shortly provide you the correct solution. So from here, let's create a new data frame. Okay, so let me create new data frame because now we don't need this overview, cast, crew, genre, like columns like this. We have already merged into a one column like tag column. So we will write here new df equals to movies. Okay. So like movies, we need movie ID. New data frame, we need movie ID, comma, we need title, and we have everything in tag column, tags column. So we need tags column. Okay, let's run this. Let's see our new data frame. Yeah. So this is how our new data look like with only 3 columns like movie ID, title, and tags. So here you can see array brackets like this array brackets. So we are gonna remove them. So we will do what we will write here. We will write new data frame that in tags equals to new data frame tags dot apply lambda x, then I will give space dot join seems good, everything is okay. Okay, fine. Yeah, so let's see the results. So we will write here new underscore data frame. So you can see the brackets are removed. Now let's see the data which is present in the 0th index in tag column, like this dot 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 in the okay. For that we have to write here a new data frame tags. We did it before, like for the overview. So here we have to, yeah. So this is the whole data in the first index, 0th index. So some part of the overview like from civilization, and some are, you can see this action, adventure, fantasy, science fiction. These are some like genres, and like here you can see like these are some crews members, and yeah, like Sam Worthington, like there are some cast crew. Okay, so like moving forward, like what we are going to do is just make them in lowercase for the better prediction, like something in capital and something in like smaller. So let's make it to lowercase. So new underscore df tags equals to new underscore df tags dot apply the colon x dot lower. Okay, so don't worry about this error. Let's see the result. New underscore df dot yeah, now all the data present at tag column is in small case, or you can say lowercase. Moving forward, let's do some feature extraction using count vectorizer. So let me write first from sklearn dot feature extraction. Okay, cool. Dot text import count vectorizer cv equals to count vectorizer underscore features equals to like 5000 top words equals to English, and this, yeah. So count vectorizer Okay, there is a like cannot import count vectorizer from sklearn from user. Okay, sorry, my bad here. V is capital. Okay, guys, so V is capital. Yeah, so no error. So count vectorizer is a great tool provided by the scikit-learn library in Python. It is used to transform a given text into a vector on the basis of the frequency count of each word that occurs in the entire text. So let me write something. cv dot fit underscore transform f x like dot to array shape. Okay, so the fit method like learns a vocabulary dictionary of all tokens in the raw documents. That is, it creates a dictionary of tokens. By default, the tokens are words separated by spaces and like punctuation. So that maps each single token to a position in the output matrix. So here CV is a counter vectorizer. So let's convert into vector to array. So for this we have to write vectors equals to cv dot fit, okay, then transform x in. So here we have to write dot to array. Yeah, then we have to write vector its vectors. Yeah, you can see vector to array all the zeros. Okay, so moving forward, let's get the feature name by writing. Okay, so we will write here len cv dot get feature names. Okay, then bracket yeah. So okay, we have like 500 feature names. So I'm saying again, like I hope you guys understand till here. If you have any question or any query regarding any code, whatever it is, so just put as in comments. Our team will shortly provide you the correct solution. Okay guys, like any code or you are not understand anything, just put as in comment. Our team will shortly provide you the correct solution. So let's import some major library, which is import NLTK. So what is NLTK? The Natural Language Toolkit NLTK is a platform used for building Python programs that work with human language for applying in statistical natural language processing NLP. It contains text processing libraries for tokenization, parsing, classification, stemming, tagging, and semantic reasoning. So moving forward, like from, let me write first, from NLTK dot stem dot porter import porter yes equals to porter stemming is a process for reducing a word to its word stem, that suffix and prefix or to the roots of words known as a lemma. Stemming is important in natural language understanding NLU and natural language processing NLP. So here, like I have to write, so here I will write def stem to text y equals to for I in text dot split y dot append dot stem done dot join y. So let's apply stemming to a tag column. So here we will write new df tags equals to new df tag dot apply stem. So let's import cosine similarity from sklearn. So here we will write from sklearn dot matrices dot pairwise import cosine underscore similarity. Okay, it seems good from sklearn matrices matrix dot pairwise it is pairwise import cosine similarity. Okay, let's run this, no error. So cosine similarity measures the similarity between two factors. I repeat, cosine similarity measures the similarity between two vectors of an inner product space. It is measured by the cosine of the angle between two vectors and determines whether two vectors are pointing in roughly the same direction. It is often used to measure document similarity in text analysis. So here we will write cosine underscore similarity vectors. So these all are the vector present. Let's see the cosine similarity vector column and row using space. So here I will write cosine similarity vectors dot shape. So it's still running, you can see here. Yeah. So 4806 rows and 4806 columns are there. Let's assign variable similarity to this. Okay. So let's similarity, we'll write like this. Similarity equals to cosine similarity underscore here. Why I did this? Because we don't have to write always this long sentence or long keyword, you can say. So moving forward, let's see first column. Like we will write similarity yeah. So this is our first column. So let's see the rows only. So we will write here similarity 0 dot shape. Okay, 4806. Okay. So let's move forward and let's create some like sorted list. So for that sorted, okay, list, enumerate, spelling is fine. Okay, one more, like similarity, 0. Here I have to write reverse equals to true, comma key equals to lambda colon x, not capital X, x. Have to write 1 colon 6. Seems good. Yeah. So the enumerate function in Python converts a data collection object into an enumerate object. Enumerate returns an object that contains a counter as a key for each value with an object, making item within a collection easier to access. So finally, let's create the recommend function to check the movie recommendation system. Okay. So let's write here def recommend movie text. So new df, in the df title equals to movie x 0 tenses equals to similarity and movie okay. So movies list equals to sorted list enumerate ret enumerate distances comma reverse equals to true, keyword sorry key only, key equals to lambda x colon x 1 and colon 6, or I in movies list df dot iloc I 0 0 dot title, because we need title only. So yeah, it seems good. Okay, so finally that like time is came. So finally the time is come to check the recommendation of your favorite movies. So you can comment in the chat section so I can check. So let me write first recommend for movie Avatar. Okay, so here you can see the recommendation system is working fine. So Titan A.E, Small Soldier, Independence Day are the recommendation for the movie Avatar. So let me check for the another one recommend, like for one of my favorite movie Iron Man. So here you can see Iron Man 2, Iron Man 3, Avengers Age of Ultron, Captain America and the Avengers are the recommendations for the movie Iron Man. So let me check for the one more recommend. Liar. It is going on 30, and the last one I want to check is Captain America Civil War. Let me copy from here only. Yeah, you can see the Captain America, the first Avenger, the Winter Soldier, Iron Man 3, Age of Ultron, the Avengers. So I hope you guys understand till here. If you have any questions or any query regarding any code or question, just put as in comments. Our team will shortly provide you the correct solution.
If you want to become an AI expert and gain handsome salary packages, look at the wide range of AI ML courses by Simplilearn in collaboration with top universities across the globe. By enrolling in any of these certification programs, you will gain expertise in skills like generative AI, prompt engineering, chat GPT, explainable AI, machine learning algorithms, supervised and unsupervised learning, model training, and optimization, and there's much more on the list. With hands-on experience in the tools like ChatGPT, DALL-E, Python, OpenCV, and TensorFlow, you will catch the eyes of top recruiters. So what are you waiting for? Hurry up and enroll now. An year of experience is preferred to enroll in these courses. Find the course link in the description box.
Interview questions for machine learning. Now, this video will probably help you when you're attending interviews for machine learning positions, and the attempt here is to probably consolidate 30 most commonly asked questions and to help you in answering these questions. We tried our best to give you the best possible answers, but of course what is more important here is, rather than the theoretical knowledge, you need to kind of add to the answers or supplement your answers with your own experience. So the responses that we put here are a bit more generic in nature, so that if there are some concepts that you are not clear, this video will help you in kind of getting those concepts cleared up as well. But what is more important is that you need to supplement these responses with your own practical experience. Okay, so with that, let's get started. So one of the first questions that you may face is, what are the different types of machine learning? Now, what is the best way to respond to this? There are three types of machine learning. If you read any material, you will always be told there are three types of machine learning. But what is important is you would probably be better off emphasizing that there are actually two main types of machine learning, which is supervised and unsupervised. And then there is a third type, which is reinforcement learning. So supervised learning is where you have some historical data and then you feed that data to your model to learn. Now, you need to be aware of a keyword that they will be looking for, which is labeled data. Right? So if you just say past data or historical data, the impact may not be so much. You need to emphasize on labeled data. So what is labeled data? Basically, let's say if you're trying to train your model for classification, you need to be aware of, for your existing data, which class each of the observations belong to, right? So that is what is labeling. So it is nothing but a fancy name, you must be already aware, but just make it a point to throw in that keyword labeled, so that will have the right impact. Okay, so that is what is supervised learning, when you have existing labeled data which you then use to train your model. That is known as supervised learning. And unsupervised learning is when you don't have this labeled data. So you have data, it is not labeled. So the system has to figure out a way to do some analysis on this. Okay, so that is unsupervised learning. And you can then add a few things like what are the ways of performing supervised learning and unsupervised learning, or what are some of the techniques. So supervised learning, we perform, or we do regression and classification, and unsupervised learning we do clustering. Okay? and clustering can be of different types. Similarly, regression can be of different types, but you don't have to probably elaborate so much. If they are asking for just the different types, you can just mention these and just at a very high level you can. But if they want you to elaborate, give examples, then of course I think there is a different question for that. We will see that later. Then the third, so we have supervised, then we have unsupervised, and then reinforcement. You need to provide a little bit of information around that as well, because it is sometimes a little difficult to come up with a good definition for reinforcement learning. So you may have to a little bit elaborate on how reinforcement learning works. Right? So reinforcement learning works in such a way that it basically has two parts to it. One is the agent and the environment, and the agent basically is working inside of this environment, and it is given a target that it has to achieve, and every time it is moving in the direction of the target, so the agent basically has to take some action, and every time it takes an action which is moving the agent towards the target, right, towards a goal. A target is nothing but a goal. Okay, then it is rewarded, and every time it is going in a direction where it is away from the goal, then it is punished. So that is the way you can a little bit explain, and this is used primarily or very, very impactful for teaching the system to learn games and so on. Examples of this are basically used in AlphaGo. You can throw that as an example where AlphaGo used reinforcement learning to actually learn to play the game of Go, and finally it defeated the Go world champion. Right? This much of information that would be good enough. Okay. Then there could be a question on overfitting. So the question could be, what is overfitting and how can you avoid it? So what is overfitting? So let's first try to understand the concept, because sometimes overfitting may be a little difficult to understand. Overfitting is a situation where the model has kind of memorized the data. So this is an equivalent of memorizing the data. So we can draw an analogy so that it becomes easy to explain this. Now let's say you're teaching a child about recognizing some fruits or something like that. Okay? And you're teaching this child about recognizing, let's say, 3 fruits: apples, oranges, and pineapples. Okay, so this is a small child, and for the first time you're teaching the child to recognize fruits. Then, so what will happen? So this is very much like that is your training data set. So what you will do is you will take a basket of fruits which consists of apples, oranges, and pineapples. Okay, and you take this basket to this child, and there may be, let's say, hundreds of these fruits. So you take this basket to this child and keep showing each of this fruit, and then first time obviously the child will not know what it is. So you show an apple and you say, hey, this is apple. Then you show maybe an orange and say this is orange, and so on and so forth. And then again you keep repeating that, right? So till that basket is over. This is basically how training works. In machine learning also, that's how training works. So till the basket is completed, maybe 100 fruits, you keep showing this child. And in the process, what has happened, the child has pretty much memorized these. So even before you finish that basket, right, by the time you are halfway through, the child has learnt about recognizing the apple, orange, and pineapple. Now what will happen after halfway through? Initially you remember it made mistakes in recognizing, but halfway through now it has learned. So every time you show a fruit, it will exactly 100% accurately it will identify. It will say, the child will say this is an apple, this is an orange, and if you show a pineapple, it will say this is a pineapple. Right? So that means it has kind of memorized this data. Now let's say you bring another basket of fruits, and it will have a mix of maybe apples, which were already there in the previous set, but it will also have, in addition to apple, it will probably have a banana or maybe another fruit like a jackfruit. Right? So this is an equivalent of your test data set, which the child has not seen before. Some parts of it probably has seen, like the apples it has seen, but this banana and jackfruit it has not seen. So then what will happen? In the first round, which is an equivalent of your training data set, towards the end it has 100% it was telling you what the fruits are. Right? Apple was accurately recognized, orange was accurately recognized, and pineapples were accurately recognized. Right? So that is like 100% accuracy. But now when you get a fresh set which were not a part of the original one, what will happen? All the apples maybe it will be able to recognize correctly, but all the others like the jackfruit or the banana will not be recognized by the child. right? So this is an analogy, this is an equivalent of overfitting. So what has happened during the training process, it is able to recognize or reach 100% accuracy, maybe very high accuracy, okay? And we call that as very low loss, right? So that is the technical term. So the loss is pretty much zero and accuracy is pretty much 100%. Whereas when you use testing, there will be a huge error, which means the loss will be pretty high and therefore the accuracy will be also low. Okay, this is known as overfitting. This is basically a process where training is done. Training process it goes very well, almost reaching 100% accuracy, but while testing, it really drops down. Now, how can you avoid it? So that is the extension of this question. There are multiple ways of avoiding overfitting. There are techniques like what you call regularization. That is the most common technique that is used for avoiding overfitting. And within regularization, there can be a few other subtypes like dropout in case of neural networks and a few other examples. But I think if you give example or if you give regularization as the technique, probably that should be sufficient. So there will be some questions where the interviewer will try to test your fundamentals and your knowledge and depth of knowledge and so on and so forth. And then there will be some questions which are more like trick questions that will be more to stump you. Okay, then the next question is around the methodology. So when we are performing machine learning training, we split the data into training and test, right? So this question is around that. So the question is, what is training set and test set in machine learning model, and how is the split done? So the question can be like that. So in machine learning, when we are trying to train the model, so we have a 3-step process. We train the model and then we test the model, and then once we are satisfied with the test, only then we deploy the model. So what happens in the train and test is that you remember the labeled data. So let's say you have 1,000 records with labeling information. Now, one way of doing it is you use all the 1,000 records for training, and then maybe, right, which means that you have exposed all these 1,000 records during the training process, and then you take a small set of the same data and then you say, okay, I will test it with this. Okay, and then you probably, what will happen, you may get some good results. Right? But there is a flaw there. What is the flaw? This is very similar to human beings. It is like you are showing this model the entire data as a part of training. Okay, so obviously it has become familiar with the entire data. So when you're taking a part of that again and you're saying that I want to test it, obviously you will get good results. So that is not a very accurate way of testing. So that is the reason what we do is we have the label data of this 1,000 records or whatever. We set aside, before starting the training process, we set aside a portion of that data and we call that test set, and the remaining we call as training set, and we use only this for training our model. Now, the training process, remember, is not just about passing one round of this data set. So let's say now your training set has 800 records. It is not just one time you pass this 800 records. What you normally do is you actually, as a part of the training, you may pass this data through the model multiple times. So this 1,000 records may go through the model maybe 10, 15, 20 times till the training is perfect, till the accuracy is high, till the errors are minimized. Okay, now, so which is fine, which means that that is what is known as the model has seen your data and gets familiar with your data. And now when you bring your test data, what will happen is this is like some new data, because that is where the real test is. Now you have trained the model and now you are testing the model with some data which is kind of new. That is like a situation, like a realistic situation, because when the model is deployed, that is what will happen. It will receive some new data, not the data that it has already seen, right? So this is a realistic test. So you put some new data. So this data which you have set aside is for the model, it is new. And if it is able to accurately predict the values, that means your training has worked. Okay, the model got trained properly. But let's say while you're testing this with this test data, you're getting a lot of errors. That means you need to probably either change your model or retrain with more data and things like that. Now, coming back to the question of how do you split this, what should be the ratio? There is no fixed number. Again, this is like individual preferences. Some people split it into 50-50, 50% test and 50% training. Some people prefer to have a larger amount for training and a smaller amount for test, so they can go by either 60-40 or 70-30, or some people even go with some odd numbers like 65-35 or 63.33 and 33, which is like 1/3 and 2/3. So there is no fixed rule that it has to be something, the ratio has to be this. You can go by your individual preferences. All right, then you may have questions around data handling, data manipulation, or what do you call data management or preparation. So these are all some questions around that area. There is again no one answer, one single good answer to this. It really varies from situation to situation, and depending on what exactly is the problem, what kind of data it is, how critical it is, what kind of data is missing, and what is the type of corruption. So there are a whole lot of things. This is a very generic question, and therefore you need to be a little careful about responding to this as well. So probably have to illustrate this again. If you have experience in doing this kind of work in handling data, you can illustrate with examples saying that I was on one project where I received this kind of data. These were the columns where data was not filled, or these were this many rows where the data was missing. That would be, in fact, a perfect way to respond to this question. But if you don't have that, obviously, if you have to provide some good answer, I think it really depends on what exactly the situation is. And there are multiple ways of handling the missing data or corrupt data. Now, let's take a few examples. Now, let's say you have data where some values in some of the columns are missing, and you have pretty much half of your data having these missing values in terms of number of rows. Okay, that could be one situation. Another situation could be that you have records or data missing, but when you do some initial calculation, how many records are corrupt, or how many rows or observations, as we call it, has this missing data. Let's assume it is very minimal, like 10%. Okay. Now, between these two cases, how do we? So let's assume that this is not a mission critical situation, and in order to fix this 10% of the data, the effort that is required is much higher, and obviously effort means also time and money, right? So it is not so mission critical, and it is okay to, let's say, get rid of these records. So obviously one of the easiest ways of handling the data part or missing data is remove those records or remove those observations from your analysis. So that is the easiest way to do. But then the downside is, as I said, as in the first case, if let's say 50% of your data is like that, because some column or the other is missing. So it is not like in every place, in every row, the same column is missing, but you have in maybe 10% of the records, column 1 is missing, and another 10% column 2 is missing, another 10% column 3 is missing, and so on and so forth. So it adds up to maybe half of your data set. So you cannot completely remove half of your data set, then the whole purpose is lost. Okay, so then how do you handle? Then you need to come up with ways of filling up this data with some meaningful value, right? That is one way of handling. So when we say meaningful value, what is that meaningful value? Let's say for a particular column, you might want to take a mean value for that column and fill wherever the data is missing, fill up with that mean value, so that when you're doing the calculations, your analysis is not completely way off. So you have values which are not missing, first of all, so your system will work. Number two, these values are not so completely out of whack that your whole analysis goes for a toss. Right? There may be situations where if the missing values, instead of putting mean, maybe a good idea to fill it up with the minimum value or with a 0. So, or with a maximum value. Again, as I said, there are so many possibilities. So there is no like one correct answer for this. You need to basically talk around this and illustrate with your experience. As I said, that would be the best. Otherwise, this is how you need to handle this question. Okay, so then the next question can be, how can you choose a classifier based on a training set data size? So again, this is one of those questions where you probably do not have like a one size fits all answer. First of all, you may not, let's say, decide your classifier based on the training set size. maybe not the best way to decide the type of the classifier. And even if you have to, there are probably some thumb rules which we can use, but then again, every time. So in my opinion, the best way to respond to this question is you need to try out few classifiers irrespective of the size of the data, and you need to then decide on your particular situation which of these classifiers are the right ones. This is a very generic issue, so you will never be able to, just by, if somebody defines a problem to you, and somebody, even if they show the data to you or tell you what is the data or even the size of the data, I don't think there is a way to really say that yes, this is the classifier that will work here. No, that's not the right way. So you need to still, test it out, get the data, try out a couple of classifiers, and then only you will be in a position to decide which classifier to use. You try out multiple classifiers, see which one gives the best accuracy, and only then you can decide. Then you can have a question around confusion matrix. So the question can be, explain confusion matrix. Right? So confusion matrix, I think the best way to explain it is by taking an example and drawing like a small diagram. Otherwise it can really become tricky. So my suggestion is to take a piece of pen and paper and explain it by drawing a small matrix. And confusion matrix is about to find out, this is used especially in classification learning process, and when you get the results, when our model predicts the results, you compare it with the actual value and try to find out what is the accuracy. Okay, so in this case, let's say this is an example of a confusion matrix, and it is a binary matrix. So you have the actual values, which is the labeled data, right? And which is, so you have how many yes and how many no. So you have that information, and you have the predicted values, how many yes and how many no, right? So the total actual values, the total yes is 12 plus 1, 13, and they are shown here. And the actual value no's are 9 plus 3, 12. Okay, so that is what this information here is. So this is about the actual, and this is about the predicted. Similarly, the predicted values, there are yes are 12 plus 3, 15 yeses, and no are 1 plus 9, 10 no's. Okay, so this is the way to look at this confusion matrix. Okay, and out of this, what is the meaning conveyed? So there are 2 or 3 things that needs to be explained outright. The first thing is, for a model to be accurate, the values across the diagonal should be high, like in this case, right? That is one. Number 2, the total sum of these values is equal to the total observations in the test data set. So in this case, for example, you have 12 plus 3, 15 plus 10, 25. So that means we have 25 observations in our test data set. Okay, so these are the 2 things you need to first explain, that the total sum in this matrix, the numbers, is equal to the size of the test data set, and the diagonal values indicate the accuracy. So by looking at it, you can probably have an idea about, is this an accurate model? Is the model being accurate? If they're all spread out equally in all these 4 boxes, that means probably the accuracy is not very good. Okay. Now, how do you calculate the accuracy itself, right? How do you calculate the accuracy itself? So it is a very simple mathematical calculation. You take sum of the diagonals, right? So in this case, it is 9 plus 12, 21, and divide it by the total. So in this case, what will it be? Let me take a pen. So your diagonal values is equal to, if I say D is equal to 12 plus 9, so that is 21, right? And the total data set is equal to, right, we just calculated, it is 25. So what is your accuracy? It is 21 by, so your accuracy is equal to 21 by 25. And this turns out to be about 85%. Right? So this is 85%. So that is our accuracy. Okay. So this is the way you need to explain, draw a diagram, give an example, and maybe it may be a good idea to be prepared with an example so that it becomes easy for you. You don't have to calculate those numbers on the fly, right? So a couple of hints are that you take some numbers which add up to 100. That is always a good idea, so you don't have to really do this complex calculations. So the total value will be 100, and then diagonal values you divide. Once you find the diagonal values, that is equal to your percentage. Okay. All right. So the next question can be a related question about false positive and false negative. So what is false positive and what is false negative? Now, once again, the best way to explain this is using a piece of paper and pen. Otherwise, it will be pretty difficult to explain this. So we use the same example of the confusion matrix, and we can explain that. So a confusion matrix looks somewhat like this, and when we just take it looks somewhat like this, and we continue with the previous example where this is the actual value, this is the predicted value, and in the actual value we have 12 plus 1 13 yeses and 3 plus 9 12 no's, and the predicted values, there are 12 plus 3 15 yeses and 1 plus 9 10 no's. Okay, now in this particular case, which is the false positive, what is a false positive? First of all, the second word, which is positive, okay, is referring to the predicted value. So that means the system has predicted it as a positive, but the real value, so this is what the false comes from, but the real value is not positive. Okay, that is the way you should understand this term, false positive or even false negative. So false positive, so positive is what your system has predicted. So where is that system predicted? This is the one. Positive is what? Yes. So you basically consider this row. Okay, now if you consider this row, so this is all positive values. This entire row is positive values. Okay, now the false positive is the one where the actual value is negative. Predicted value is positive, but the actual value is negative. So this is a false positive, right? And here is a true positive. So the predicted value is positive and the actual value is also positive. Okay, I hope this is making sense. Now let's take a look at what is false negative. False negative. So negative is the second term. That means that is the predicted value that we need to look for. So which are the predicted negative values? This row corresponds to predicted negative values. All right. So this row corresponds to predicted negative values. And what they are asking for? False. So this is the row for predicted negative values, and the actual value is this one, right? This is predicted negative and the actual value is also negative. Therefore, this is a true negative. So the false negative is this one. Predicted is negative, but actual is positive. Right? So this is the false negative. So this is the way to explain, and this is the way to look at false positive and false negative. Same way, there can be true positive and true negative as well. So again, positive, the second term you will need to use to identify the predicted row, right? So if we say true positive, we need to take for the predicted part. So predicted positive is here. Okay, and then the first term is for the actual. So true positive. So true in case of actual is yes, right? So true positive is this one. Okay, and then in case of actual, the negative. Now we are talking about, let's say, true negative. True negative. Negative is this one, and the true comes from here. So this is true negative. Right? 9 is true negative. The actual value is also negative and the predicted value is also negative. Okay, so that is the way you need to explain this, the terms false positive, false negative, and true positive, true negative. Then you might have a question like, what are the steps involved in the machine learning process, or what are the 3 steps in the process of developing a machine learning model, right? So it is around the methodology that is applied. So basically, the way you can probably answer in your own words, but the way the model development of the machine learning model happens is like this. So first of all, you try to understand the problem and try to figure out whether it is a classification problem or a regression problem. Based on that, you select a few algorithms and then you start the process of training these models. Okay, so you can either do that, or you can, after due diligence, you can probably decide that there is one particular algorithm which is most suitable. Usually it happens through trial and error process, but at some point you will decide that, okay, this is the model we are going to use. Okay, so in that case, we have the model, algorithm, and the model decided, and then you need to do the process of training the model and testing the model. And this is where, if it is supervised learning, you split your data, the labeled data, into training data set and test data set. And you use the training data set to train your model. And then you use the test data set to check the accuracy, whether it is working fine or not. So you test the model before you actually put it into production, right? So once you test the model, you're satisfied, it's working fine, then you go to the next level, which is putting it for production. And then in production, obviously, new data will come and the inference happens. So the model is readily available, and only thing that happens is new data comes and the model predicts the values, whether it is regression or classification. Now, so this can be an iterative process. So it is not a straightforward process where you do the training, do the testing, and then you move it to production. No. So during the training and test process, there may be a situation where because of either overfitting or things like that, the test doesn't go through, which means that you need to put that back into the training process. So that can be an iterative process. Not only that, even if the training and test goes through properly and you deploy the model in production, there can be a situation that the data that actually comes, the real data that comes, with that, this model is failing. So in which case you may have to once again go back to the drawing board. Or initially it will be working fine, but over a period of time, maybe due to the change in the nature of the data, once again the accuracy will deteriorate. So that is again a recursive process. So once in a while, you need to keep checking whether the model is working fine or not. And if required, you need to tweak it and modify it and so on and so forth. So net, this is a continuous process of tweaking the model and testing it and making sure it is up to date. Then you might have question around deep learning. So because deep learning is now associated with AI, artificial intelligence, and so on. So it can be as simple as what is deep learning? So I think the best way to respond to this could be deep learning is a part of machine learning. And then obviously the question would be then what is the difference, right? So deep learning, you need to mention there are two key parts that interviewer will be looking for when you are defining deep learning. So first is, of course, deep learning is a subset of machine learning. So machine learning is still the bigger, let's say, scope, and deep learning is one part of it. So then what exactly is the difference? Deep learning is primarily when we are implementing these our algorithms, or when we are using neural networks for doing our training and classification and regression and all that, right? So when we use neural network, then it is considered as deep learning. And the term deep comes from the fact that you can have several layers of neural networks, and these are called deep neural networks, and therefore the term deep, deep learning. The other difference between machine learning and deep learning, which the interviewer may be wanting to hear, is that in case of machine learning, the feature engineering is done manually. What do we mean by feature engineering? Basically, when we are trying to train our model, we have our training data, right? So we have our training labeled data, and this data has several, let's say if it is a regular table, it has several columns. Now each of these columns actually has information about a feature, right? So if we are trying to predict height, weight, and so on and so forth, so these are all features of human beings. Let's say we have census data and we have all this. So those are the features. Now there may be probably 50 or 100, in some cases there may be 100 such features. Now all of them do not contribute to our model, right? So we as a data scientist, we have to decide whether we should take all of them, all the features, or we should throw away some of them. Because again, if we take all of them, number one, of course, your accuracy will probably get affected, but also there is a computational part. So if you have so many features and then you have so much data, it becomes very tricky. So in case of machine learning, we manually take care of identifying the features that do not contribute to the learning process, and thereby we eliminate those features and so on, right? So this is known as feature engineering, and in machine learning we do that manually. Whereas in deep learning, where we use neural networks, the model will automatically determine which features to use and which to not use, and therefore feature engineering is also done automatically. So this is an explanation. These are two key things probably will add value to your response. All right, so the next question is, what is the difference between, or what are the differences between machine learning and deep learning? So here, this is a quick comparison table between machine learning and deep learning. And in machine learning enables machines to take decisions on their own based on past data. So here we are talking primarily of supervised learning. And it needs only a small amount of data for training, and then works well on low-end systems, so you don't need large machines. And most features need to be identified in advance and manually coded. So basically the feature engineering part is done manually. and the problem is divided into parts and solved individually and then combined. So that is about the machine learning part. In deep learning basically enables machines to take decisions with the help of artificial neural networks. So here in deep learning we use neural networks. So that is the key differentiator between machine learning and deep learning. And usually deep learning involves a large amount of data, and therefore the training also requires, usually the training process requires high-end machines because it needs a lot of computing power. And the machine learning features the feature engineering is done automatically. So the neural networks takes care of doing the feature engineering as well. And in case of deep learning, therefore, it is said that the problem is handled end to end. So this is a quick comparison between machine learning and deep learning in case you have that kind of a question. Then you might get a question around the uses of machine learning or some real life applications of machine learning in modern business. The question may be worded in different ways, but the meaning is how exactly is machine learning used, or actually supervised machine learning. It could be a very specific question around supervised machine learning. So this is like give examples of supervised machine learning, use of supervised machine learning in modern business. So that could be the next question. So there are quite a few examples or quite a few use cases, if you will, for supervised machine learning. The very common one is email spam detection. So you want to train your application or your system to detect between spam and non-spam. So this is a very common business application of supervised machine learning. So how does this work? The way it works is that you obviously have historical data of your emails, and they are categorized as spam and not spam. So that is what is the labeled information. And then you feed this information or all these emails as an input to your model, right? And the model will then get trained to detect which of the emails are to detect which is spam and which is not spam. So that is the training process. And this is supervised machine learning because you have labeled data. You already have emails which are tagged as spam or not spam. And then you use that to train your model, right? So this is one example. Now, there are a few industry-specific applications for supervised machine learning. One of the very common ones is in healthcare diagnostics. In healthcare diagnostics, you have these images and you want to train models to detect whether from a particular image, whether it can find out if the person is sick or not, whether a person has cancer or not. Right? So this is a very good example of supervised machine learning. Here, the way it works is that existing images, it could be X-ray images, it could be MRI or any of these images are available and they are tagged saying that, okay, this X-ray image is defective or the person has an illness or it could be cancer, whichever illness, right? So it is tagged as defective or clear or good image and defective image, something like that. So we come up with a binary, or it could be multi-class as well, saying that this is defective to 10%, this is 25%, and so on. But let's keep it simple. You can give an example of just a binary classification, that would be good enough. So you can say that in healthcare diagnostics, using image, we need to detect whether a person is ill or whether a person is having cancer or not. So here, the way it works is you feed labeled images and you allow the model to learn from that, so that when new image is fed, it will be able to predict whether this person is having that illness or not, having cancer or not, right? So I think this would be a very good example for supervised machine learning in modern business. All right, then we can have a question like, so we've been talking about supervised and unsupervised, then so there can be a question around semi-supervised machine learning. So what is semi-supervised machine learning? Now, semi-supervised learning, as the name suggests, it falls between supervised learning and unsupervised learning, but for all practical purposes it is considered as a part of supervised learning. And the reason this has come into existence is that in supervised learning, you need labeled data. So all your data for training your model has to be labeled. Now, this is a big problem in many industries or under many situations. Getting the labeled data is not that easy because there's a lot of effort in labeling this data. Let's take an example of the diagnostic images. We can just let's say take X-ray images. Now there are actually millions of X-ray images available all over the world, but the problem is they are not labeled. So their images are there, but whether it is defective or whether it is good, that information is not available along with it, right, in a form that it can be used by a machine, which means that somebody has to take a look at these images, and usually it should be like a doctor, and then say that, okay, yes, this image is clean and this image is cancerous, and so on and so forth. Now that is a huge effort by itself. So this is where semi-supervised learning comes into play. So what happens is there is a large amount of data, maybe a part of it is labeled. Then we try some techniques to label the remaining part of the data so that we get completely labeled data, and then we train our model. So I know this is a little long winding explanation, but unfortunately there is no quick and easy definition for semi-supervised machine learning. This is the only way probably to explain this concept. We may have another question as what are unsupervised machine learning techniques, or what are some of the techniques used for performing unsupervised machine learning? So it can be worded in different ways. So how do we answer this question? So unsupervised learning, you can say that there are two types, clustering and association. And clustering is a technique where similar objects are put together. And there are different ways of finding similar objects. So their characteristics can be measured, and if they have, in most of the characteristics, if they are similar, then they can be put together. This is clustering. Then association, I think the best way to explain association is with an example. In case of association, you try to find out how the items are linked to each other. So for example, if somebody bought maybe a laptop, the person has also purchased a mouse. So this is more in an e-commerce scenario, for example. So you can give this as an example. So people who are buying laptops are also buying a mouse. So that means there is an association between laptops and mouse. Or maybe people who are buying bread are also buying butter. So that is a association that can be created. So this is unsupervised learning, one of the techniques. Okay. All right, then we have very fundamental question. What is the difference between supervised and unsupervised machine learning? So machine learning, these are the two main types of machine learning, supervised and unsupervised. And in case of supervised, and again here, probably the keyword that the person may be wanting to hear is labeled data. Now, very often people say, we have historical data, and if we run it, it is supervised, and if we don't have historical data, yes, but you may have historical data, but if it is not labeled, then you cannot use it for supervised learning. So it's very key to understand that we put in that keyword labeled. Okay. So when we have labeled data for training our model, then we can use supervised learning. And if we do not have labeled data, then we use unsupervised learning. And there are different algorithms available to perform both of these types of trainings. So there can be another question, a little bit more theoretical and conceptual in nature. This is about inductive machine learning and deductive machine learning. So the question can be, what is the difference between inductive machine learning and deductive machine learning, or somewhat in that manner, so that the exact phrase or exact question can vary. They can ask for examples and things like that, but that could be the question. So let's first understand what is inductive and deductive training. Inductive training is induced by somebody, and you can illustrate that with a small example. I think that always helps. So whenever you're doing some explanation, try as much as possible, as I said, to give examples from your work experience or give some analogies, and that will also help a lot in explaining as well, and for the interviewer also to understand. So here we'll take an example, or rather we will use an analogy. So inductive training is when we induce some knowledge or the learning process into a person without the person actually experiencing it. Okay, what can be an example? So we can probably tell the person or show a person a video that fire can burn his finger, or fire can cause damage. So what is happening here? This person has never probably seen a fire or never seen anything getting damaged by fire. But just because he has seen this video, he knows that, okay, fire is dangerous, and if fire can cause damage. Right? So This is inductive learning. Compared to that, what is deductive learning? So here you draw conclusion, or the person draws conclusion out of experience. So we will stick to the analogy. So compared to the showing a video, let's assume a person is allowed to play with fire. Right? And then he figures out that if he puts his finger, it's burning, or if he throws something into the fire, it burns. So he is learning through experience. So this is known as deductive learning. Okay, so you can have applications or models that can be trained using inductive learning or deductive learning. All right, I think probably that explanation will be sufficient. The next question is, are KNN and k-means clustering similar to one another, or are they same? Right, because the letter K is kind of common between them. Okay, so let us take a little while to understand what these two are. One is KNN, another is k-means. KNN stands for K nearest neighbors, and k-means, of course, is the clustering mechanism. Now, these two are completely different, except for the letter K being common between them. KNN is completely different. K-means clustering is completely different. KNN is a classification process, and therefore it comes under supervised learning, whereas k-means clustering is actually unsupervised. Okay, when you have KNN, when you want to implement KNN, which is basically K nearest neighbors, the value of K is a number. So you can say K is equal to 3. You want to implement KNN with K is equal to 3. So which means that it performs the classification in such a way that, how does it perform the classification? So it will take 3 nearest objects, and that's why it's called nearest neighbor. So basically, based on the distance, it will try to find out its nearest objects that are, let's say, 3 of the nearest objects, and then it will check whether the class they belong to which class, right? So if all 3 belong to one particular class, obviously this new object is also classified as that particular class. But it is possible that they may be from 2 or 3 different classes. Okay, so let's say they are from 2 classes, and then if they are from 2 classes, now usually you take a odd number, you assign an odd number to. So if there are 3 of them and 2 of them belong to one class and then 1 belongs to another class, so this new object is assigned to the class to which the 2 of them belong. Now, the value of K is sometimes tricky, whether should you use 3, should you use 5, should you use 7. That can be tricky because the ultimate classification can also vary. So it's possible that if you're taking K as 3, the object is probably in one particular class, but if you take K is equal to 5, maybe the object will belong to a different class, because when you're taking 3 of them, probably 2 of them belong to class 1 and 1 belong to class 2. Whereas when you take 5 of them, it is possible that only 2 of them belong to class 1 and 3 of them belong to class 2. So which means that this object will belong to class 2, right? So you see that? So the class allocation can vary depending on the value of K. Now, k-means, on the other hand, is a clustering process, and it is unsupervised, where what it does is the system will basically identify how the objects are, how close the objects are with respect to some of their features. Okay, but the similarity, of course, is the letter K, and in case of k-means also we specify its value, and it could be 3 or 5 or 7. There is no technical limit as such, but it can be any number of clusters that you can create. Okay, so based on the value that you provide, the system will create that many clusters of similar objects. So there is a similarity to that extent that K is a number in both the cases, but actually these two are completely different processes. We have what is known as naive Bayes classifier, and people often get confused thinking that naive Bayes is the name of the person who found this classifier or who developed this classifier, which is not 100% true. Bayes is the name of the person, B-A-Y-E-S is the name of the person, but naive is not the name of the person, right? So naive is basically an English word, and that has been added here because of the nature of this particular classifier. Naive Bayes classifier is a probability based classifier, and it makes some assumptions that presence of one feature of a class is not related to the presence of any other feature of maybe other classes, right? So which is not very
very strong or not a very, accurate assumption, because these features can be related and so on. But even if we go with this assumption, this whole algorithm works very well, even with this assumption. And that is the good side of it. But the term comes from there. So that is the explanation that you can give. Then there can be question around reinforcement learning. It can be paraphrased in multiple ways. One could be, can you explain how a system can play a game of chess using reinforcement learning? Or it can be any game. So the best way to explain this is again to talk a little bit about what reinforcement learning is about and then elaborate on that to explain the process. So first of all, reinforcement learning has an environment and an agent, and the agent is basically performing some actions in order to achieve a certain goal. And these goals can be anything, either if it is related to game, then the goal could be that you have to score very high, score a high value, high number. Or it could be that your number of lives should be as high as possible. Don't lose lives. So these could be some of them. More advanced examples could be for driving. In the automotive industry, self-driving cars, they actually also make use of reinforcement learning to teach the car how to navigate through the roads and so on and so forth. That is also another example. Now, how does it work? So if the system is basically there is an agent and environment, and every time the agent takes a step or performs a task which is taking it towards the goal, the final goal, let's say to maximize the score or to minimize the number of lives and so on, or minimize the deaths, for example, it is rewarded. And every time it takes a step which goes against that goal, right, contrary or in the reverse direction, it is penalized. Okay, so it is like a carrot and stick system. Now, how do you use this to create a game of chess, or to create a system to play a game of chess? Now, the way this works is, and this could probably go back to this AlphaGo example where AlphaGo defeated a human champion. So the way it works is in reinforcement learning, the system is allowed, for example, if in this case we are talking about chess, so we allow the system to first of all watch playing a game of chess. So it could be with a human being or it could be the system itself. There are computer games of chess, right? So either this new learning system has to watch that game or watch a human being play the game, because this is reinforcement learning is pretty much all visual. So when you're teaching the system to play a game, the system will not actually go behind the scenes to understand the logic of your software, of this game or anything like that. It is just visually watching the screen and then it learns. Okay, so reinforcement learning to a large extent works on that. So you need to create a mechanism whereby your model will be able to watch somebody playing the game, and then you allow the system also to start playing the game. So it pretty much starts from scratch. Okay. And as it moves forward, it's right at the beginning, the system really knows nothing about the game of chess. Okay, so initially it is a clean slate. It just starts by observing how you're playing. So it will make some random moves and keep losing badly. But then what happens is, over a period of time, so you need to now allow the system, or you need to play with the system, not just 1, 2, 3, 4 or 5 times, but hundreds of times, thousands of times, maybe even hundreds of thousands of times. And that's exactly how AlphaGo has done. It played millions of games between itself and the system, right? So for the game of chess also, you need to do something like that. You need to allow the system to play chess and then learn on its own over a period of repetition. So I think you can probably explain it to this much, to this extent, and it should be sufficient. Now, this is another question which is again somewhat similar, but here the size is not coming into picture. So the question is, how will you know which machine learning algorithm to choose for your classification problem? Now, this is not only classification problem, it could be a regression problem. I would like to generalize this question. So if somebody asks you, how will you choose? How will you know which algorithm to use? The simple answer is, there is no way you can decide exactly saying that this is the algorithm I'm going to use. In a variety of situations, there are some guidelines. Like for example, you will obviously, depending on the problem, you can say whether it is a classification problem or a regression problem. And then in that sense, you are kind of restricting yourself to, if it is a classification problem, there
you can only apply a classification algorithm, right? To that extent, you can probably, let's say, limit the number of algorithms. But now within the classification algorithms, you have decision trees, you have SVM, you have logistic regression. Is it possible to outright say, yes, so for this particular problem, since you have explained this, now this is the exact algorithm that you can use? That is not possible. Okay, so we have to try out a bunch of algorithms, see which one gives us the best performance and best accuracy, and then decide to go with that particular algorithm. So in machine learning, a lot of it happens through trial and error. There is no real possibility that anybody can, just by looking at the problem or understanding the problem, tell you that, okay, in this particular situation, this is exactly the algorithm that you should use. Then the questions may be around application of machine learning, and this question is specifically around how Amazon is able to recommend other things to buy. So this is around recommendation engine. How does it work? How does the recommendation engine work? So this is basically the question is all about. So the recommendation engine again works based on various inputs that are provided. Obviously something like Amazon, a website or e-commerce site like Amazon collects a lot of data around the customer behavior, who is purchasing what. And if somebody is buying a particular thing, they're also buying something else. So this kind of association, right? So this is the unsupervised learning we talked about. They use this to associate and link or relate items. And that is one part of it. So they kind of build association between items, saying that somebody buying this is also buying this. That is one part of it. Then they also profile the users, right? Based on their age, their gender, their geographic location. They will do some profiling, and then when somebody is logging in and when somebody is shopping, kind of the mapping of these two things are done. They try to identify, obviously if you have logged in, then they know who you are and your information is available, like for example your age, maybe your gender, and where you're located, what you purchased earlier, right? So all this is taken, and the recommendation engine basically uses all this information and comes up with recommendations for a particular user. So that is how the recommendation engine works. All right, then the question can be something very basic, like when will you go for classification versus regression, right? When do you do classification instead of regression, or when will you use classification instead of regression? Now, yes, so this is basically going back to the understanding of the basics of classification and regression. So classification is used when you have to identify or categorize things into discrete classes. So the best way to respond to this question is to take up some examples and use it. Otherwise, it can become a little tricky. The question may sound very simple, but explaining it can sometimes be very tricky. In case of regression, we use, of course, there will be some keywords that they will be looking for. So just you need to make sure you use those keywords. One is the discrete values, and other is the continuous values. So for regression, if we are trying to find some continuous values, you use regression. Whereas if you're trying to find some discrete values, you use classification. And then you need to illustrate. What are some of the examples? So classification is like, let's say there are images and you need to put them into classes like cat, dog, elephant, tiger, something like that. So that is a classification problem. Or it can be, that is a multi-class classification problem. It could be binary classification problem, like for example, whether a customer will buy or he will not buy. That is a classification, binary classification. It can be in the weather forecast area. Now, weather forecast is again combination of regression and classification, because on the one hand, you want to predict whether it's going to rain or not. That's a classification problem. That's a binary classification, right? Whether it's going to rain or not rain. However, you also have to predict what is going to be the temperature tomorrow, right? Now, temperature is a continuous value. You can't answer the temperature in a yes or no kind of a response, right? So what will be the temperature tomorrow? So you need to give a number, which can be like 20 degrees, 30 degrees or whatever. Right? So that is where you use regression. One more example is stock price prediction. So that is where again you will use regression. So these are the various examples. So you need to illustrate with examples and make sure you include those keywords like discrete and continuous. So the next question is more about a little bit of a design related question to understand your concepts and things like that. So it is, how will you design a spam filter? So how do you basically design or develop a spam filter? So I think the main thing here is he is looking at probably understanding your concepts in terms of what is the algorithm you will use, or what is your understanding about difference between classification and regression and things like that, right? And the process, of course, the methodology and the process. So the best way to go about responding to this is we say that, okay, this is a classification problem because we want to find out whether an email is a spam or not spam so that we can apply the filter accordingly. So first thing is to identify what type of a problem it is. So we have identified that it is a classification. Then the second step may be to find out what kind of algorithm to use. Now, since this is a binary classification problem, logistic regression is a very common algorithm. But however, right, as I said earlier also, we can never say that, okay, for this particular problem, this is exactly the algorithm that we can use. So we can also probably try decision trees or even support vector machines, for example, SVM. So we will kind of list down a few of these algorithms and we will say, okay, we would like to try out these algorithms. And then we go about taking your historical data, which is the labeled data, which are marked. So you will have a bunch of emails, and then you split that into training and test data sets. You use your training data set to train your model or your algorithm that you have used, or rather the model actually. So, and you actually will have three models. Let's say you are trying to test out three algorithms, so you will obviously have three models. So you need to try all three models and test them out as well, see which one gives the best accuracy, and then you decide that you will go with that model. Okay, so training and test will be done, and then you zero in on one particular model, and then you say, okay, this is the model we will use, and then go ahead and implement that or put that in production. So that is the way you design a spam filter. The next question is about random forest. So what is random forest? So this is a very straightforward question. However, the response, you need to be again a little careful. While we all know what is random forest, explaining this can sometimes be tricky. So one thing is, random forest is kind of, in one way, it is an extension of decision trees, because it is basically nothing but you have multiple decision trees, and trees will basically, we will use for doing, if it is classification, mostly it is classification, you will use the trees for classification, and then you use voting for finding the final class. So that is the underlines. But how will you explain this? How will you respond to this? So first thing, obviously, we will say that random forest is one of the algorithms, and the more important thing that you need to, probably the interviewer is waiting to hear, is ensemble learner, right? So this is one type of ensemble learner. What is ensemble learner? Ensemble learner is like a combination of algorithms. So it is a learner which consists of more than one algorithm or more than one maybe models. Okay, so in case of random forest, the algorithm is the same, but instead of using one instance of it, we use multiple instances of it, and we use. So in a way, that is a random forest is an ensemble learner. There are other types of ensemble learners where we have, like, we use different algorithms itself. So you have one maybe logistic regression and a decision tree combined together, and so on and so forth. Or there are other ways, like for example, splitting the data in a certain way, and so on. So that's all about ensemble. We will not go into that. But random forest itself, I think the interviewer will be happy to hear this word ensemble learner. And so then you go and explain how the random forest works. So if the random forest is used for classification, then we use what is known as a voting mechanism. So basically, how does it work? Let's say your random forest consists of 100 trees, okay, and each observation you pass through this forest, and each observation, let's say it is a classification problem, binary classification 0 or 1, and you have 100 trees. Now if 90 trees say that it is a 0 and 10 of the trees say it is a 1, you take the majority, you may take a vote, and since 90 of them are saying 0, you classify this as 0. Then you take the next observation, and so on. So that is the way random forest works for classification. If it is a regression problem, it's somewhat similar, but only thing is, instead of vote, what we will do is, so in regression, remember what happens? You actually calculate a value, right? So for example, you're using regression to predict the temperature, and you have 100 trees, and each tree obviously will probably predict a different value of the temperature. They may be close to each other, but they may not be exactly the same value. So these 100 trees. So how do you now find the actual value, the output for the entire forest, right? So you have outputs of individual trees which are a part of this forest, but then you need to find the final output of the forest itself. So how do you do that? So in case of regression, you take like an average or the mean of all the 100 trees, right? So this is also a way of reducing the error. So maybe if you have only one tree, and if that one tree makes an error, it is basically 100% wrong or 100% right? But if you have, on the other hand, if you have a bunch of trees, you are basically mitigating that error, reducing that error. Okay, so that is the way random forest works. So the next question is, considering the long list of machine learning algorithms, how will you decide on which one to use? So once again, here there is no way to outright say that this is the algorithm that we will use for a given data set. This is a very good question, but then the response has to be like, again, there will not be a one size fits all. So we need to, first of all, you can probably shorten the list in terms of by saying, okay, whether it is a classification problem or it is a regression problem. To that extent, you can probably shorten the list, because you don't have to use all of them. If it is a classification problem, you only can pick from the classification algorithms, right? So for example, if it is a classification, you cannot use linear regression algorithm there. Or if it is a regression problem, you cannot use SVM, or maybe, no, you can use SVM, but maybe a logistic regression, right? So to that extent, you can probably shorten the list, but still you will not be able to 100% decide on saying that this is the exact algorithm that I'm going to use. So the way to go about is, you choose a few algorithms based on what the problem is. You try out your data, you train some models of these algorithms, check which one gives you the lowest error or the highest accuracy, and based on that, you choose that particular algorithm. Okay. All right. Then there can be questions around bias and variance. So the question can be, what is bias and variance in machine learning? So you just need to give out a definition for each of these. For example, bias in machine learning, it occurs when the predicted values are far away from the actual value. So that is a bias. Okay. And whereas they are all the values are probably, they are far off, but they are very near to each other though. The predicted values are close to each other, right? While they are far off from the actual value, but they are close to each other. You see the difference? So that is bias. And then the other part is your variance. Now variance is when the predicted values are all over the place, right? So the variance is high. That means it may be close to the target, but it is kind of very scattered. So the predicted values are not close to each other, right? In case of bias, the predicted values are close to each other, but they are not close to the target. But here they may be close to the target, but they may not be close to each other. So they are a little bit more scattered. So that is what in case of a variance. Okay, then the next question is about, again, related to bias and variance. What is the trade-off between bias and variance? Yes, I think this is an interesting question, because these two are heading in different directions. So for example, if you try to minimize the bias, variance will keep going high. And if you try to minimize the variance, bias will keep going high. And there is no way you can minimize both of them. So you need to have a trade-off saying that, okay, this is the level at which I will have my bias, and this is the level at which I will have variance. So the trade-off is that pretty much that you decide what is the level you will tolerate for your bias and what is the level you will tolerate for variance, and a combination of these two in such a way that your final results are not way off. And having a trade-off will ensure that the results are consistent, right? So that is basically the output is consistent, and which means that they are close to each other, and they are also accurate. That means they are as close to the target as possible, right? So if either of these is high, then one of them will go off the track. Define precision and recall. Now again, here I think it would be best to draw a diagram and take the confusion matrix, and it is very simple. The definition is like a formula. Your precision is true positive by true positive plus false positive, and your recall is true positive by true positive plus false negative. Okay, so that's, you can just show it in a mathematical way. That's pretty much that can be shown. That's the easiest way to define. So the next question can be about decision tree. What is decision tree pruning and why is it? So basically, decision trees are really simple to implement and understand, but one of the drawbacks of decision trees is that it can become highly complicated as it grows. Right? And the rules and the conditions can become very complicated, and this can also lead to overfitting, which is basically that during training you will get 100% accuracy, but when you're doing testing you will get a lot of errors. So that is the reason pruning needs to be done. So the purpose or the reason for doing decision tree pruning is to reduce overfitting or to cut down on overfitting. And what is decision tree pruning? It is basically that you reduce the number of branches, because as you may be aware, a tree consists of the root node, and then there are several internal nodes, and then you have the leaf nodes. Now, if there are too many of these internal nodes, that is when you face the problem of overfitting, and pruning is the process of reducing those internal nodes. Alright, so the next question can be, what is logistic regression? So basically, logistic regression is one of the techniques used for performing classification, especially binary classification. Now, there is something special about logistic regression, and there are a couple of things you need to be careful about. First of all, the name is a little confusing. It is called logistic regression, but it is used for classification. So this can be sometimes confusing. So you need to probably clarify that to the interviewer if it's really, if it is required. And they can also ask this like a trick question, right? So that is one part. Second thing is, the term logistic has nothing to do with the usual logistics that we talk about, but it is derived from log. So that the mathematical derivation involves log, and therefore the name logistic regression. So what is logistic regression and how is it used? So logistic regression is used for binary classification, and the output of a logistic regression is either a 0 or a 1, and it varies. So it's basically, it calculates a probability between 0 and 1, and we can set a threshold that can vary. Typically it is 0.5. So any value above 0.5 is considered as 1, and if the probability is below 0.5, it is considered as 0. So that is the way we calculate the probability, or the system calculates the probability, and based on the threshold it sets a value of 0 or 1, which is like a binary classification, 0 or 1. Okay, then we have a question around k nearest neighbor algorithm. So explain k nearest neighbor algorithm. So first of all, what is a k nearest neighbor algorithm? This is a classification algorithm. So that is the first thing we need to mention. And we also need to mention that the k is a number. It is an integer. And this is variable, and we can define what the value of k should be. It can be 2, 3, 5, 7, and usually it is an odd number. So that is something we need to mention. Technically, it can be even number also, but then typically it would be odd number, and we will see why that is. Okay. So based on that, we need to classify objects. Okay, we need to classify objects. So again, it will be very helpful to draw a diagram. If you're explaining, I think that will be the best way. So draw some diagram like this, and let's say we have 3 clusters or 3 classes existing, and now you want to find for a new item that has come, you want to find out which class this belongs to, right? So you go about, as the name suggests, you go about finding the nearest neighbors, right? The points which are closest to this, and how many of them you will find, that is what is defined by k. Now let's say our initial value of k was 5. Okay? So you will find the the 5 nearest data points. So in this case, as it is illustrated, these are the 5 nearest data points. But then all 5 do not belong to the same class or cluster. So there are one belonging to this cluster 1, the second one belonging to this cluster 2, 3 of them belonging to this third cluster. Okay. So how do you decide? That's exactly the reason we should, as much as possible, try to assign an odd number so that it becomes easier to assign this. So in this case, you see that the majority, actually, if there are multiple classes, then you go with the majority. So since 3 of these items belong to this class, we assign, which is basically the, in this case, the green or the tennis or the third cluster, as I was talking about. Right, so we assign it to this third class. So in this case, it is that's how it is decided. Okay, so k nearest neighbors. So first thing is to identify the number of neighbors that are mentioned as k. So in this case, it is k is equal to 5. So we find the 5 nearest points and then find out of these 5 which class has the maximum number in that. Okay, and then the new data point is assigned to that.
And with that, we have come to the end of Machine Learning Beginners to Advanced full course. I hope you found it valuable and entertaining. Please ask any questions about the topics covered in this video in the comment section below. Our experts will assist you in addressing your problems. Thank you for watching, stay safe and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.